Our universe is an endless expanse, filled with countless stars, galaxies, and mysterious objects. From the crushing gravity of black holes to the whisper-thin particles that make up dark matter, the universe continually surprises us with its strange and exhilarating phenomena. It is far more complex and wondrous than we ever imagined. In this journey, we delve deep into the most mind-bending discoveries and the most perplexing questions that modern astronomy continues to present. Together, we'll venture toward the edges of the known universe and peer into the enigmatic mysteries that may lie beyond. Take, for example, NASA's Juno mission, which has revealed astonishing details about Jupiter's atmosphere, an intricate tapestry of gases and storms far beyond what scientists had expected. One of the mission's most remarkable findings is the existence of massive cyclones, each the size of Earth, clustered around the planet's poles. These cyclones behave in ways that defy our conventional understanding of storm systems. Unlike anything seen here on Earth, these cyclones form into geometric patterns with incredible precision. At the North Pole, 8 cyclones arrange themselves in an octagonal shape, while the South Pole displays a striking pentagonal arrangement with 5 cyclones. What is truly astounding is how these storms remain stable for extended periods, refusing to merge or dissipate. This behavior challenges current meteorological models, which assumed such large-scale systems would inevitably break apart or change. Juno also uncovered another unexpected feature, an uneven distribution of ammonia in Jupiter's atmosphere. At the planet's equator, ammonia accumulates in a dense plume, an anomaly that suggests some form of deep atmospheric activity. This ammonia-rich equatorial plume may be the result of upwelling processes, where material from the planet's deep interior is brought up into the upper atmosphere. Even more astonishing is the depth of these atmospheric phenomena. Juno's data suggests that the influence of these processes reaches hundreds of miles beneath the cloud tops, offering new insights into Jupiter's inner workings. These discoveries are turning our previous assumptions about the gas giant's composition and behavior upside down, indicating that Jupiter's atmosphere is far more complex than previously thought. Meanwhile, the New Horizons mission's flyby of Pluto has forever changed our perception of this distant, icy dwarf planet. What was once considered a static, frozen world is now revealed to be a dynamic, ever-changing entity. The spacecraft's images of Pluto's surface were nothing short of breathtaking. Vast plains of ice, deep canyons, and towering mountains made of frozen water paint a picture of a world far more complex than anticipated. Among the most iconic features discovered was the heart-shaped region, informally named Tombaugh Regio, after the planet's discoverer, Clyde Tombaugh. This area, composed of a vast nitrogen ice plain called Sputnik Planitia, shows clear evidence of glacial movement and resurfacing, indicating that Pluto is not frozen in time, but is instead geologically active. Even more surprising were the findings regarding Pluto's thin atmosphere. Composed mostly of nitrogen with traces of methane and carbon monoxide, this atmosphere is far more layered and extended than scientists had predicted. The way sunlight interacts with the atmospheric particles creates a stunning, hazy visual effect that changes dramatically with the seasons. These seasonal changes indicate that Pluto's climate is more active than previously believed, and the presence of small geysers or ice volcanoes suggests that the dwarf planet may have internal heat sources. These revelations upend the long-held belief that Pluto is a lifeless, frozen body, revealing instead a planet that is constantly evolving and full of hidden surprises. Similarly, one of the most compelling discoveries regarding Europa, one of Jupiter's moons, is the evidence of a subsurface ocean beneath its icy crust. This theory is supported by a variety of scientific data. The Galileo spacecraft, for instance, observed a magnetic field around Europa that could be produced by an electrically conductive layer beneath the surface, most likely a salty ocean of liquid water. Gravity measurements have also revealed irregularities in Europa's density and mass distribution, further suggesting the presence of a thick liquid water layer beneath its icy shell. These groundbreaking discoveries are changing how we think about the solar system and the potential for life beyond Earth. As we continue to unravel the mysteries of distant worlds like Jupiter, Pluto, and Europa, it becomes clear that our universe is full of hidden wonders, waiting to be explored. What we once thought were simple, lifeless planets and moons have revealed themselves to be complex, dynamic environments. This ongoing journey into the unknown is only beginning, and as technology advances, we may soon uncover even more astonishing revelations about the universe that surrounds us. In the quest to uncover the mysteries of our solar system, Europa, one of Jupiter's moons, has become a focal point of intrigue. Surface geology offers significant visual clues about a hidden ocean beneath its icy crust. High-resolution images reveal chaotic terrain that seems to mimic the broken ice flows of Earth's polar seas. This fractured surface implies that Europa's icy crust floats atop a liquid layer as the disrupted patterns align with what we would expect from surface ice that is separated from the material beneath. The concept of a liquid ocean is further supported by the presence of dark, linear features across Europa's surface, known as lineae. These fractures are believed to be filled with subsurface material, suggesting that Europa's ice shell is flexing and stretching. This is likely caused by gravitational interactions with Jupiter and its moons, which could create conditions favorable for the upwelling of liquid water. Adding to this compelling evidence are recent observations made by the Hubble Space Telescope, which have detected plumes of water vapor erupting from Europa's surface, similar to geysers on Earth. These plumes provide strong, direct evidence of liquid water interacting with the surface. Taken together, the geological features, the fractures, and the plumes create a striking picture of an oceanic world hidden beneath Europa's frozen exterior. This discovery presents the tantalizing possibility that an environment conducive to life might exist in the depths of this distant moon. Could this hidden ocean harbor the conditions necessary for life to thrive? Only time and further exploration will tell. Moving across our solar system to Saturn, another captivating phenomenon continues to baffle scientists. The mysterious hexagonal storm pattern at Saturn's North Pole, discovered by the Voyager spacecraft in the early 1980s and later observed in greater detail by the Cassini mission, remains one of the most bizarre and puzzling phenomena observed in our cosmic neighborhood. This geometric wonder, spanning approximately 20,000 miles across, features each side measuring about 9,000 miles, wider than the diameter of Earth itself. What is even more astonishing is the hexagon's remarkable stability. It has persisted for decades and rotates with a period of about 10 hours and 39 minutes, synchronized with Saturn's internal rotation. The exact mechanism behind the formation of this structure continues to elude scientists, but one prevailing theory is that it might be created by atmospheric jet streams and fluid dynamics unique to Saturn's gaseous environment. The hexagon may be the result of a standing wave pattern, a phenomenon that occurs in rotating fluids. Laboratory experiments have demonstrated that rotating a circular tank of liquid at different speeds can produce polygonal shapes similar to the hexagon observed on Saturn, albeit on a much smaller scale. The hexagonal integrity is likely maintained by differences in wind speeds, creating a boundary where vortexes align into a neat polygonal shape. However, this still leaves many questions unanswered, especially regarding the nature of the powerful rotating storm at the hexagon's center. This storm, akin to a terrestrial hurricane but far more intense and stationary, is marked by a clearly defined eye and high-speed winds reaching up to 300 miles per hour. As researchers continue to study this extraordinary atmospheric feature, it challenges our understanding of planetary weather systems, offering new insights into dynamic principles that govern gas giants. On a different front, the discovery of liquid water on Mars has revolutionized the search for extraterrestrial life. This groundbreaking finding reignited both scientific and public interest, shifting the focus of Martian exploration. In 2015, NASA announced that recurring slope lineae, dark streaks observed on Martian slopes, were formed by seasonal flows of briny liquid water. This discovery, made possible through data from the Mars Reconnaissance Orbiter, revealed the presence of hydrated salts within the streaks, offering chemical evidence of water. Even if the water is salty, its existence opens the door to the possibility of microbial life on Mars, as liquid water is essential for life as we know it. The revelation of water has since redirected the goals of Martian exploration missions, with current rovers like Curiosity and Perseverance focusing on areas where liquid water or subsurface ice might be present. These missions are not only searching for traces of water, but are also investigating potential biosignatures, chemical signs that might indicate past or present microbial life. Rovers are drilling into Martian rock and soil, analyzing samples for organic molecules, and preparing for future missions that could bring Martian samples back to Earth for more detailed study. This shift in focus represents a paradigm change in the search for life beyond Earth, making Mars a prime target for future exploration and study. Could Mars have once supported life, or even harbor it today in its hidden subsurface waters? The answers to these questions may soon change our understanding of life's existence beyond our planet. Identifying regions with liquid water on Mars has become a cornerstone in our quest to understand the planet's potential for sustaining life. This discovery not only aids in selecting ideal landing sites for future human missions, but also has profound implications for the long-term survival of astronauts. Water, a vital resource, is essential for not only sustaining human life, but also for producing fuel and oxygen, both of which are necessary for extended missions. Furthermore, the discovery of water stretches beyond practical concerns for human exploration. It holds the key to unraveling Mars's ancient history, its climatic and geological processes, as well as the possibility of past habitability. This remarkable breakthrough has revitalized the field of comparative planetology, where scientists now look to Mars to uncover similarities and differences with Earth's own history. Through these comparisons, we can better understand the fundamental question of whether Mars could have once harbored life. The detection of liquid water on Mars has breathed new life into astrobiological research. It provides a more promising environment for life, encouraging researchers to expand their search for extraterrestrial life and explore the broader implications of this discovery for the search for life beyond Earth. Mars has once again become a central focus, its potential for ancient life sparking new waves of scientific curiosity. Meanwhile, the surprising geological activity observed on Mercury has completely shifted our understanding of this sun-scorched planet. Prior to recent missions, scientists believed that Mercury, long considered geologically dead, had cooled and contracted to the point of ceasing any major geological processes. However, data from NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015, revealed a dynamic and ever-changing landscape. The planet, once thought inert, was found to possess a number of unexpected geological features, forcing a re-evaluation of its geological history. Among the most astonishing discoveries was the presence of relatively young fault scarps, cliff-like landforms that signal tectonic activity. These scarps, formed as Mercury's surface contracts while its interior cools, challenged the previous assumption that the planet's geological activity had ceased. These features are not just remnants of the distant past. They are signs of a planet still undergoing tectonic shifts, possibly within the last few million years. This revelation suggests that Mercury is far from geologically dead, with ongoing surface deformations indicating that its core is still cooling and contracting, influencing the planet's surface today. Even more surprising were the discovery of hollows, irregular, rimless depressions found scattered across many of Mercury's craters and plains. These bright, reflective features are believed to be relatively young and may form through the sublimation of volatile substances exposed by meteor impacts. Sublimation is the process by which solid materials transition directly into a gas, an intriguing phenomenon that hints at the presence of volatile compounds beneath Mercury's surface. Given the planet's proximity to the Sun and its extreme temperatures, the formation of such features challenges previous models of Mercury as a static, desolate world. The continuous formation of these hollows serves as further evidence that Mercury's geology remains active and dynamic. In the distant reaches of the solar system, Uranus offers another perplexing mystery. The planet's tilted magnetic field and unusual rotation provide valuable insights into the processes that shaped its evolution. Unlike most planets in the solar system, whose magnetic fields are more or less aligned with their rotation axis, Uranus's magnetic field is tilted at a staggering 59 degrees relative to its rotation axis. This oddity raises significant questions about the planet's formation and the forces that have influenced its development over billions of years. The unusual behavior of Uranus's magnetic field could hold the answers to some of the most fundamental questions about the dynamics of our solar system, shedding light on the planet's past and its unique characteristics. Each of these discoveries, whether it's Mars's liquid water, Mercury's ongoing geological activity, or Uranus's magnetic field, provides us with deeper insights into the complexities of planetary formation and evolution. As we continue to explore the solar system, we inch closer to unlocking the mysteries of these worlds, expanding our understanding of the universe and our place within it. The more we learn about these planets, the more we realize that our assumptions about their dead, static natures were far from accurate. The universe is alive with unexpected activity, and as our technology advances, so too will our understanding of these fascinating celestial bodies. The mysteries of Uranus's magnetosphere have long intrigued scientists, and recent observations have only deepened our fascination with this distant planet. Uranus's magnetic field is unusually offset from its core, displaced by about 1/3 of the planet's radius, an anomaly that sets it apart from Earth and most other planets in our solar system. This oddity strongly suggests that Uranus's interior is much more complex than we originally imagined, hinting at an intricate and non-uniform composition. A leading theory to explain these magnetic peculiarities is that Uranus suffered a colossal collision early in its history, likely with a protoplanet or another massive object. This impact would have been so violent that it could have knocked the planet onto its side, creating its extreme axial tilt of roughly 98 degrees. As a result, Uranus doesn't spin like most planets, but instead rolls on its side, dramatically altering the way it orbits the Sun. The aftermath of such a catastrophic event also provides a compelling explanation for the planet's tilt-off-center magnetic field. The impact may have disrupted Uranus's internal dynamo, responsible for generating its magnetic field, creating multiple layers within the planet's icy and rocky interior. These layers could each be generating their own magnetic forces, causing the planet's magnetic field to be both offset and tilted. Supporting this theory is the fact that this impact may have stirred Uranus's interior, mixing its icy, rocky, and metallic components in ways we hadn't anticipated. This complex internal structure could have led to the creation of different dynamo zones within the planet, further complicating its magnetic field. Additionally, the violent collision would have scattered material throughout Uranus, perhaps giving rise to unusual physical states and compositions within the planet's mantle and core. These findings open a window into Uranus's violent past, providing insight into how catastrophic events might shape a planet's structure and ongoing internal processes. Understanding the planet's magnetic field could reveal much more about the forces that continue to shape Uranus's evolution today. Similarly, the Cassini mission, which ended in a dramatic finale with its plunge into Saturn's atmosphere, offered a treasure trove of scientific revelations. As Cassini made its final dives into the gap between Saturn and its innermost rings, a region about 1,200 miles wide, it gathered high-resolution data that allowed scientists to peer into Saturn's core like never before. What they discovered was groundbreaking. Saturn's core, much like Uranus's, is larger and more diffuse than once thought. It consists of a mix of rock, ice, and metallic hydrogen, stretching up to 20,000 miles in diameter. This revelation challenged previous models that depicted Saturn's core as compact and well-defined, instead suggesting that its interior is far more dynamic and complex than we had assumed. Cassini's close flybys also yielded critical insights into Saturn's iconic rings. The spacecraft's measurements showed that the rings are surprisingly lightweight, leading scientists to propose that they might be much younger than previously thought, only about 100 million years old. Over time, material from the rings is slowly falling into Saturn, a process known as ring rain, driven by the planet's magnetic field. This phenomenon suggests that Saturn's rings might eventually disappear, reshaping our understanding of their lifespan and behavior. Cassini also sampled Saturn's upper atmosphere, revealing new insights into the planet's chemical makeup. During its descent, it encountered complex organic molecules raining down from the rings into the atmosphere, hinting at the intricate interplay between the planet's rings and its dynamic atmosphere. In contrast, Jupiter's Great Red Spot, an iconic storm that has been raging for more than 300 years, has similarly captivated scientists. This immense hurricane-like storm is not just an astronomical curiosity, it offers vital clues about the planet's atmospheric processes. The Great Red Spot measures an astounding 12,000 miles in width and 25,000 miles in length, making it larger than Earth itself. Winds within the storm can reach speeds of up to 400 kilometers per hour, and its reddish hue is likely due to complex chemical reactions between atmospheric compounds and ultraviolet radiation from the sun. Despite its enduring presence, recent observations have shown that the Great Red Spot is undergoing significant changes. Over the last few decades, the storm has been shrinking. Its size has decreased by more than half, and it has transformed from its original oval shape into a more circular one. Currently, it measures about 10,000 miles across. The color within the spot has also fluctuated, sometimes appearing more vividly red, while other times it looks more muted. These changes indicate that Jupiter's atmosphere is dynamic, and scientists are still working to determine the causes. One hypothesis suggests that smaller vortices around the Great Red Spot might be siphoning off its energy, contributing to its gradual shrinkage. Another possibility is that shifts in Jupiter's broader atmospheric conditions are influencing the storm's behavior. Though the future of the Great Red Spot remains uncertain, its ongoing transformation provides a unique opportunity for scientists to study the forces at work in Jupiter's chaotic atmosphere, offering insights that could apply to other planetary systems both within and beyond our solar system. These planetary phenomena, Uranus's unusual magnetosphere, Saturn's dynamic rings and interior, and Jupiter's changing Great Red Spot, each reflect the incredible complexity of planetary bodies. Their study not only enhances our understanding of these individual planets, but also offers a glimpse into the broader processes that govern planetary formation, evolution, and weather systems across the universe. The insights gained from missions like Cassini and telescopes like Hubble continue to shape our evolving picture of the solar system, offering clues that could one day reveal the secrets of distant worlds far beyond our reach. In recent years, the idea of a ninth planet hidden at the edge of our solar system has sparked the imaginations of astronomers and stargazers alike. While this planet, often dubbed Planet 9, remains elusive, indirect evidence continues to mount, suggesting that it might actually exist. Located far beyond the orbit of Neptune in the far reaches of the Kuiper Belt, this hypothetical world could be lurking in the dark recesses of our cosmic neighborhood. The story of Planet 9 began in 2016, when astronomers Konstantin Bagan and Mike Brown proposed an intriguing hypothesis. Their calculations suggested that a massive planet, roughly 10 times the mass of Earth, could explain the strange behavior of certain distant objects in our solar system. These objects, known as trans-Neptunian objects, TNOs, follow highly elliptical orbits that seem unusually aligned. Such behavior is not what you would expect if these objects were moving in isolation. Instead, it points to the presence of an unseen force, an unknown gravitational influence that could only come from a large, distant object. The potential existence of Planet 9 is supported by these peculiar orbital patterns. These TNOs are moving in such a way that it seems they are being gently guided, almost as if a cosmic shepherd were herding them along their paths. And who might this shepherd be? Planet 9. The planet's gravitational pull could be enough to influence the orbits of these far-off objects, keeping them in line. According to Bagan and Brown's models, this mysterious planet would orbit the Sun from a distance of around 400 to 800 astronomical units, AU, 1 AU being the distance between Earth and the Sun. With such an immense orbit, Planet 9 could take between 10,000 to 20,000 Earth years to complete just one revolution around our star. This planet would not only be massive and far-flung, but also capable of exerting an enormous gravitational influence on the objects around it. Its presence, though unseen, could be shaping the outer solar system, creating order where we once believed there was none. More proof for the existence of Planet 9 comes from computer simulations that model the outer solar system with and without such a planet. When the simulations included Planet 9, they showed that the paths of TNOs could be explained far more accurately. Without it, the data didn't add up. But while we haven't yet directly observed this hidden world, astronomers are not giving up. Multiple astronomical surveys and telescopes are actively searching for Planet 9, combing the skies with ever-increasing precision. If they succeed, the discovery would not only solidify the planet's place in our solar system, but also provide valuable insight into how planets form, especially in the far reaches of the cosmic expanse. The hunt for Planet 9 has become one of the most exciting and tantalizing quests in modern astronomy. The promise of discovery looms large, with the potential to rewrite our understanding of the solar system we call home. Meanwhile, the universe continues to surprise us with strange and unexpected phenomena, one of which is the existence of hot Jupiters. These exoplanets are similar in size and mass to Jupiter, but defy expectations by orbiting incredibly close to their host stars. In fact, these planets are so close to their stars that they can complete an orbit in under 10 days, exposing them to intense radiation and heat. Surface temperatures on hot Jupiters can soar to thousands of degrees Celsius, making them some of the hottest planets ever discovered. The existence of hot Jupiters challenges conventional theories of planetary formation. According to the widely accepted core accretion model, gas giants like Jupiter are expected to form in cooler regions of a young star system beyond the so-called snow line. The snow line is the boundary where temperatures drop low enough for volatile compounds like water to freeze into ice. In these frigid regions, ice grains accumulate to form a solid core, which can then gather a thick envelope of gas. However, the close proximity of hot Jupiters to their stars contradicts this model. If they were to form in such heat, it would be nearly impossible for these massive planets to accumulate the necessary materials to build a solid core, let alone gather enough gas to become a gas giant. The discovery of hot Jupiters has led astronomers to reconsider their theories of planetary formation. How could such massive planets form so close to their stars? The answer may lie in the dynamic and chaotic nature of planetary systems, where gravitational interactions and planetary migration could move these massive worlds closer to their stars after their formation. This discovery opens the door to new possibilities as scientists continue to grapple with how planets evolve and what forces shape their paths. In both the search for Planet 9 and the study of hot Jupiters, we are reminded of the vast and ever-changing nature of our universe. These mysterious phenomena challenge our understanding of the cosmos and remind us that there is always more to explore. As we peer deeper into the reaches of space, who knows what other cosmic secrets await our discovery? The study of hot Jupiters has led to a fascinating paradox that has confounded astronomers for years. This phenomenon has prompted scientists to devise alternate theories to explain the presence of these enigmatic exoplanets. One leading hypothesis is that these gas giants didn't form in their current locations, but instead migrated inward from their original formation zones, a theory known as planetary migration. Initially, hot Jupiters likely formed in the colder, distant regions of their star systems, beyond the snow line, just like traditional gas giants. However, their journeys were far from straightforward. Through complex gravitational interactions with the protoplanetary disk or other planets, these giants began a gradual inward migration. As they neared their stars, their orbits became dynamically unstable, eventually settling into stable positions very close to their sun. But the story doesn't end there. The powerful tidal forces exerted by the host star played a crucial role in shaping the final fate of these planets. As hot Jupiters continued their inward migration, these tidal interactions helped circularize their orbits, stabilizing them and locking the planets into synchronous rotation. This meant that one hemisphere of the planet would forever face the star, while the other side remained in perpetual darkness. This phenomenon, known as tidal locking, is responsible for the extreme temperature variations between the day and night sides of these planets, creating an environment of intense heat on one side and freezing cold on the other. The discovery of hot Jupiters has not only provided scientists with a new perspective on planetary formation, but has also forced a reevaluation of the diverse and dynamic architectures that planetary systems can take on. Equally as groundbreaking as the discovery of hot Jupiters has been the detection of the TRAPPIST-1 system. Announced in 2017, this remarkable system is located about 40 light-years from Earth and contains 7 Earth-sized planets orbiting a faint M-dwarf star. What makes this discovery especially significant is that 3 of these planets fall within the star's habitable zone, where conditions could be just right for liquid water to exist on their surfaces, an essential ingredient for life as we know it. The TRAPPIST-1 system has radically shifted our understanding of what conditions are necessary for habitability. Prior to this discovery, M-dwarf stars, small, cool stars that emit most of their radiation in the infrared, were not considered ideal hosts for habitable planets. Because these stars are so dim, any planets that might support life would need to orbit extremely close to their stars. In the case of TRAPPIST-1, all 7 planets reside closer to their star than Mercury does to our Sun. Despite these close orbits, however, the planets are not automatically hostile to life. The lower luminosity of the M-dwarf star combined with its cooler temperatures creates a more inviting environment for life than previously imagined. What's truly transformative about TRAPPIST-1 is the sheer number of potentially habitable planets in a single system. The discovery suggests that planets capable of supporting life may be far more common throughout the galaxy than we had thought. This realization has reinvigorated the search for extraterrestrial life, emphasizing the importance of M-dwarf stars in exoplanet research. The close proximity of these planets and their alignment for transits make them prime candidates for detailed atmospheric study. Future telescopes like the James Webb Space Telescope are poised to give us the tools to study these atmospheres in depth, searching for gases like oxygen or methane that could hint at the presence of life. TRAPPIST-1 has sparked a revolution in the way we think about habitable worlds, pushing us to reconsider our assumptions about where life could thrive. It suggests that the conditions for life may be far more widespread than we ever imagined. The discovery has encouraged scientists to reorient their observational strategies, focusing on M-dwarf stars as potential homes for life and generating new excitement in the search for extraterrestrial life. Meanwhile, the concept of super-Earths has also expanded our understanding of exoplanets. These fascinating worlds are characterized by their larger masses compared to Earth, typically up to 10 times the mass of our planet, but are significantly smaller than the gas giants like Uranus and Neptune. Super-Earths can have a wide range of compositions depending on their size and proximity to their host stars. They can be rocky like Earth, or possess thick atmospheres, possibly even enveloping oceans or extensive gas layers. Some of these planets are rocky, with significant quantities of metal and rock, while others may present more of an oceanic or gas-heavy environment. Super-Earths further broaden the scope of planets we consider potentially habitable. With their diverse compositions and varying environments, these planets may offer insights into how planets form, evolve, and potentially support life. As our ability to detect and study these distant worlds improves, we may one day find that Earth-like conditions exist not just on planets in the habitable zone of Sun-like stars, but also on super-Earths orbiting a variety of different stars. The possibilities are as boundless as the universe itself. The discovery of super-Earths has marked a monumental shift in our understanding of planetary systems, shedding light on the wide variety of planetary environments that may exist beyond our solar system. These planets, which are larger than Earth but smaller than gas giants, open up thrilling new possibilities in the search for life beyond our home planet. Super-Earths are particularly fascinating because their size places them within a range where conditions may resemble those of Earth, including the potential for liquid water, a key ingredient for life as we know it. However, the exact characteristics of these planets vary drastically. Some super-Earths may have thick atmospheres that prevent life from thriving, while others might be more hospitable, offering environments where liquid water could exist. This makes them a critical focus of ongoing research. The prevalence of super-Earths in our galaxy has profound implications. According to data from the Kepler Space Telescope and other observational programs, these planets are among the most common types of exoplanets. In fact, estimates suggest that about 30% or more of Sun-like stars could host at least one super-Earth in their habitable zone, the region around a star where conditions might be right for liquid water to exist. This high frequency of super-Earths raises intriguing questions about the potential for extraterrestrial life and challenges current models of planetary formation. Historically, our understanding of how planets form was based on our solar system's architecture, which does not feature any super-Earths. However, the widespread presence of these planets suggests that the processes driving their formation are likely more accessible and robust than those that create Earth-sized planets. As a result, super-Earths are seen as a vital component of the exoplanetary landscape, offering a middle ground between smaller terrestrial planets like Earth and massive gas giants like Jupiter. The sheer number of super-Earths in the galaxy makes them an essential focus for astronomers seeking to understand planetary evolution and the possibility of life elsewhere in the universe. Their prevalence also challenges our assumptions about the variety and formation of planets, prompting astronomers to re-examine the complex processes that shape planetary systems. To detect these distant worlds, astronomers use a variety of sophisticated techniques, each providing unique insights into the nature of exoplanets. These methods have revolutionized our understanding of the universe, allowing us to discover thousands of planets orbiting stars far beyond our solar system. Among the most effective methods are the transit method, the radial velocity method, direct imaging, astrometry, and gravitational microlensing. The transit method, made famous by the Kepler Space Telescope, has been particularly successful in detecting exoplanets. This technique involves monitoring the brightness of a star over time. When a planet passes in front of its star, it causes a small, temporary dip in the star's light. By measuring the periodicity of these dimming events, astronomers can infer the presence of a planet, estimate its size, and even determine its orbital period. This method is especially useful for detecting planets that orbit relatively close to their stars, making it ideal for identifying super-Earths. The radial velocity method, also known as Doppler spectroscopy, detects planets by measuring the star's motion as it responds to the gravitational pull of an orbiting planet. This motion causes the star to wobble slightly, shifting its light spectrum toward red and blue wavelengths. By analyzing these shifts, astronomers can determine the mass and orbital characteristics of the planet. This method is particularly useful for identifying larger planets, including super-Earths, which have a significant gravitational influence on their stars. Direct imaging is a more challenging method due to the difficulty of isolating the faint light of a planet from the overpowering brightness of its host star. However, recent advancements in technology, such as adaptive optics and coronagraphs, have made it possible to directly capture images of exoplanets. This technique provides valuable information about the planet's atmospheres and surface conditions, enabling scientists to study their composition and potential habitability. Astrometry involves precisely measuring the positions of stars and detecting slight changes in their positions caused by the gravitational pull of orbiting planets. This technique allows astronomers to track the movement of planets around their stars with incredible accuracy, providing further insights into the characteristics of exoplanets. In summary, the discovery of super-Earths has opened up a new frontier in the exploration of exoplanets. These planets represent a fascinating link between Earth-like worlds and massive gas giants, and their abundance in the galaxy makes them crucial targets in the search for extraterrestrial life. As astronomers continue to refine their detection techniques and expand our understanding of planetary systems, we may be one step closer to answering the age-old question: are we alone in the universe? This method, although not widely used, demands extraordinary precision and can be highly effective for detecting distant, massive planets orbiting far from their stars. It harnesses the power of gravitational microlensing, a fascinating phenomenon where the gravitational field of a star magnifies the light from a background star when it passes directly in front of it. If the foreground star is accompanied by a planet, the planet's gravitational influence subtly alters the light curve, leaving behind a distinct signature that signals its presence. This technique is especially useful for discovering planets located at significant distances from their stars, or even those that have been ejected from their systems altogether, commonly referred to as rogue planets. Gravitational microlensing has become a crucial tool for astronomers, offering insights into planets that might otherwise remain hidden from traditional detection methods, such as the transit or radial velocity methods. Its unique ability to detect planets in remote, less explored regions of space broadens our understanding of the diverse types of planets that exist across the galaxy. Combined with other planet detection techniques, it has illuminated the rich variety of exoplanets, ranging from scorching hot Jupiters, super-Earths. These combined efforts are not just expanding our knowledge of the cosmos, but also enhancing our understanding of the potential for life beyond Earth. One of the key factors in this search for life beyond our solar system is the concept of the Goldilocks zone, also known as the habitable zone. This is the region around a star where conditions are just right for liquid water to exist on the surface of a planet, not too hot and not too cold. The term Goldilocks draws inspiration from the classic fairy tale, suggesting that, much like the porridge in the story, the environment in this zone is perfect for sustaining life as we know it. Liquid water is considered one of the most essential ingredients for life, as it serves as a solvent for chemical reactions that are vital for biological processes. Without it, the complex chemistry required for life could not occur. The importance of the Goldilocks zone extends far beyond water. A planet within this zone has a much higher chance of maintaining an atmosphere, critical for shielding life from harmful radiation and helping to stabilize the climate. Earth, situated perfectly within the Sun's Goldilocks zone, provides an ideal example of how this delicate balance allows life to flourish. This zone is also a prime target for astrobiologists, as planets within it are the most likely candidates for hosting life-supporting conditions. The ongoing search for exoplanets within their star's habitable zone has become a central focus of the quest to answer one of humanity's most profound questions. Are we alone in the universe? In stark contrast to planets that reside in the Goldilocks zone, certain exoplanets experience extremely short orbital periods. These ultra-short period planets, due to their proximity to their host stars, complete an orbit in a matter of hours, drawn in by the immense gravitational forces of the star they circle. As a result, these planets not only experience extreme temperatures, soaring to thousands of degrees Celsius, but are also subjected to intense tidal forces and stellar radiation. These forces contribute to the formation of unique, sometimes hostile environments, raising profound questions about what kind of life, if any, could survive in such conditions. For instance, many of these planets are tidally locked, meaning one hemisphere constantly faces the star, while the other remains in perpetual darkness. This leads to a stark contrast in temperature, with one side of the planet scorched by relentless heat and the other frozen in cold. The extreme conditions present on these planets challenge our traditional notions of what constitutes a habitable environment. Could life, as we understand it, exist in such environments? Or might we need to rethink the very nature of life, considering organisms that thrive under drastically different conditions from those on Earth? These questions push the boundaries of astrobiology, underscoring the incredible diversity of planetary systems in our galaxy, and opening our minds to the possibility of life in forms radically different from what we know. Lastly, rogue planets, those mysterious celestial nomads that wander the galaxy without the anchor of a host star, present an entirely different puzzle. These planets were likely ejected from their original systems due to gravitational interactions with other planetary bodies or the passing influence of a nearby star. Despite drifting through the cold void of space, rogue planets have shown remarkable resilience. Many retain residual heat from their formation, allowing them to survive without sunlight. This internal heat can keep them warm for billions of years, offering the possibility of subsurface oceans or other forms of life-supporting environments. While these planets may never host life as we know it, they offer a unique opportunity to study planetary evolution in isolation, providing clues to the complex and dynamic processes that shape planetary systems. Together, these fascinating planetary phenomena Gravitational microlensing, the Goldilocks zone, ultra-short period planets, and rogue planets highlight the breathtaking diversity of planetary systems across the galaxy. They remind us that the universe is full of surprises, and the potential for life may be more varied and resilient than we ever imagined. As our search for exoplanets continues, we are uncovering not just new worlds, but also expanding the boundaries of what we consider possible in the vast and mysterious cosmos. In the vast expanse of the cosmos, rogue planets, free from the gravitational grip of any star, present one of the most intriguing possibilities for extraterrestrial life. These solitary wanderers drifting in the dark void are not necessarily lifeless. In fact, some may harbor conditions that are more conducive to life than initially imagined. While they lack a star to provide warmth, these planets may still possess geothermal heating generated by the radioactive decay within their interiors. This process, similar to what occurs on Earth, could provide enough energy to create subsurface oceans beneath thick layers of ice, where liquid water might exist in a stable, habitable state. These hidden aquatic environments raise the tantalizing possibility that microbial life could exist on rogue planets, protected from the harsh conditions of space by a thick ice crust and thriving in a deep, sheltered ecosystem. This challenges our conventional notions of habitability, pushing the boundaries of what we thought was necessary for life to flourish. Could rogue planets, isolated and seemingly inhospitable, actually be home to vibrant ecosystems hidden in the depths of their icy exteriors? These rogue worlds without a parent star force us to reconsider the very nature of life in the universe. Could life not only exist on planets that orbit stars, but also on those that drift alone, far from the warmth of a sun? Meanwhile, binary star systems where two stars orbit a common center of mass introduce complex gravitational dynamics that profoundly affect planetary formation and habitability. These systems, with their unique gravitational interactions, present both challenges and opportunities for planets that orbit them. Binary star systems fall into two categories when it comes to planetary orbits. Circumbinary planets, which orbit both stars in a wide, encompassing path, and circumstellar planets, which orbit just one of the stars, with the second star serving as a distant companion. The formation of planets in these systems is fraught with difficulties. The gravitational forces exerted by two stars often lead to destabilizing perturbations in the planetary disk, making it harder for planetesimals to coalesce and form planets. Yet, despite these challenges, planets can still emerge and thrive under the right conditions. NASA's Kepler mission has identified several circumbinary planets, challenging the long-standing assumption that such environments were too chaotic for stable planetary formation. When it comes to habitability, binary star systems can have a profound impact on a planet's climate and radiation exposure. A planet in the habitable zone where liquid water can exist must maintain a stable orbit despite the gravitational tug-of-war between the twin stars. In circumbinary systems, this could lead to more varied climate patterns, with shifting positions of the stars, potentially resulting in complex dynamic seasons. On the other hand, planets orbiting just one star in a binary system may experience periodic disturbances in their orbit from the gravitational pull of the second star, leading to fluctuations in their climate stability. Yet, the discovery of such planets in binary systems broadens the horizon for habitable worlds, showing the extraordinary adaptability of planetary systems in our galaxy. Then there are the lava worlds, exoplanets that embody extreme conditions, with vast regions of molten rock covering their surfaces. These planets orbit extremely close to their host stars, enduring intense heat that keeps their surfaces perpetually molten. One of the most notable examples is the exoplanet 55 Cancri E, which orbits its star so closely that temperatures can soar above 2,000 degrees Celsius, transforming its surface into a searing lava landscape. The study of lava worlds offers valuable insights into planetary evolution. These planets provide natural laboratories for understanding the early stages of planetary development, mirroring the molten conditions that Earth likely experienced shortly after its formation. Observations of these fiery worlds can shed light on processes like planetary differentiation, where heavier materials sink to form a core and lighter materials rise to form a crust. The extreme heat and volcanic activity on these planets also give scientists the opportunity to study outgassing processes, where volatile compounds are released from the planet's interior to its atmosphere, an essential process in the formation and evolution of atmospheres. Furthermore, the intense environments of lava worlds help refine theoretical models of planet-star interactions, particularly concerning tidal locking and planetary deformation under strong gravitational forces. By examining these fiery exoplanets, scientists can better understand the full range of planetary conditions that exist across the universe, providing deeper insights into the factors that influence planetary formation, stability, and the potential for habitability. Lastly, some exoplanets defy our traditional understanding of atmospheric composition by displaying features and elements that are completely unexpected, unlike anything observed within our own solar system. These peculiarities challenge existing models of planetary formation and atmospheric science, prompting researchers to rethink the chemical and physical processes that govern such environments. With each new discovery, our understanding of what is possible in the universe continues to expand, offering new and fascinating possibilities for the existence of life on other worlds. In the vast and ever-expanding universe, there are discoveries that challenge our understanding of the very nature of planetary systems. One striking example of this is the exoplanet WASP-33b, a gas giant classified as a hot Jupiter. Its orbit around its host star is so incredibly close that its atmospheric temperatures soar to an astonishing 3,000 degrees Celsius. At these extreme temperatures, the atmosphere of WASP-33b contains exotic elements, such as titanium oxide, an element typically associated with stellar atmospheres rather than planetary ones. This unexpected discovery not only demonstrates the intense thermal dynamics of hot Jupiters, but also suggests the presence of strong thermal inversion layers in its atmosphere, where temperature increases with altitude instead of the usual decrease. The presence of such a phenomenon challenges traditional ideas about atmospheric science, revealing just how unpredictable and diverse planetary environments can be. Another fascinating example comes from the exoplanet HD 18973b, which continues to baffle scientists with its deep electric blue hue. While Earth's blue color is due to the scattering of sunlight by our oceans, the color of HD 18973b comes from a hazy atmosphere filled with high-altitude clouds made of silicate particles. These particles contribute to an extraordinary weather system where rain made of glass shards falls sideways due to incredibly high winds, reaching speeds of up to 5,000 miles per hour. The atmosphere's composition and the violent weather patterns it supports have made it clear that the environmental conditions on this planet are unlike anything we could imagine. Such extreme conditions demand more sophisticated models of planetary formation and evolution, which will not only help scientists better understand exoplanets, but also broaden the scope of what we think is possible in the universe. By studying these remarkable atmospheres, we are expanding our comprehension of planetary science and challenging the conventional definitions of habitability and the potential for life elsewhere. As our knowledge of distant planets grows, so too does our understanding of the forces that shape them. One of the most significant milestones in our journey into deep space occurred in April 2019 with the groundbreaking capture of the first image of a black hole. This extraordinary image was made possible through an innovative technique known as Very Long Baseline Interferometry, VLBI, which involved an unprecedented collaboration of telescopes worldwide. The Event Horizon Telescope (EHT) project united 8 radio telescopes from various corners of the Earth, including locations in Hawaii, Chile, Spain, and even Antarctica, to create a virtual Earth-sized telescope. By synchronizing these telescopes and combining their data, scientists were able to achieve the incredible resolution needed to capture the image of a black hole located at the center of the galaxy M87, about 53 million light-years away from Earth. This monumental achievement required meticulous planning and cutting-edge technology. The telescopes had to be perfectly synchronized using atomic clocks that ensured precision down to the microscopic level. The EHT team gathered petabytes of data over multiple nights, and through sophisticated algorithms, they were able to process these colossal data sets. The result? a stunning image of a bright ring-like structure surrounding a dark central region, which aligns perfectly with theoretical predictions of a black hole's shadow. This historic image not only proved the existence of black holes, but also provided an invaluable opportunity to test Einstein's general theory of relativity under the extreme conditions near a black hole. This breakthrough represents a triumph of global collaboration and technological innovation, pushing the boundaries of our understanding of the universe. The event horizon of a black hole is one of the most captivating and mysterious features in astrophysics. It marks a boundary so powerful that nothing, no light, can escape from within its grip. This is why the event horizon itself is invisible. Anything that crosses it disappears from view, making it a point of no return. The theory behind the event horizon is rooted in general relativity, Einstein's groundbreaking framework that explains how massive objects warp the fabric of space-time. As an object approaches the event horizon, the forces acting on it become extreme. For an external observer, it appears that time slows down for the object as it nears the event horizon, a phenomenon known as gravitational time dilation. To the observer, the object never truly crosses the event horizon. Instead, it seems to freeze in time, gradually fading away as its light shifts to longer wavelengths, appearing redder and redder. But from the perspective of the object itself, it continues its inevitable journey, entering the black hole without a backward glance. In this incredible quest to understand the universe, every discovery, whether it's the strange atmosphere of a distant exoplanet or the enigmatic pull of a black hole, reveals more about the forces that govern the cosmos and how little we know of the vast, mysterious universe around us. Our pursuit of these cosmic truths not only challenges our scientific boundaries, but also ignites our curiosity about what lies beyond the limits of our current understanding. And with every new revelation, we inch closer to understanding the fundamental nature of existence itself. However, the experience of approaching a black hole, especially upon crossing the event horizon, is strikingly different from what one might expect. As you pass through this invisible boundary, the descent into the black hole continues with no immediate or obvious changes. According to classical general relativity, the crossing of the event horizon might seem imperceptible at first, but as you venture deeper, the effects become more dramatic. The tidal forces grow increasingly stronger, stretching you along the axis of the black hole's immense gravitational field while compressing you sideways. This process, known as spaghettification, results from the extreme differences in gravitational pull across your body. As you move even closer to the heart of the black hole, you would eventually reach the singularity, where space-time curvature becomes infinite and the known laws of physics cease to function as we understand them. This moment represents one of the most profound mysteries in modern astrophysics, inspiring researchers to explore a unified theory that merges quantum mechanics with general relativity. At the heart of these investigations lies the enigmatic event horizon, a region that continues to captivate scientists and laypeople alike. The quest to understand this boundary and the forces that operate within it remains at the forefront of theoretical physics. The event horizon's ability to challenge the very foundation of our physical laws keeps it a central point of study, pushing the limits of human knowledge about the cosmos. The deeper we probe into this unfathomable region, the more we confront the limitations of our current theories, driving a continuous reevaluation of our understanding of the universe itself. Supermassive black holes, which dominate the centers of most galaxies, including our Milky Way, are cosmic giants of extraordinary proportions. These behemoths can weigh anywhere from millions to billions of times the mass of our Sun. Their formation and the mechanisms behind their staggering size have long been a subject of fascination and intense research. One leading theory suggests that these supermassive black holes originated from the collapse of massive primordial gas clouds in the early universe. These clouds, primarily composed of hydrogen and helium, would have collapsed under their own gravity, forming seed black holes with masses ranging from 100 to 1,000 times that of the Sun. Over eons, these seed black holes could grow through a process known as accretion, where they pull in surrounding gas and dust, gradually gaining mass and energy. This growth often results in the emission of tremendous amounts of radiation, which can be observed as quasars, distant and highly energetic sources of light. Another formation hypothesis posits that supermassive black holes could arise from the merger of smaller black holes within dense regions of the early universe. These regions, teeming with star collisions and stellar remnants, would have produced many stellar mass black holes, each with a fraction of the mass of their supermassive counterparts. Over billions of years, these smaller black holes would eventually collide and merge, growing in size. The mergers of entire galaxies, which were more frequent in the early universe, played a crucial role in this process, ultimately leading to the formation of supermassive black holes. As galaxies collided, their central black holes would eventually coalesce, forming the supermassive black holes that we observe today. The relationship between these black holes and the galaxies they inhabit is profound. Observations have shown a significant correlation between the mass of a galaxy's central black hole and the mass of its bulge. This suggests that the evolution of black holes is intricately linked to the growth and evolution of their host galaxies. The energy emitted by the accretion of matter onto these black holes can influence star formation within the galaxy, acting as a regulating force on its growth. Despite numerous breakthroughs, the precise mechanisms behind the formation of these colossal black holes are still shrouded in mystery. Ongoing research, including observational data and computer simulations, continues to probe this cosmic puzzle. Gravitational waves, the ripples in space-time caused by some of the most violent events in the universe, were predicted by Albert Einstein's general theory of relativity a century ago. These waves travel at the speed of light and carry vital information about their violent origins, such as black hole mergers or neutron star collisions. Gravitational waves represent one of the most groundbreaking achievements in astrophysics, offering an entirely new way to study cosmic phenomena, especially black holes. Unlike electromagnetic waves, which can be absorbed or scattered by matter, gravitational waves travel unimpeded through space, offering a pristine view of some of the most extreme environments in the universe. When two black holes spiral toward each other and merge, they generate these waves, which, as they pass through Earth, create tiny distortions in space-time. These disturbances are detectable by ultra-sensitive instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo. In 2016, the first direct detection of gravitational waves was announced, marking a historic moment in astrophysics. The detected waves came from the merger of two black holes located about 1.3 billion light-years away, providing both the first direct evidence of binary black hole systems and confirming the existence of gravitational waves themselves. The study of these waves offers an unprecedented glimpse into the inner workings of black holes. By analyzing the specific waveform of gravitational waves, scientists can infer key properties of their sources, including the masses, spins, and dynamics of the black holes involved. This data also opens the door to new insights into the population of black holes across the universe. By observing the rates at which stellar mass black holes merge, researchers can gain a deeper understanding of the environments where these black holes form and evolve. Furthermore, gravitational wave astronomy provides a powerful testing ground for Einstein's general theory of relativity under extreme conditions, potentially revealing anomalies that could point to new physics beyond our current understanding. In this way, the study of gravitational waves not only enriches our knowledge of black holes, but also furthers our exploration of fundamental forces and the nature of gravity itself. Hawking radiation, a theoretical prediction proposed by renowned physicist Stephen Hawking in 1974, challenges the very nature of black holes. Traditionally seen as the ultimate cosmic voids where nothing, not even light, can escape, Hawking's discovery suggests that these enigmatic objects are not entirely black. Instead, they may emit radiation due to quantum effects near their event horizons, the boundary beyond which escape is impossible. This groundbreaking idea arises from the intersection of quantum mechanics and general relativity, two of the most well-established theories in physics that generally operate in separate realms: quantum mechanics governing the atomic scale, and general relativity describing the vastness of the cosmos. Hawking radiation is a direct consequence of the unique properties of quantum fields in curved spacetime around a black hole. At the edge of the event horizon, the extreme gravitational field is so strong that it can cause pairs of virtual particles to spontaneously form from the vacuum of space. These pairs, made up of a particle and its antiparticle counterpart, would typically annihilate each other almost instantly. However, when this pair forms right at the event horizon, something remarkable can occur. One particle may fall into the black hole while the other escapes into space. To an observer far from the black hole, the escaping particle seems to radiate outward, as though coming from the black hole itself. The particle that falls into the black hole carries negative energy relative to the outside universe. This process gradually decreases the black hole's mass, a phenomenon often described as black hole evaporation. Over vast timescales, this loss of mass could result in the eventual disappearance of the black hole, an intriguing and revolutionary possibility that had not been seriously considered before Hawking's insight. The concept of Hawking radiation not only reshapes our understanding of black holes, but also raises questions about their true nature. Black holes, once thought to be eternal, may instead follow a life cycle that culminates in their complete evaporation. Furthermore, Hawking radiation stirs a deep philosophical and physical dilemma about the loss of information. According to the classical laws of general relativity, anything that falls into a black hole is lost to the universe. This includes all information about the particles, their state, and their interactions. However, quantum mechanics firmly asserts that information cannot be destroyed. This clash between the classical and quantum descriptions of the universe has sparked intense debate, leading to the development of new theories such as the holographic principle and black hole complementarity, which attempt to reconcile these conflicting views. This tension between quantum mechanics and general relativity highlights the need for a unified theory of quantum gravity, one that could seamlessly integrate both the microcosm of particles and the macrocosm of black holes. As researchers continue to explore the mysteries of black holes, they are not only revisiting fundamental questions about the universe, but are also pushing the boundaries of our understanding of space, time, and information. The fabric of space-time itself becomes utterly distorted in the presence of a black hole. This is a concept predicted by Einstein's general theory of relativity, which states that the stronger the gravitational field, the greater the warping of space-time. A black hole's intense gravity bends this four-dimensional continuum, combining 3 dimensions of space with the dimension of time. Imagine space-time as a stretchable rubber sheet. When a massive object is placed on it, the sheet stretches and curves around the object. Similarly, a black hole creates an extreme curvature in space-time, creating a pit from which nothing, not even light, can escape. This warping has significant consequences for the paths of light and matter that come near a black hole. For example, light from distant stars or galaxies may bend around the black hole, creating multiple images or a distorted view of objects behind it. This phenomenon, known as gravitational lensing, provides astronomers with indirect evidence of black holes and has become an essential tool for studying their properties. The more massive the black hole, the stronger its gravitational field and the more dramatic the lensing effect. Another remarkable aspect of black holes is their influence on time itself, a phenomenon known as gravitational time dilation. According to general relativity, time passes more slowly in stronger gravitational fields. Near a black hole, this effect becomes extreme. From the perspective of an observer far away, time appears to slow down for an object approaching the event horizon. As the object nears this boundary, it seems to freeze in time, never fully crossing into the black hole. However, the object itself perceives time normally and would pass through the event horizon without noticing any dramatic changes. This profound distortion of time and space not only challenges our basic understanding of the universe, but also provides a unique opportunity to test the predictions of general relativity in extreme conditions. This profound understanding of space-time and time dilation has far-reaching implications. It forces us to rethink the nature of the universe, the laws that govern it, and the very fabric of reality itself. As we continue to probe these cosmic phenomena, we push the boundaries of science, all while gaining deeper insights into the fundamental nature of the cosmos. Among the most luminous and energetic objects in the universe are quasars, short for quasi-stellar objects. These incredible phenomena are intrinsically linked to supermassive black holes that reside at the centers of most galaxies. As these black holes consume surrounding matter, an accretion disk forms, a swirling mass of gas, dust, and other debris. The intense gravitational forces near the black hole accelerate this material, causing it to heat up to extreme temperatures. This, in turn, leads to the release of tremendous amounts of electromagnetic radiation, particularly in the radio, ultraviolet, and X-ray wavelengths. Quasars are so bright that they can outshine entire galaxies despite their relatively small size. Some quasars are so luminous that they can be observed from billions of light years away, offering astronomers a glimpse into the early universe. The energy emitted by quasars comes from the dynamic and violent processes occurring within their accretion disks. Friction between particles in the disk generates immense heat, which radiates outward in the form of intense light. The study of quasars and their connection to supermassive black holes also provides invaluable insights into the evolution of galaxies. The central black hole powers the quasar by rapidly consuming nearby material, and in doing so, it plays a significant role in shaping the structure and behavior of the galaxy as a whole. Understanding this relationship helps us comprehend the forces that drive the formation and evolution of galaxies throughout the universe. In sum, black holes, Hawking radiation, gravitational time dilation, and quasars all present us with profound mysteries and extraordinary phenomena that continue to challenge our understanding of the cosmos. As we deepen our investigation into these cosmic objects, we not only unlock secrets about the universe's past, but also push the frontiers of knowledge into new realms of scientific discovery. The accretion process is a captivating phenomenon, not just in the way it fuels the brilliant radiation of quasars, but also in its vital role in shaping the environments of host galaxies. This process involves material, often gas and dust, spiraling into the supermassive black hole at the center of a galaxy. As the material heats up, it emits vast amounts of energy, fueling the quasar's intense brightness. But there's more to it than just illumination. This energy also drives powerful outflows of gas and dust, creating dramatic changes within the host galaxy. These outflows can act as cosmic architects, either sparking the birth of new stars by compressing nearby molecular clouds, or halting star formation by dispersing the raw materials necessary for their creation. The balance between these competing forces plays a central role in regulating the star formation activity in galaxies across cosmic timescales. Quasars, therefore, serve as dynamic engines of both creation and destruction, profoundly influencing the evolution of galaxies around them. Not only do quasars shape their local environments, but they have also transformed our understanding of the universe itself. The discovery of the first quasar, 3C273, revealed a surprising truth about these enigmatic objects. Initially thought to be distant stars or galaxies, it became clear that quasars are intimately tied to supermassive black holes at the centers of galaxies. These objects are not merely points of light, but incredibly energetic phenomena that reveal the inner workings of black holes, offering us a glimpse into their role in cosmic evolution. Moreover, quasars act as beacons of light, allowing astronomers to peer into the distant universe. As their radiation passes through intergalactic space, it interacts with the surrounding medium, providing valuable data about the composition and structure of the universe itself. Quasars allow us to study the vast cosmic web, tracing the paths of galaxies and clusters, and shedding light on the mysterious dark matter that holds the universe together. In this way, quasars remain a central focus of scientific inquiry, offering insights into the fundamental workings of matter, energy, and the forces that govern the cosmos. Now, turning our attention to binary black hole systems, these captivating systems, which consist of two black holes orbiting a common center of mass, exhibit behaviors distinctly different from solitary black holes. The gravitational interactions between the two black holes are extraordinarily complex, leading to dynamic phenomena that intrigue astrophysicists. One of the most fascinating aspects of these systems is their emission of gravitational waves. As the black holes spiral closer to each other, intense gravitational fields stretch and distort space-time, sending ripples through the fabric of the universe. These waves carry away energy from the system, causing the black holes to gradually lose their orbital separation. As they draw nearer, the gravitational waves intensify, growing stronger and stronger until eventually the two black holes merge. This merger is a breathtaking event, releasing an immense amount of energy, sometimes more than the combined output of all the stars in the observable universe. The detection of these gravitational waves by observatories like LIGO and Virgo has opened a new frontier in astrophysical research, providing direct evidence of binary black hole systems and allowing scientists to study the properties of black holes, such as their masses, spins, and the very nature of gravity itself. These merger events are not only spectacular cosmic phenomena, but also provide crucial tests for Einstein's theory of general relativity. As the black holes spiral inward, scientists have the opportunity to examine the behavior of gravity under the most extreme conditions imaginable. The dynamics of these systems provide a rich playground for exploring the very fabric of space-time, offering insights that are both profound and awe-inspiring. Before the merger, binary black hole systems exhibit unique behaviors. The intense gravitational forces between the two black holes cause orbital precession, a phenomenon in which the orientation of the orbit changes over time. This behavior is similar to the precession of a spinning top, but in the case of black holes, it's driven by the complex interplay of their masses and spins. The geometry of space-time around the binary system becomes increasingly distorted, a dramatic contrast to the more static warping found around solitary black holes. As these systems evolve, they provide a wealth of information about the universe's most enigmatic objects. By studying the behavior of binary black holes, we can learn more about the fundamental forces that shape the cosmos and deepen our understanding of the intricate workings of the universe at its most extreme. Every discovery brings us closer to answering some of the most profound questions about the nature of matter, energy, and the evolution of the cosmos. These systems are not only fascinating in their own right, but serve as a reminder of the vastness and complexity of the universe, where black holes dance in the darkness, revealing the mysteries of existence itself. Furthermore, the formation and evolution of binary black hole systems reveal an intricate and fascinating divergence from their solitary counterparts. These systems, often the result of the collapse of massive stellar binaries or dynamic interactions in dense stellar environments like globular clusters, offer a complex yet invaluable window into the workings of gravitational physics. Unlike single black holes, binary black holes are shaped by a variety of processes, leading to variations in their masses, spins, and orbital eccentricities. These distinct features provide crucial insights into the formation of black holes and the broader mechanics of stellar evolution. The intricate interactions between the two black holes, particularly during their mergers, generate gravitational waves, ripples in spacetime, that allow scientists to probe the very fabric of the universe itself. As these binary systems spiral toward each other, their behavior acts as a dynamic laboratory where the laws of physics are pushed to their limits, offering answers to age-old questions about the nature of gravity and the cosmos. The study of these systems has brought about profound revelations, particularly through the observation of their mergers, which often result in the emission of gravitational waves detectable by instruments like LIGO and Virgo. These discoveries provide a powerful tool for understanding the invisible forces that govern the universe. The waves reveal not only the characteristics of the black holes themselves, but also the underlying structure of spacetime during these intense cosmic events. As researchers analyze the properties of these binary systems, they draw closer to answering some of the most profound questions in modern physics. What happens when two black holes collide? How does the mass and spin of a black hole evolve as it interacts with another? The answers to these questions are not just academic. They have the potential to reshape our understanding of gravity, the behavior of space-time, and the very nature of black holes themselves. Yet, within this realm of discovery, Theoretical challenges abound, none more perplexing than the firewall paradox, a conundrum that emerges from the attempt to reconcile general relativity and quantum mechanics. The firewall paradox questions the very nature of black holes, particularly the behavior of the event horizon. General relativity, with its principle of equivalence, suggests that an observer falling into a large black hole would not experience anything unusual as they cross the event horizon. In this theory, the horizon is a smooth, unremarkable boundary. However, quantum mechanics paints a more complicated picture, particularly when considering the phenomenon of Hawking radiation. According to Stephen Hawking's theory, black holes slowly lose mass over time through the emission of radiation. This process suggests that black holes can eventually evaporate, raising the critical question: what happens to the information contained within the black hole? If it is lost, it violates a fundamental tenet of quantum mechanics, that information cannot be destroyed. To resolve this, some theorists propose that information might be encoded in the Hawking radiation itself. However, this leads to an even more perplexing issue. If particles inside the black hole become entangled with those outside, breaking this entanglement could release an enormous amount of energy, creating a firewall at the event horizon. This firewall would burn up anything that crossed the horizon, contradicting the smoothness predicted by general relativity. Thus, the firewall paradox forces physicists to choose between three conflicting ideas: the smoothness of the event horizon, the preservation of information, or the rules of quantum field theory in curved spacetime. This dilemma highlights the tension between our understanding of gravity and quantum mechanics, emphasizing the need for a unified theory, one that can seamlessly incorporate both realms of physics. The debate surrounding the firewall paradox is not just theoretical, it has profound implications for how we view the universe. If we are to resolve this paradox, it may require a deeper understanding of how gravity and quantum mechanics coexist. A potential resolution might lead to the discovery of quantum gravity, a theory that unifies the very forces that shape our universe. As researchers delve into this ongoing puzzle, they are uncovering new insights that could forever change our understanding of black holes, space-time, and the fundamental laws that govern reality. In addition to these cosmic mysteries, astronomers and cosmologists face the intriguing challenge of understanding intermediate mass black holes, a class of black holes with masses ranging from 100 to 100,000 times that of our Sun. These enigmatic objects fill a critical gap in our understanding of black hole formation, falling between stellar mass black holes and supermassive black holes. Stellar mass black holes are formed from the collapse of massive stars, typically with masses ranging from 10 to 100 times that of the Sun, while supermassive black holes, found at the centers of galaxies, can have masses millions or even billions of times greater than that of the Sun. But intermediate mass black holes don't fit neatly into either of these categories, creating a mystery that challenges current models of black hole evolution. One of the primary difficulties in studying intermediate mass black holes lies in their elusive nature. These black holes are too small to be detected through the X-ray emissions typically associated with binary systems, yet too large to be easily ignored by the gravitational influences that shape their environments. As a result, they remain largely undetected and poorly understood. Their formation mechanisms also remain uncertain. Unlike stellar mass black holes, which are the result of supernova explosions, and supermassive black holes, which are thought to grow over billions of years through the accretion of matter, intermediate mass black holes do not fit into these established narratives. This gap in knowledge presents a significant challenge for astronomers, who must rethink their models of black hole growth and evolution in order to account for these mysterious objects. Could new mechanisms exist that give rise to black holes of intermediate mass? Or could these black holes represent a transitional phase in the life cycle of larger black holes? Finally, the cosmic web, an intricate network of filaments composed mainly of dark matter and gas, plays a pivotal role in shaping the large-scale structure of the universe. This web can be visualized as a massive, three-dimensional structure stretching across billions of light years, with dense knots and filaments serving as the scaffolding for galaxies and galaxy clusters. These filaments, formed by the gravitational attraction of dark matter, create an intricate structure within which all other cosmic structures are embedded. The nodes or intersections of these filaments are areas of high density, where the gravitational pull is strong enough to draw in matter, leading to the formation of galaxy clusters. The influence of the cosmic web on the universe's shape and dynamics is profound. The distribution of dark matter within the web acts as a gravitational catalyst, attracting ordinary matter and encouraging the formation of stars and galaxies. In the densest regions, the gravitational pull becomes so strong that entire galaxies are born and clusters of galaxies form. As the cosmic web evolves, it continues to shape the distribution of matter across the universe, ensuring that galaxies and clusters remain interconnected through this vast, invisible network. Understanding the cosmic web is crucial for understanding the universe as a whole, its past, present, and future. In conclusion, the universe is a place of immense complexity, filled with phenomena that challenge our understanding of the laws of physics. From the mysteries of binary black hole systems and the firewall paradox to the enigma of intermediate mass black holes and the structure of the cosmic web, scientists are continuously pushing the boundaries of knowledge. Each new discovery brings us one step closer to uncovering the secrets of the universe, offering glimpses into the intricate workings of space, time, and the forces that shape the cosmos. As our ability to observe and study these phenomena improves, so too will our understanding of the profound mysteries that lie at the heart of the universe. In the vast, interconnected web of the cosmos, filamentary structures play a vital role in shaping the universe we see today. These filaments, which form the backbone of the cosmic web, guide the flow of gas and galaxies, directing them along their defined paths. This continuous movement is not just a passive journey, but a crucial mechanism in the ongoing evolution of cosmic structures. As gas and galaxies travel along these filaments, they facilitate the distribution of elements essential for star and planet formation. This flow ensures that regions of the universe, once devoid of the building blocks for life, are constantly replenished, fostering the creation of new celestial bodies. The cosmic web, thus, is not merely a map of the universe's structure. It is the lifeblood of its growth. It helps form a detailed picture of the universe, from the smallest individual galaxies to the massive superclusters of galaxies that dominate the cosmic landscape. In this vast expanse, galaxy clusters serve as some of the most intriguing cosmic laboratories, providing compelling evidence for the existence of dark matter, an invisible yet essential component of the universe's mass. One of the most striking pieces of evidence for dark matter comes from the velocities of galaxies within a cluster. Astronomers have observed that these galaxies move at such high speeds that the visible matter within the cluster, such as stars and gas, cannot provide enough gravitational pull to keep them bound together. The missing mass that accounts for this extra gravitational force is, scientists believe, dark matter. This form of matter, which does not emit light or energy, remains hidden from direct observation, yet exerts a profound influence on the structure of the universe. In addition to velocity measurements, gravitational lensing provides another powerful piece of evidence. This phenomenon occurs when the immense gravitational pull of a galaxy cluster bends and distorts the light from more distant galaxies, creating a visual lens. By studying the extent of this distortion, scientists can map the distribution of mass within the cluster. Remarkably, these maps often reveal far more mass than is visible through direct observation of stars and gas. This discrepancy again points to the presence of dark matter, as it is the unseen mass that contributes to the gravitational lensing effect. Another critical line of evidence comes from the study of the hot gas found within galaxy clusters. This gas, observed through X-ray emissions, makes up the majority of visible mass within a cluster. The temperature of the gas can be used to calculate the depth of the gravitational well that holds it in place. When scientists perform these calculations, they find that the gravitational well is far deeper than can be accounted for by the visible gas and stars alone. This implies that dark matter is present in large quantities, providing the additional gravitational pull necessary to stabilize the cluster. Taken together, these various pieces of evidence converge to provide a strong case for the existence of dark matter, which is thought to constitute approximately 85% of the total mass in the universe. This mysterious substance plays a crucial role in the formation and stability of galaxies, stars, and clusters, influencing the very structure of the cosmos. In contrast to these dense, galaxy-packed regions, cosmic voids stand as vast, empty expanses of space. These voids, which can span tens of millions of light years, contain very few galaxies or matter. Despite their emptiness, cosmic voids are some of the largest structures in the universe. They may seem insignificant at first glance, but they offer valuable insights into the large-scale structure of the cosmos. They represent the dark, empty spaces between the bright filaments and clusters of galaxies, providing a stark contrast to the dense regions that populate the cosmic web. The study of cosmic voids is essential for understanding the broader evolution of the universe. One of the key revelations from these studies is the way in which voids help improve our understanding of dark energy, the mysterious force responsible for the accelerated expansion of the universe. By examining the size, distribution, and shape of these voids, scientists can gather indirect clues about how dark energy behaves across vast distances and different periods of cosmic history. For example, the rate at which voids expand can offer insights into the overall expansion rate of the universe, providing a complementary method of measurement alongside other techniques, such as observations of supernovae. Furthermore, the properties of cosmic voids, particularly their lack of galaxies and low density, make them invaluable laboratories for studying processes that would be difficult to isolate in denser regions of the universe. Within these voids, scientists can explore the formation and distribution of galaxies, shedding light on the underlying mechanisms that govern the structure of the cosmos. The emptiness of voids allows for a clearer view of the forces at play in the early universe, providing a critical context for understanding the ongoing evolution of cosmic structures. Ultimately, cosmic voids, like galaxy clusters, serve as essential pieces of the puzzle in our quest to understand the universe. They offer us a glimpse into the mysterious forces that shape the cosmos, from dark energy to dark matter, and provide the context for the ongoing growth and evolution of the universe's complex structure. In the vast emptiness of cosmic voids, something remarkable occurs. These immense empty spaces provide scientists with a rare opportunity to observe phenomena that are otherwise hidden behind the gravitational pull of denser regions of the universe. In the absence of significant gravitational forces, the influence of cosmic events, like galactic winds and the formation of small-scale structures, is laid bare. The quiet voids become a laboratory where fundamental forces shaping the cosmos can be dissected and understood. This unique perspective complements our knowledge of the universe's denser knots and filaments, creating a striking contrast between the universe's quietest and most active regions. It is this interplay, the dramatic contrast between the emptiness of cosmic voids and the rich density of cosmic filaments, that provides insight into the underlying forces driving the universe's evolution. The collision of galaxies, for example, is an intricate, complex event, not a dramatic crash like we might imagine with everyday objects. It's not the stars or planets themselves that collide, but rather their gravitational fields interacting, pulling, and distorting one another. Due to the enormous distances between stars, the sheer size of galaxies, and the vastness of the empty space between objects, a galaxy collision takes millions or even billions of years to unfold. What begins as a slight distortion in the outer regions of the galaxies transforms into a cosmic spectacle. Tidal forces, those invisible strings pulling at the galaxies, stretch out stars and gas into long streams called tidal tails, leaving a visible mark of their passage across space. As the galaxies approach each other, the central regions feel the brunt of the gravitational pull, dramatically altering their structures. Spiral arms become twisted and stretched. Gas clouds within the galaxies begin to compress, and the stars themselves are jolted into new formations. This compression of gas clouds triggers a burst of star formation known as a starburst. It's an explosive event where new stars form at an accelerated rate, igniting in the heart of the collision. The galaxies begin to pass through each other, then, like magnets, their gravitational forces draw them back for a more significant and often final merger. This coalescence is not just a reshaping of stellar matter, but also the merging of their supermassive black holes at the centers of each galaxy. As these black holes collide, they release tremendous energy, sometimes creating powerful quasar emissions or active galactic nuclei, spectacular bursts of light and energy visible across the universe. After this final merger, the galaxy settles into a more elliptical shape, forgoing the characteristic spiral arms of its former self. Over billions of years, these mergers play a critical role in the evolution of galaxies, allowing them to grow and transform, impacting the distribution and types of stars they host. Each collision adds another layer to the intricate history of the universe, a story written in the very structure of the galaxies themselves. Yet, beyond the stars and galaxies, there exists an invisible force, dark energy. This mysterious force seems to be accelerating the expansion of the universe, pushing galaxies further apart over time. First detected in the late 20th century, when astronomers studying distant supernovae discovered these explosions were dimmer and thus farther away than expected, dark energy quickly became one of the greatest puzzles in cosmology. If gravity pulls matter together, dark energy acts as a cosmic repellent, pushing galaxies and clusters of matter away from one another. Though we've known about dark energy for decades, its true nature remains largely speculative. The most prominent hypothesis is that dark energy might be related to a property of space itself, a remnant of Albert Einstein's cosmological constant, which suggested the energy density of space remains unchanged as the universe expands. What dark energy means for the universe's future is profound. If its repulsive force continues to dominate, the universe will keep expanding faster and faster, eventually leading to a big freeze scenario. Galaxies will drift so far apart that they will no longer be visible from one another, stars will burn out, and the universe will enter a cold, dark age. But despite our growing understanding of dark energy's effects, much remains unknown. The study of the cosmic microwave background radiation, galaxy clusters, and the large-scale structure of the universe continues to offer new clues, but the true identity of dark energy is still one of the most significant unsolved problems in modern science. To further explore the universe's hidden contents, scientists have also turned their attention to dark matter. Using techniques like gravitational lensing, they map the distribution of this elusive substance, which is invisible to telescopes, but reveals its presence through the distortion of light from more distant objects. By studying these gravitational distortions, researchers gain insight into the unseen mass that shapes galaxies, clusters, and ultimately the entire universe. There are two types of gravitational lensing: strong lensing, which produces dramatic arcs or multiple images of a single object, and weak lensing, which causes subtle statistical distortions in the shapes of many background galaxies. The weak lensing method, in particular, is incredibly powerful for mapping dark matter on large scales. It reveals the presence of dark matter even where no visible matter exists. This technique has proven to be one of the most effective tools for uncovering the invisible force that shapes the universe. Another critical method involves observing the motion of galaxies within galaxy clusters. The velocities of galaxies can be measured through the Doppler shift of their light. By measuring these velocities, astronomers can gain insight into the gravitational forces at play within the cluster. This data allows them to estimate the total mass of the cluster, including the unseen dark matter. Interestingly, the observed motion of galaxies within clusters often shows that the visible matter is insufficient to generate the required gravitational pull. This leads to the conclusion that a significant amount of dark matter must be present, even though it cannot be directly detected. Cosmic microwave background, CMB, radiation also provides critical clues about the distribution of dark matter. The CMB is the relic radiation from the Big Bang, and its fluctuations in temperature and density offer a snapshot of the early universe. By studying these fluctuations, scientists can model the initial distribution of matter and how it evolved over time, including the influence of dark matter in shaping the large-scale structure of the cosmos. Combining methods like gravitational lensing, galaxy motion, and CMB analysis, astronomers create detailed maps of dark matter. These maps reveal a cosmic web-like structure with dark matter forming a scaffolding within which galaxies and galaxy clusters reside. Advanced technologies and surveys, such as the Hubble Space Telescope, the Sloan Digital Sky Survey, and future missions like the Euclid Space Telescope and the James Webb Space Telescope, will continue to refine our understanding of dark matter distribution. They will unveil even more about this invisible, yet profoundly influential component of the universe. With these tools, astronomers are gradually piecing together the hidden forces that govern the cosmos. Galactic filaments are colossal, thread-like structures composed primarily of galaxies, gas, and dark matter. These filaments form part of the intricate cosmic web that spans the universe. They can stretch hundreds of millions of light years and serve as bridges between galaxy clusters, forming the framework upon which the large-scale structure of the universe is built. The formation of these filaments traces back to the early universe, following the Big Bang, when initial quantum fluctuations created slight density variations in the primordial plasma. As the universe expanded and cooled, these density fluctuations were amplified by gravity, causing regions with slightly higher densities to attract more matter. Over time, these regions grew denser, eventually forming long interconnected structures of dark matter. Ordinary matter, composed of atoms, followed the gravitational pull of dark matter, accumulating along these filaments. As this ordinary matter collected, it cooled down and condensed, leading to the formation of stars and galaxies along the filaments. Though the process is governed by the same gravitational principles that direct the flow of ordinary matter, dark matter provides the underlying skeleton that holds everything together. Simulations of the universe's evolution, like those from the Millennium simulation, illustrate how these filaments emerged from initial conditions and evolved over billions of years. These simulations reveal a complex network of filaments, interspersed with voids, vast empty regions where very little matter exists. As galaxies form and evolve along these filaments, their interactions, mergers, and gravitational effects further shape the cosmic web. Filaments act as cosmic highways, guiding the movement of gas and galaxies toward denser nodes where galaxy clusters reside. This continual flow enhances the richness and complexity of the cosmic web, illustrating a dynamic and interconnected universe. Thus, galactic filaments are essential to understanding the large-scale structure of the universe. They not only reveal the distribution of matter, but also shed light on the gravitational and evolutionary processes that have sculpted the cosmos into the vast and captivating tapestry we observe today. Without these filaments, the universe would be a much different place, less organized, less structured, and far less fascinating. Superclusters of galaxies represent some of the largest known structures in the universe, each containing tens of thousands of galaxies spread across hundreds of millions of light years. These colossal assemblies present significant challenges and intriguing complexities to our understanding of cosmic structure. First and foremost, their sheer scale and mass concentration push the boundaries of current models of structure formation, requiring more sophisticated simulations and theories that account for such substantial accumulations of matter. One of the primary challenges superclusters pose is their formation and evolution within the framework of the Big Bang and cosmic inflation theories. According to our current understanding, the early universe underwent rapid expansion, smoothing out initial irregularities in the density distribution of matter. Over time, gravity amplified these slight variations, leading to the clustering of matter into galaxies and larger conglomerates. However, the existence of superclusters necessitates that these initial density fluctuations were adequately significant and well distributed to eventually coalesce into such massive structures. This challenge requires precise fine-tuning in our models of initial conditions and particle physics, especially those concerning dark matter and dark energy, which are thought to drive cosmic evolution. The presence of superclusters forces us to rethink the foundations of our understanding of the universe's earliest moments, pushing the limits of our knowledge about the birth and evolution of the cosmos. As we continue to develop more advanced models and simulations, we may one day uncover the secrets behind these extraordinary cosmic structures, revealing even deeper insights into the nature of our universe. The vastness of our universe is filled with mysteries that stretch the limits of human understanding. Among the most fascinating of these are superclusters, colossal cosmic structures that challenge our comprehension of cosmic flows and gravitational forces on the largest scales. These superclusters, with their immense gravitational pull, don't just influence the galaxies within them. They have a far-reaching impact, affecting the motion of galaxies across vast expanses of space. The sheer magnitude of their gravitational force plays a role in phenomena such as the cosmic microwave background anomalies and the peculiar velocities of galaxies, both of which hint at the underlying complexity of the universe's structure. Take, for example, the observation of superclusters like the Sloan Great Wall and the Laniakea supercluster, which includes our own Milky Way. These vast cosmic structures are not solitary islands in space, but are interconnected through the delicate web of the cosmic web. Their interwoven nature tells us that the universe is far more interconnected than it may seem at first glance. To understand the dynamics of these superclusters, we must consider how they funnel and redistribute matter, particularly through their interactions with dark matter, the mysterious substance that makes up much of the universe's mass. Over billions of years, these superclusters evolve, their gravity shaping the galaxies and matter within them. Research into superclusters also holds the key to understanding dark energy, the enigmatic force behind the universe's accelerated expansion. The distribution of superclusters and their gravitational effects offer valuable clues about how dark energy influences the cosmos on the grandest scale. By studying these structures, we are not only gaining insights into the architecture of the universe, but also refining our models of how dark energy shapes the evolution of everything around us. This ongoing inquiry in both observational and theoretical astrophysics continually pushes the boundaries of human knowledge. One of the most compelling gravitational anomalies we've discovered is the Great Attractor, a mysterious region located in the direction of the Centaurus constellation, approximately 150 to 200 million light-years away from Earth. This region exerts an enormous gravitational influence on galaxies, including our very own Milky Way, as well as the Andromeda Galaxy and the entire local group of galaxies. Spanning hundreds of millions of light-years, the Great Attractor appears to be a gravitational focal point, pulling clusters of galaxies toward it. What makes the Great Attractor especially intriguing and difficult to study is its location within the zone of avoidance. This area of the sky is densely obscured by the plane of our Milky Way, filled with thick clouds of gas and dust that block out traditional optical observations. As a result, astronomers have to rely on X-ray and radio observations to uncover the secrets hidden in this darkened region. Through this unconventional approach, researchers have determined that the Great Attractor aligns with the center of the Laniakea supercluster, the vast cosmic neighborhood that contains our galaxy. This gravitational anomaly disturbs the motion of galaxies, pulling them at extraordinary speeds, some reaching hundreds of kilometers per second. The immense gravitational pull of the Great Attractor suggests it contains a massive amount of mass, far beyond what can be accounted for by the visible matter we can observe. It is likely that this region harbors enormous galaxy clusters and, even more profoundly, an immense amount of dark matter, the invisible substance that constitutes approximately 85% of the universe's total mass. Unraveling the mystery of the Great Attractor is critical for completing our understanding of the cosmic forces that shape the universe. It impacts the trajectory and evolution of galaxies, influencing their future over vast timescales. As technology advances and new observational techniques become available, our understanding of these cosmic phenomena continues to grow. The study of the Great Attractor is not just about understanding a single anomaly. It's about refining our models of the universe's gravitational landscape and cosmic flow. These advancements help us better comprehend the formation of cosmic structures, how they evolve over time, and how they influence the universe's expansion. Alongside these massive structures, dwarf galaxies also play a crucial role in shaping the cosmos. These small galaxies, typically containing just a few million to a few billion stars, frequently interact with larger galaxies like the Milky Way through gravitational processes. These interactions, often chaotic and dynamic, have a profound impact on both the dwarf galaxies and their larger counterparts, influencing the evolution of galaxies across the universe. Understanding the intricate web of interactions between these galaxies offers a deeper insight into the forces that govern our cosmic neighborhood. As we continue to peel back the layers of the universe, every new discovery, whether about superclusters, gravitational anomalies, or dark matter, adds another piece to the puzzle. The universe is vast and complex, and as we learn more about these hidden forces, we move closer to understanding the true nature of the cosmos, its past, its present, and its future. Each new finding invites us to question the very fabric of reality, propelling us forward in our quest for knowledge. One of the most striking and observable phenomena in the universe is the process of galactic cannibalism. This occurs when the gravitational pull of a larger galaxy captures a smaller, less massive dwarf galaxy, eventually absorbing it into its vast cosmic structure. The larger galaxy's immense gravity dominates the smaller galaxy, gradually stripping away its stars, gas, and dark matter. As the dwarf galaxy is pulled in, this process is clearly visible through the elongated streams of stars and gas that trail behind it, known as tidal streams. These spectacular cosmic ribbons are created as the dwarf galaxy is torn apart by the forces at play. A perfect example of this process can be found in the Milky Way's satellite dwarf galaxies, such as the Magellanic Clouds. As these smaller galaxies orbit the Milky Way, they experience intense tidal forces exerted by its gravity, which results in the loss of stars and gas. The material stripped away often forms dramatic bridges and tails that connect the two galaxies. One of the most notable of these structures is the Magellanic Stream, an enormous ribbon of gas stretching across the sky, emanating from the Magellanic Clouds. This interaction, while destructive, is not without its positive effects on the host galaxy. As the gas from the dwarf galaxy is funneled into the Milky Way, it compresses, creating dense pockets that can eventually collapse to form new stars. This process of stellar formation is just one example of how galactic cannibalism can fuel the growth of the larger galaxy. Dwarf galaxies, in fact, play a crucial role in the evolution of their larger host galaxies. When a dwarf galaxy is absorbed, the accretion of its material adds fresh gas and stars to the host galaxy's halo, altering its overall mass and potentially sparking periods of intense star formation. This ongoing accumulation of material contributes to the growth and evolution of the host galaxy over cosmic timescales. Furthermore, the assimilation of stars from smaller galaxies also changes the chemical composition of the larger galaxy, which can affect the dynamics of its halo. These interactions, through countless mergers and accretions, are essential in the growth and evolution of galaxies like the Milky Way over billions of years. But these mergers also reveal much more than just the fate of individual galaxies. By studying the distribution and behavior of dwarf galaxies around the Milky Way, astronomers gain valuable insights into the unseen structure of the universe, specifically the elusive dark matter. The way these dwarf galaxies orbit and interact with the Milky Way provides indirect clues about the dark matter halo surrounding the galaxy. These interactions are fundamental to the hierarchical model of galaxy formation, which suggests that large galaxies are built up through successive mergers of smaller galaxies over time. As astronomers continue to study these processes, they unlock the secrets of how galaxies grow and evolve in the vast expanse of the universe. Shifting to another cosmic phenomenon, supernovae are colossal explosions marking the catastrophic end of a star's life. These incredibly violent events release immense amounts of energy, light, and heavy elements into the surrounding space, playing a pivotal role in the cycle of matter throughout the universe. Supernovae come in two primary types: core collapse supernovae and thermonuclear supernovae, each arising from different stellar processes. Core collapse supernovae, also known as Type 2, Type 1, and Type IC supernovae, occur in massive stars, those with a mass greater than 8 times that of the Sun. Within these stars, nuclear fusion continuously creates heavier elements in the core, starting from hydrogen and progressing all the way up to iron. However, once the core becomes predominantly iron, fusion can no longer generate energy to counteract gravity, leading to a rapid collapse. The implosion generates a shock wave, resulting in a massive explosion, a supernova. The distinction between Type 2, Type 1, and Type YC supernovae lies in the outer layers of the progenitor star. Type 2 retains its hydrogen envelope, while types on B and IC have lost their hydrogen, with type IC even shedding its helium layer. Thermonuclear supernovae, or Type 1a supernova, occur in binary star systems where one star is a white dwarf, a dense remnant of a star that has exhausted its nuclear fuel. When a white dwarf accumulates material from a companion star, either through accretion or via a merger, it can reach a critical mass known as the Chandrasekhar limit, approximately 1.4 times of the Sun. At this point, the pressure becomes so intense that runaway nuclear reactions ignite in the core, causing the white dwarf to explode in a thermonuclear fireball. Unlike core collapse supernovae, Type 1a supernovae exhibit a consistent peak brightness, which makes them invaluable as standard candles for measuring cosmic distances and studying the expansion of the universe. Both types of supernovae, though originating from vastly different processes, contribute to the enrichment of the interstellar medium with heavy elements. These elements, from carbon to iron and beyond, are crucial for the formation of new stars, planets, and ultimately life itself. Thus, supernovae are not just explosive events, but are integral to the continuing cycle of creation and destruction in the cosmos, pushing forward the evolution of galaxies, stars, and the very building blocks of life across the universe. In the grand theater of the cosmos, where stars are born and die in spectacular fashion, the building blocks of life emerge as more than just a fundamental concept. They are the very foundation for understanding not only the life cycles of stars, but the broader tapestry of cosmic evolution and the intricate processes of chemical enrichment throughout the universe. Neutron stars, some of the most enigmatic objects in our universe, are born from the explosive deaths of massive stars. These cataclysmic events, known as supernovae, result from the collapse of a star's core under its own immense gravity after it has exhausted its nuclear fuel. When the core's mass is between approximately 1.4 and 3 times that of our Sun, it condenses into a neutron star, a hyperdense object held together by the incredible force of neutron degeneracy pressure. This process not only creates one of the most extraordinary objects in the universe, but also marks a critical point in the cycle of stellar evolution. The mass of a typical neutron star ranges from 1.4 to roughly 2.0 times that of the Sun, but it is compressed into a sphere no more than 10 to 15 kilometers in diameter. This makes it one of the densest objects in existence. A mere teaspoon of neutron star material would weigh an astonishing billion tons. The matter inside is in an exotic state, found nowhere else in the cosmos. Under these extreme conditions, neutron stars exhibit features that challenge our understanding of physics. They possess magnetic fields that are trillions of times stronger than Earth's. These intense magnetic fields accelerate charged particles to unimaginable speeds, often resulting in the emission of high-energy radiation like X-rays or gamma rays. Some neutron stars, in fact, are observed as pulsars, rapidly rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As these stars spin, their radiation sweeps across space like a lighthouse beacon, and when these beams align perfectly with Earth, we see them as periodic pulses. Some pulsars can spin at jaw-dropping speeds, rotating hundreds of times per second. This rapid rotation, combined with the neutron star's intense surface gravity, around 100 billion times that of Earth, produces another fascinating phenomenon, the warping of space-time. This distortion, as predicted by Einstein's theory of general relativity, can be measured, offering a unique glimpse into the nature of gravity and the fabric of space itself. Neutron stars are also powerful emitters of gravitational waves, ripples in space-time that are caused by violent cosmic events, like the collision of two neutron stars, or a neutron star merging with a black hole. The detection of these waves by observatories like LIGO and Virgo has opened a new frontier in astronomy, providing us with an entirely new way to study the universe. The study of neutron stars offers incredible insights into the fundamental properties of matter under the most extreme conditions imaginable. These cosmic laboratories give scientists the opportunity to observe the interactions of particles and forces at densities and energies that cannot be replicated on Earth, pushing the boundaries of our understanding of physics. One particular subclass of neutron stars stands out due to their extraordinary magnetic properties: magnetars. These stars, which have the most intense magnetic fields known to exist in the universe, are a special class of neutron stars. While typical neutron stars already possess strong magnetic fields, magnetars take this to a whole new level. Their magnetic fields can reach strengths up to 1,000 trillion Gauss. For perspective, Earth's magnetic field is just about half a Gauss, and a regular neutron star's magnetic field might range from 10 to 100 million Gauss. The formation of a magnetar is similar to that of other neutron stars that's arising from the collapse of a massive star during a supernova explosion. However, what sets magnetars apart is the unique conditions that exist within their progenitor stars. Rapid rotation and specific internal dynamics may amplify the magnetic field to these extreme levels. The exact process behind this amplification is still an open question, but one leading theory suggests that it is the result of a dynamo process during the first few seconds after the birth of the neutron star, where rapid rotation and convection within the star work together to enhance the existing magnetic field. The magnetic fields of magnetars are so powerful that they can have profound effects on their surroundings. The intense radiation they emit can affect nearby matter, causing distortions in the electromagnetic environment and possibly even influencing the formation of other celestial objects. Understanding magnetars and neutron stars alike continues to challenge our comprehension of the cosmos, offering a never-ending source of fascination and discovery. The fields surrounding magnetars are so intensely powerful that they can bend the very fabric of space, distorting the shape of atoms and affecting the quantum vacuum itself. This disturbance leads to unusual phenomena that, like vacuum biofringent, where the vacuum behaves as a biofringent medium due to the intense magnetic influence. Magnetars, with their extraordinarily strong magnetic fields, exhibit incredibly dramatic and violent activity, producing bursts and flares of X-rays and gamma rays. These bursts are not random, but arise from the unstable behavior and reconnection of magnetic field lines. When these field lines snap and reconnect, they unleash a vast amount of energy in a fraction of a second. In fact, the bursts from magnetars are among the most energetic events ever recorded in the universe. Some of the most extreme manifestations are seen in phenomena like soft gamma ray repeaters, SGRs, and anomalous X-ray pulsars. SGRs are known for their intense, episodic bursts of hard X-rays and soft gamma rays. These bursts can become so powerful that they temporarily outshine every other X-ray source in the entire sky. One particularly notable event recorded in 2004 was a flare from the magnetar SGR 1806-20, which emitted more energy in just a fraction of a second than the Sun does over a span of 100,000 years. The study of magnetars provides invaluable insights into exotic states of matter and magnetic fields under extreme conditions. It also offers a unique glimpse into the behavior of fundamental particles and the intricate interactions of quantum fields, acting as an unparalleled cosmic laboratory. Magnetars continue to challenge our understanding of physics and the dynamics of stellar evolution, pushing the boundaries of what we know about the universe. These powerful celestial objects reveal profound mysteries of matter and energy, providing clues to the deeper mechanics of the cosmos. In binary star systems, mass exchange can occur under specific conditions, particularly when one star expands beyond its Roche lobe. This lobe is the region around a star within which orbiting material is gravitationally bound to that star. When a star in a close binary system reaches this threshold, its outer layers overflow into the space around it. This overflow typically occurs in systems where the stars are in close proximity. The mass transfer process has far-reaching consequences for both stars in the system, altering their evolutionary paths in ways that are both complex and fascinating. A red giant, or supergiant star, is usually the primary donor in these systems. As it evolves off the main sequence, it expands, and once it fills its Roche lobe, material starts flowing toward its companion star. The receiving star may or may not have undergone significant evolutionary changes. If the companion star is a compact object like a white dwarf, neutron star, or black hole, the material flowing from the donor star can form an accretion disk around it. This disk emits large amounts of energy, often observable in X-ray binaries, where the accreting object is a neutron star or black hole. Mass transfer between stars has significant consequences. The donor star loses mass, which can drastically shorten its life cycle. This process can push it into different evolutionary phases, such as becoming a white dwarf or rapidly entering a helium-burning phase. The accreting star, on the other hand, gains mass, which can lead to rejuvenation. If the accreting star was initially of lesser mass, this additional material can allow it to burn hydrogen again, causing it to evolve into a more massive star. One of the most explosive outcomes of mass transfer occurs in systems involving white dwarfs. If a white dwarf in a binary system accumulates enough material from its companion star to approach the Chandrasekhar limit, about 1. For solar masses, it can trigger a runaway nuclear fusion reaction, culminating in a Type 2a supernova. These supernovae are of great importance in measuring cosmic distances due to their predictable luminosity. Another fascinating consequence of mass exchange is the formation of peculiar stars like blue stragglers. These stars are an anomaly within their clusters, appearing younger and hotter than other stars of the same age. It is believed that blue stragglers are the result of mass transfer, where the material gained from a companion star alters the evolutionary course of the star, causing it to behave differently from other stars in the same stellar population. This phenomenon adds another layer of complexity to our understanding of stellar evolution and the intricate interactions within binary star systems. In the vast expanse of the universe, the processes shaping the fate of stars and their interactions are intricate and dynamic. Mass transfer within binary star systems, for example, has profound effects on their orbital characteristics. As mass is transferred from the donor star to its companion, the system's center of mass shifts. This change often alters the orbital period and eccentricity, especially in cases where a significant amount of mass is lost to the interstellar medium. The system's total mass can decrease, leading to an increase in orbital separation. Such shifts illustrate just one aspect of mass exchange in binary systems, a complex process that is transformative, not just for the stars involved, but for the broader cosmic environment as well. In some cases, this exchange contributes to energetic events that ripple outward, affecting nearby celestial bodies. The evolution of these stars, fueled by these interactions, can take unexpected turns, pushing them toward dramatic changes. These phenomena also help scientists understand the broader mechanisms at play within the universe, demonstrating how even the smallest shifts in mass can lead to grand cosmic consequences. The interplay between these stellar bodies is a key element of how the universe continues to evolve, constantly reshaping its structure. Among the many fascinating objects in the cosmos are brown dwarfs, a class of celestial objects that occupy a unique space between the largest planets and the smallest stars. Often referred to as failed stars, brown dwarfs are intriguing not because of their inability to ignite nuclear fusion, but because of their potential to unlock secrets about the boundary between stars and planets. When a star forms, it needs to amass enough mass to trigger hydrogen fusion in its core, which requires a mass of at least 75 times that of Jupiter. Brown dwarfs, however, fall short of this threshold, typically weighing between 13 and 65 Jupiter masses. Due to this mass limitation, brown dwarfs can't sustain the traditional hydrogen fusion that powers more massive stars like our Sun. Instead, they emit a dim reddish glow, a far cry from the bright radiance of a typical star. Yet, despite their inability to sustain regular fusion, brown dwarfs still engage in a limited form of nuclear fusion. They are able to fuse deuterium, a heavier isotope of hydrogen, and in some cases lithium. However, these fusion reactions are short-lived and insufficient to elevate brown dwarfs into the category of stars. Their temperatures and luminosities lie somewhere between those of stars and gas giant planets, making them critical subjects for studying the transition between stellar and planetary formation. These failed stars may not be the stellar giants we often envision, but they are far from failures in the grand scheme of the cosmos. Instead, they provide invaluable insights into the universe's most fundamental processes. Massive stars, those with more than 8 times the mass of our Sun, serve as the cosmic forges where the heaviest elements in the universe are born. Through a process known as nucleosynthesis, these fiery giants transform lighter elements into heavier ones. This process begins with hydrogen fusion, converting hydrogen into helium, and as the star ages, it begins to fuse heavier elements in its core. With time, the fusion ladder climbs, starting with hydrogen, moving through helium, and advancing to carbon, oxygen, and beyond. As the star exhausts its hydrogen fuel, the core contracts and its temperature rises, eventually reaching levels high enough to fuse carbon into heavier elements like neon, magnesium, and silicon. The star continues this escalating chain of fusion until iron is produced in its core. However, iron fusion is different from earlier stages. It consumes energy rather than producing it, halting the exothermic fusion processes that had been powering the star up to that point. When the star's core collapses under its own gravity, a supernova explosion is triggered, releasing an enormous amount of energy. This explosion causes a burst of neutrons that collide with atomic nuclei in a process known as neutron capture. Through this process, elements like gold, uranium, and platinum are formed. The immense force of the supernova disperses these newly forged elements into space, enriching the surrounding environment with the building blocks for future generations of stars, planets, and potentially even life. The explosive death of a massive star thus not only marks the end of its life cycle, but also plays a crucial role in the ongoing creation of the universe, spreading essential elements that shape the formation of new worlds and life. In this mesmerizing spectacle, massive stars serve as the cosmic crucibles, forging the elements that will eventually build the complex structures and life forms that fill our universe. A pulsar is one such extraordinary phenomenon, born from the remnants of a supernova explosion. When a massive star burns through its nuclear fuel, its core collapses under the immense pressure of gravity, compressing protons and electrons together into neutrons. This collapse creates an incredibly dense object, often no more than 20 kilometers in diameter, yet containing the mass of 1 to 2 suns. The pulsar's distinguishing feature is its intense magnetic field, which can be over 1 trillion times stronger than Earth's. This magnetic field accelerates charged particles near the star's magnetic poles, causing them to emit beams of electromagnetic radiation, often in the form of radio waves. Due to the misalignment between the pulsar's rotational axis and its magnetic field, these beams sweep across space like the beams of a lighthouse. When one of these beams points toward Earth, it is detected as a pulse of radiation, a regular and predictable signal that acts like a cosmic clock. What makes pulsars even more captivating is the astonishing precision with which they pulse. The frequency of these pulses can range from a few times per second to over 600 times per second, and the regularity with which they occur is unmatched by any human-made technology. The rapid rotation of the neutron star, along with its immense gravitational and magnetic fields, ensures the stability of the emission mechanism, allowing for incredibly precise intervals between pulses. This consistency allows astronomers to use pulsars not only as clocks to measure cosmic distances, but also as tools to test theories of general relativity. These fascinating cosmic objects help us unlock secrets about the fundamental nature of our universe, serving as indispensable tools in astrophysical research. Stellar nurseries, or molecular clouds, are vast regions of gas and dust where new stars are born. These clouds are mostly made of hydrogen molecules, along with small amounts of other elements and compounds. The birth of new stars begins with the cooling and condensation of these dense molecular clouds over time. As certain regions of the cloud grow denser, they experience gravitational instabilities, causing them to collapse under their own weight. For a star to form, certain conditions must be met. First, the molecular cloud needs to be dense enough to accumulate sufficient material for nuclear fusion. The cloud must also be cold, typically between 10 and 20 Kelvin above absolute zero, as lower temperatures promote the formation of molecular hydrogen, the fundamental building block of stars. Turbulence within the cloud creates clumps of matter, which serve as the seeds for star formation. When these clumps reach a critical mass, gravity takes over, pulling in more material and increasing the pressure and temperature at the core. Once the core reaches temperatures of around 1 million Kelvin, nuclear fusion ignites, converting hydrogen into helium and releasing energy in the process. The energy generated by nuclear fusion creates an outward pressure that counteracts the inward pull of gravity, leading to the formation of a new protostar. As the protostar continues to accumulate material from its surroundings, it grows in mass and luminosity until it reaches the stable equilibrium of a main sequence star. Throughout this process, the surrounding gas and dust are either incorporated into the forming star or swept away by the star's powerful stellar winds and radiation, often creating stunning nebulae that mark the birthplace of new stars. These stellar nurseries are essential to the ongoing evolution of the cosmos, turning cold, dark clouds into the brilliant stars that light up the night sky. But they are not just factories for star creation. They are also laboratories that allow astronomers to study the fundamental processes that govern the life cycles of stars and the dynamics of entire galaxies. One of the most remarkable types of stars is the Wolf-Rayet star, a rare and extreme form of massive star. These stars are distinguished by their incredibly high temperatures, powerful stellar winds, and prominent spectral lines that indicate a high level of ionization. Wolf-Rayet stars represent the final phase in the evolution of massive stars, typically those with initial masses greater than 20 times that of the Sun. Through intense stellar winds, these stars shed their outer hydrogen layers, exposing their hot, helium-rich cores. The rarity of Wolf-Rayet stars is due to the rapid and tumultuous path they follow in their evolution. Only a small fraction of massive stars ever reach this stage, as the conditions required are both specific and short-lived. These stars burn through their fuel at an astonishing rate, living fast and dying young, spending only a few 100,000 years in the Wolf-Rayet phase. This brief lifespan is minuscule compared to the millions or even billions of years that lower mass stars like our Sun spend on the main sequence. The hallmark of a Wolf-Rayet star is its powerful stellar wind, which can eject material at speeds of up to several thousand kilometers per second. These winds strip the star of its outer layers, enriching the surrounding interstellar medium with heavy elements. The material ejected from the star forms spectacular nebulae, illuminated by the star's intense radiation. As the star continues to shed mass, it grows increasingly unstable, eventually reaching the end of its life. Most Wolf-Rayet stars are expected to end their existence in a dramatic supernova explosion, which could lead to the formation of a black hole or a neutron star. The death of these stars is as dramatic and intense as their lives, marking the end of an extraordinary cosmic journey. In this awe-inspiring journey of stars, from pulsars and stellar nurseries to Wolf-Rayet stars, we witness the cyclical nature of stellar life, death, and rebirth. These processes not only shape the universe, but also provide us with essential tools to explore the cosmos and deepen our understanding of the fundamental forces that govern it. Every pulse of a neutron star and every explosion of a Wolf-Rayet star takes us one step closer to unraveling the mysteries of the universe itself. In the vast expanse of the cosmos, the rarity of Wolf-Rayet stars lies in their extreme, fleeting nature. These stars are not merely fascinating celestial objects. They are integral to our understanding of the universe's most massive stars and their life cycles, but their role extends beyond that. They are essential contributors to the chemical enrichment and dynamic processes in galaxies. Wolf-Rayet stars serve as both creators and destroyers in the cosmic landscape, influencing everything around them with their intense energy and short-lived existence. In the complex dance of binary star systems, a captivating phenomenon known as stellar vampirism unfolds. This dramatic and often destructive process occurs when one star, usually the more massive and evolved companion, begins to siphon material from its partner. The binary systems consist of two stars that orbit each other closely, and as they evolve, their interactions become more dynamic. In some cases, these interactions turn predatory, with one star literally feeding on the other. The process of stellar vampirism typically begins when the more massive star, having evolved into a red giant, expands and causes its outer layers to overflow its gravitational boundary. This boundary is known as the Roche lobe. When the outer material of the red giant crosses this boundary, it is pulled toward the gravitational pull of the smaller, denser companion star. This companion, often a white dwarf neutron star, or even a black hole, then captures the gas and dust spiraling toward it. The captured material forms an accretion disk around the compact object, which then feeds off the energy and mass, altering both stars' evolutionary paths. The exchange of material between the stars can have profound effects on the system. The mass-gaining star experiences a dramatic increase in luminosity and temperature, leading to periods of intense radiative outbursts. Meanwhile, the donor star is stripped of its outer layers, exposing its core and significantly altering its own evolutionary trajectory. In some extreme cases, the vampirized star is entirely consumed or reduced to a much less massive remnant. This transfer of mass between the two stars can lead to spectacular cosmic phenomena. For example, in a binary system involving a white dwarf, the accumulation of enough material may trigger a thermonuclear runaway reaction, resulting in a Type 1a supernova. These supernovae are crucial for astronomers, as their consistent luminosity allows them to be used as standard candles to measure cosmic distances. This dramatic interaction between stars reveals a deeper understanding of the universe's ongoing cycle of creation, destruction, and transformation. It paints a picture of an unpredictable and often dangerous cosmic dance, where even the most massive stars are at the mercy of gravitational forces beyond their control. Stellar vampirism is a perfect example of how the fate of stars in binary systems are intertwined, each star shaping the destiny of the other in a profound and sometimes violent manner. Meanwhile, in a different realm of thought, the Fermi paradox presents a puzzling contradiction. It highlights the discrepancy between the high probability of extraterrestrial civilizations existing in our vast galaxy and the lack of any evidence or contact with such civilizations. This paradox was famously named after physicist Enrico Fermi, who bluntly asked, "Where is everybody?" The paradox brings into question why, if the universe is so vast and the probability of intelligent life is so high, we have yet to find any signs of extraterrestrial life. The silence we encounter in our searches for alien civilizations raises profound questions about the nature of life itself. One proposed solution to the Fermi paradox is the rare Earth hypothesis. This hypothesis suggests that a unique combination of rare and complex factors has conspired to make Earth exceptionally suitable for life. These factors include our planet's stable climate, a protective magnetic field that deflects harmful cosmic rays, the availability of liquid water, and the stabilizing influence of Jupiter. Jupiter's immense gravity helps shield Earth from potential impacts by comets and asteroids, making the conditions for life on Earth highly improbable, yet incredibly rare. This confluence of factors may make Earth an extraordinary, perhaps even unique, oasis of life in an otherwise inhospitable galaxy. While we continue to search for answers to the Fermi paradox, we are reminded of how precious and rare the conditions for life can be. In a universe where stars are born, live, and die in cycles of unimaginable scale, the existence of intelligent life, if it exists elsewhere, might be one of the rarest phenomena of all. As we look to the stars, we find that the universe is both a vast and mysterious place, full of wonder and possibilities, yet untouched by the certainty of answers. The hypothesis suggests a thought-provoking possibility. Microbial life may be abundant in the universe, but the emergence of intelligent life could be an extraordinarily rare event. This idea challenges our assumptions about the likelihood of finding other intelligent civilizations. However, it is not the only theory that attempts to explain the absence of detectable extraterrestrial life. One particularly compelling idea is the Great Filter theory, which proposes that there is a critical stage in the evolution of life that is highly improbable to surpass. This filter could exist at various stages, such as the emergence of life itself, the transition from simple cells to more complex organisms, or even the leap from advanced civilizations to spacefaring societies capable of interstellar communication. According to the Great Filter theory, there are two possibilities. Either humanity has already passed this rare and difficult hurdle, making us uniquely advanced, or the filter lies ahead of us, posing a significant challenge to our long-term survival. The question then becomes, where exactly does this filter lie, and what are the consequences if we haven't yet surpassed it? Alternatively, other theories entertain the possibility that extraterrestrial civilizations may be aware of us, but are deliberately avoiding contact. This idea suggests that alien societies could have imposed a self-quarantine to protect less advanced civilizations, much like the fictional Prime Directive seen in science fiction. It is also possible that extraterrestrial civilizations are using communication technologies or strategies beyond our current understanding, further complicating our efforts to detect them. Another hypothesis that has garnered attention is the simulation theory, which posits that our perceived reality might be an artificial simulation. In this scenario, the absence of contact with extraterrestrial life could be a deliberate parameter set by the creators of this simulated environment, raising questions about the nature of existence and our place in the cosmos. These various theories, each distinct in its implications, highlight the complexity of the search for extraterrestrial intelligence, pushing us to re-examine our assumptions and to look both inward and outward with greater curiosity and wonder. Fast radio bursts, FRBs, are another cosmic enigma that have captured the attention of scientists and astronomers. These brief, intense bursts of radio waves last only milliseconds, but release an amount of energy equivalent to what the sun emits in an entire day. First discovered in 2007, FRBs present significant challenges due to their mysterious origins and extreme energy scale. Their fleeting nature, combined with their enormous power, makes them both a captivating and puzzling subject of study. One of the major difficulties with studying FRBs is pinpointing their exact source. The short duration and unpredictable nature of these bursts make them difficult to localize with precision. Early detections were thought to be isolated, random events originating from distant regions beyond our galaxy. However, the discovery of repeating FRBs has added layers of complexity to the mystery, suggesting that, unlike one-off cataclysmic events like supernovae, there could be a mechanism or environment capable of producing multiple bursts over time. The potential sources of FRBs are varied and intriguing. They may originate from highly magnetized neutron stars known as magnetars, which generate extreme magnetic fields and intense radiation. Alternatively, FRBs could be the result of exotic phenomena involving black holes or even advanced alien technologies, though the latter remains purely speculative. The discovery of repeating FRBs has deepened the mystery and prompted scientists to reconsider their existing astrophysical models. FRBs also present an opportunity to probe the intergalactic medium, the sparse hydrogen and helium gas that fills the space between galaxies. As these bursts travel across vast distances, their radio waves interact with free electrons encountered along the way, causing a dispersion effect. By analyzing this dispersion, scientists can infer properties of the intergalactic medium and gain insights into the distribution of matter in the universe. This effect provides a new method for studying the cosmos on a grand scale, unlocking secrets about the invisible structures that shape the universe. The study of FRBs challenges existing scientific models and calls for the development of more advanced observational technologies. Current instruments are not sufficient to fully capture and analyze these elusive signals, highlighting the need for better tools to explore the universe's most energetic and short-duration events. The ongoing research into fast radio bursts offers the potential to solve one of the most captivating cosmic mysteries of our time, and to deepen our understanding of the universe's fundamental structure and the extreme environments that exist within it. As scientists continue to unravel the origins and implications of FRBs, they are uncovering new avenues for exploring the nature of reality itself. The Great Silence, an eerie and perplexing enigma, continues to captivate the imagination of scientists, astronomers, and thinkers across the globe. Despite the overwhelming scale of the universe, filled with billions of stars and potentially even more planets, we hear nothing from extraterrestrial civilizations. The vastness of the cosmos suggests that intelligent life should exist elsewhere. Yet the silence is deafening. No signals, no probes, no tangible signs of alien activity. This mystery is intertwined with the Fermi paradox, a dilemma that has confounded generations. If the universe is so vast and old, about 13 billion years, and if the number of potentially habitable planets is astronomical, why haven't we heard from anyone? Where are the aliens? One explanation for this silence is the rare Earth hypothesis. This theory suggests that the conditions required for intelligent life, like those we enjoy on Earth, are extraordinarily rare. Perhaps life is common in the universe, but intelligent life capable of communicating across the stars is a unique rarity. This would mean we are, in essence, alone in the cosmos, isolated on a planet in a largely barren universe. Another intriguing possibility is the zoo hypothesis. According to this theory, advanced extraterrestrial civilizations may be aware of our existence but intentionally avoid making contact, much like humans observe animals in a zoo, carefully maintaining a safe distance. Their reasons could range from ethical concerns about interfering with our natural development to a desire to study us in our unspoiled state. Then there's the Great Filter Hypothesis, a chilling notion suggesting that there is a crucial stage in the development of life, perhaps the leap from simple organisms to intelligent beings, or the ability to avoid self-destruction, that almost no civilization can surpass. If this great filter lies ahead of us, it could explain the absence of any alien signals. Civilizations may tend to self-destruct before achieving the technological capabilities necessary for interstellar communication. This theory raises the unsettling possibility that we may be the last generation of humans, with no other civilizations around to share the stars. Another perspective is that we may simply not be looking or listening in the right way. Advanced civilizations could be using forms of communication beyond our current understanding, methods and technologies far beyond our capabilities, leaving their signals undetectable with today's instruments. Moreover, the vast distances between stars and galaxies, combined with the incomprehensibly long timescales in play, mean that even if alien signals do exist, they may take eons to reach us, or they could be directed in ways we have yet to explore or comprehend. This cosmic silence remains one of the most profound and perplexing mysteries in the world of astronomy. It challenges our assumptions about life, intelligence, and our place in the universe. As we continue to search for signs of extraterrestrial life, new technologies are being developed to detect potential cosmic neighbors. The quest for contact remains one of the most compelling and exciting scientific endeavors of our time. But the mystery doesn't stop at the silence of alien civilizations. There's another riddle that has captivated the minds of astrophysicists for decades. The observation that some galaxies spin far faster than we ever expected. According to Newtonian mechanics and the visible matter in galaxies, stars at the outer edges of galaxies should orbit at slower speeds. Yet observations show that in many galaxies, particularly spiral ones, the stars on the outer rim spin at unexpectedly high velocities. This cosmic discrepancy has led to a groundbreaking realization: the existence of dark matter. While dark matter is invisible, unable to be detected through conventional electromagnetic observations, it is believed to make up approximately 27% of the universe's mass energy content, vastly more than the mere 5% accounted for by ordinary matter. Dark matter's gravitational pull is thought to explain the surprising rotational speeds of stars in the outer regions of galaxies. Essentially, it forms a vast, invisible halo around galaxies, its unseen gravity keeping stars in motion at higher velocities than we would expect from the visible matter alone. The evidence for dark matter is compelling, with support coming from various sources: its impact on the cosmic microwave background radiation, gravitational lensing, where massive objects bend the light from distant stars and galaxies, and the large-scale structure of the universe. Yet, despite all this indirect evidence, dark matter itself remains elusive. Scientists have been unable to directly detect it, and it continues to be one of the biggest unsolved mysteries in modern astrophysics. The search for dark matter is as crucial to our understanding of the universe as the search for extraterrestrial life, both enigmas that drive the quest for knowledge forward into the vast unknown. One of the most compelling and yet elusive topics in astrophysical research revolves around the hunt for dark matter. Scientists around the world have launched groundbreaking efforts to detect dark matter particles using sophisticated detectors buried deep underground. The purpose of these underground facilities is to shield the detectors from cosmic radiation and other forms of interference, ensuring the purity of their measurements. However, not all researchers believe that the answer lies in this mysterious substance. A group of scientists has proposed alternative theories, suggesting that perhaps our understanding of gravity itself needs to be modified. One such theory is modified Newtonian dynamics, or MOND, which posits that the laws of gravity may change under low acceleration conditions, specifically in the outskirts of galaxies. MOND offers an intriguing explanation for the observed rotational curves of galaxies, which traditionally required the presence of dark matter to explain. According to this theory, the gravitational force could be altered at the galactic edges, leading to the faster than expected rotation of stars. While MOND offers a compelling alternative, it fails to account for certain observations, particularly on larger cosmological scales, where the theory of dark matter still provides a much more complete and coherent explanation. The rapid rotation of galaxies has proven to be a monumental puzzle, pointing to the existence of a vast amount of unseen mass that is responsible for shaping the dynamics of these cosmic systems. The question now is whether this mystery will ultimately be solved by the discovery of dark matter, an adjustment to our theories of gravity, or perhaps some other unknown force or phenomenon yet to be uncovered. Regardless of the solution, this question remains one of the most critical drivers of research in modern astrophysics, reshaping our understanding of the universe's most fundamental nature. Turning from the unseen forces of the universe to the mysteries that reach us through space, the WOW signal stands as one of the most intriguing and enigmatic radio signals ever detected. Captured on August 15, 1977 by Dr. Jerry R. Amen using the Big Ear radio telescope at Ohio State University, this narrowband radio signal appeared to originate from the direction of the constellation Sagittarius. Lasting for a brief but powerful 72 seconds, the maximum time Big Ear could record, it was unlike anything previously observed. The signal was so strong that Dr. Amen was compelled to circle it on the printout and scrawl, "Wow! Wow!" in the margin, giving the signal its now legendary name. Despite numerous attempts to detect a repeat of the WOW signal from the same region of the sky, no such signal has ever been recorded again. This absence of recurrence makes it difficult for scientists to conduct further study or draw definitive conclusions about its origin. In the world of astrophysics, recurring signals are vital to understanding phenomena, as they allow for repeated observations from different locations and instruments. The one-time nature of the WOW signal means that astronomers are left with only the brief 72-second window to analyze and interpret its potential source. Several hypotheses have been put forward to explain the WOW signal, ranging from natural astrophysical phenomena to the tantalizing possibility of it being an artificial transmission. One natural explanation suggests that the signal could have been a reflection from Earth-based satellites or emissions from an asteroid, but these theories fail to account for the signal's narrow frequency band and intensity. Alternatively, the idea that the signal could be a message from an extraterrestrial civilization captures the imagination. This theory is bolstered by the fact that the signal was centered around the 1420 megahertz frequency, the natural emission frequency of neutral hydrogen, the most abundant element in the universe. This frequency is also considered a prime hailing frequency for potential interstellar communication. However, despite the excitement surrounding this theory, the failure to detect the signal again, and the lack of supporting data from other observatories leave its extraterrestrial origin firmly in the realm of speculation. Adding to the challenge, the limitations of the Big Ear telescope at the time of detection meant that there were gaps in the data, further complicating efforts to draw definitive conclusions. As it stands, the WOW signal remains one of the most mysterious phenomena in the search for extraterrestrial intelligence, symbolizing both the promise and the challenge of understanding the vast, unexplored universe. Though the WOW signal has not provided any concrete evidence of alien life, it continues to spark curiosity and inspire research. It serves as a reminder of the unexplained mysteries that lie beyond our planet and encourages the development of new, more advanced instruments and methods to probe the cosmos. As we continue to search for answers, the WOW signal remains an open question, a piece of the cosmic puzzle that fuels the ever-growing quest to explore the unknown. The observation that some stars appear older than the universe is a perplexing paradox that has intrigued astronomers and astrophysicists for many years. The universe's age is currently estimated at about 13.8 billion years, determined from measurements of the cosmic microwave background radiation and the rate at which the universe is expanding. However, certain stars, particularly ancient ones found in globular clusters, seem to defy this timeline. These stars exhibit characteristics that suggest they could be older than the calculated age of the universe itself, a mystery that has yet to be fully unraveled. To determine the age of a star, astronomers rely on a variety of methods, one of the most common being spectroscopy. By studying the composition of light emitted by a star, they can measure its metal content, astronomical metals being elements heavier than hydrogen and helium. Stars that possess low metallicity are often considered some of the universe's firstborn stars, created when the cosmos was still in its early stages, long before subsequent generations of stars produced heavier elements. Another technique for estimating a star's age involves examining its location on the Hertzsprung-Russell diagram, a graph that plots stars based on their luminosity and temperature. By understanding where a star falls on this diagram, scientists can predict its life cycle, which helps them calculate its age. However, the apparent paradox of stars that seem older than the universe may arise from a number of potential sources of error or misunderstanding. One of the main possibilities is that our current models of stellar evolution might require refinement. If key physical processes affecting a star's life cycle haven't been properly accounted for, it could lead to age estimates that are off. Furthermore, uncertainties in measurements such as distance, luminosity, and other crucial factors can result in inaccurate age calculations. Another significant factor is the uncertainty surrounding the Hubble constant, the rate at which the universe is expanding. Depending on the method used to measure it, estimates of the Hubble constant can vary, and even slight discrepancies in its value can lead to substantial differences in the calculated age of the universe. This challenge in reconciling the apparent age discrepancy between stars and the universe itself remains an active area of research. Astronomical observatories like the Hubble Space Telescope and upcoming instruments like the James Webb Space Telescope are expected to refine these measurements, bringing scientists closer to resolving this conundrum. Additionally, advancements in our understanding of dark energy and dark matter, two mysterious substances that make up most of the universe's mass and energy content, could provide crucial insights. As our tools and models improve, we may finally harmonize the seemingly impossible age discrepancies, providing a more complete picture of both stellar evolution and the cosmos as a whole. In conclusion, while the discovery of stars that appear older than the universe's estimated age is a captivating puzzle, it simultaneously pushes the boundaries of scientific knowledge. This paradox has become a catalyst for developing more accurate instruments and sophisticated models, driving further exploration into the fundamental processes that shape our universe. One of the largest and most massive structures in the observable universe is the Shapley supercluster, located approximately 650 million light-years from Earth in the direction of the Centaurus constellation. This immense supercluster, named after American astronomer Harlow Shapley, contains around 8,000 galaxies, making it one of the densest and most massive regions in the universe. The gravitational pull of the Shapley supercluster plays a key role in influencing the motion of our Milky Way galaxy, as well as the motion of our local galactic neighborhood. The combined mass of the galaxies, dark matter, and interstellar gas within the supercluster creates a deep gravitational well, which affects the peculiar motion patterns observed in our region of the universe. Our Milky Way galaxy, along with the rest of the local group, is being drawn toward a mysterious region called the Great Attractor. This gravitational anomaly, located about 150 to 250 million light-years away in the vicinity of the Hydra Centaurus supercluster, exerts an enormous gravitational force on galaxies within our neighborhood. While the Great Attractor is the dominant influence on the Milky Way's motion, the gravitational forces from the Shapley supercluster also contribute significantly to the movement. Essentially, the Milky Way's motion through space is the result of the combined gravitational effects from both the Great Attractor and the massive distant structures like the Shapley supercluster. Understanding these gravitational forces is crucial for astronomers seeking to map the large-scale structure of the universe. The dynamic motion of galaxies within these vast cosmic structures helps scientists track the evolution of the universe itself. This grand dance of galaxies and clusters, driven by gravity, unfolds over billions of years, shaping the cosmos in a way that is both intricate and awe-inspiring. As we continue to uncover the mysteries of these massive cosmic forces, we gain a deeper understanding of the universe's past, present, and future. In the vast, sprawling universe, structures like the Shapley supercluster, with its colossal collection of galaxies and enormous gravitational pull, shape the very motion of our Milky Way and its neighboring galaxies. By studying such enormous formations, astronomers hope to unravel the intricate web of gravitational forces that holds the cosmos together. These investigations give us a clearer picture, not just of our immediate galactic environment, but of the deeper, more complex workings of the universe itself. Meanwhile, in our own solar system, some planetary and moon-based geological activity is surprising and downright intriguing. It challenges everything we thought we knew about planetary science and geophysics. Traditionally, we believed significant geological events, like volcanic eruptions, tectonic shifts, and cryovolcanism, occurred mainly on larger, warmer planets like Earth. However, data from multiple space missions are turning that assumption upside down, showing that smaller, colder bodies also exhibit complex geological processes. This discovery suggests that geological activity is far more widespread and diverse than previously imagined. A prime example of this is Jupiter's moon Io, which holds the title of the most volcanically active body in the entire solar system. Io's geological frenzy is driven by tidal heating, a phenomenon caused by the immense gravitational forces from Jupiter and its neighboring moons, Europa and Ganymede. These forces generate internal friction within Io's interior, leading to constant volcanic eruptions. Some of these eruptions are so powerful they launch plumes of molten material hundreds of kilometers into space, making Io a fascinating case study in celestial dynamics. Further out in our solar system, Saturn's moon Enceladus provides another remarkable example. Despite its small size and considerable distance from the Sun, Enceladus showcases geysers that erupt from its southern polar region, sending water vapor and ice particles into space. These plumes are a strong indication of a subsurface ocean beneath the moon's icy crust, kept in a liquid state by heat produced from tidal interactions with Saturn. The discovery of organic compounds in these plumes adds another layer of mystery, offering tantalizing clues about the potential for life in these hidden sub-ice oceans. Neptune's moon Triton also defies expectations, demonstrating signs of cryovolcanism, volcanic activity that involves substances like water, ammonia, or methane instead of molten rock. Triton's surface is dotted with nitrogen geysers, which are driven by signal heating from the sun. These geysers release plumes of nitrogen gas and dust, providing strong evidence of internal geological activity, something that was once thought impossible on such a cold, distant moon. One of the most surprising revelations from the New Horizons mission is Pluto, once considered a frozen, inert dwarf planet. Instead, it was found to have a surprisingly youthful surface, brimming with features like ice mountains and vast plains of nitrogen ice. These signs suggest that Pluto's surface is far from static. Instead, ongoing geological processes are at work. The heat that fuels these processes likely comes from a mix of radioactive decay in Pluto's core and the possibility of subsurface oceans that remain warm due to internal heat. These discoveries push the boundaries of what we thought we understood about geological activity. No longer can we simply rely on the traditional mechanisms observed here on Earth, such as tectonic movements and volcanism. Now, tidal heating, radioactive decay, and the unique properties of icy and rocky materials in extreme environmental conditions are revealed as crucial players in the geophysical processes of moons and dwarf planets. This evolving understanding not only sheds light on the complexity of planetary geology, but also expands our horizons in the search for environments that might support life beyond Earth. In the end, our solar system is far more dynamic and diverse than we ever imagined. These findings don't just expand our knowledge of geological activity, they offer hope that life, perhaps in forms we've never conceived, could exist in places once thought too cold, or too far removed from the sun to support it. With each new discovery, the mysteries of our universe grow deeper, pushing us to look further, think bigger, and explore the farthest reaches of space in our quest to understand the cosmos. The Botez void, often simply called the void, stands as one of the most striking and mysterious features in the universe. Spanning nearly 330 million light-years in diameter, this vast and largely empty region is located within the Botez constellation. Its discovery in 1981 by astronomer Robert Kirshner and his team, while conducting a survey of galaxy redshift, stunned the scientific community. The sheer emptiness of the Botez void, with far fewer galaxies than one might expect in a region of space of such enormous size, initially left astronomers baffled. In fact, this absence of matter makes the void one of the largest known voids in the universe, a phenomenon that challenges our understanding of cosmic structure. This void is a striking example of the complex web of cosmic structures that makes up the large-scale framework of the universe. The universe itself resembles a vast, interconnected web composed of galaxy clusters and filaments with vast, empty expanses known as voids separating them. These voids, including the Botez void, form as a result of cosmic inflation during the early stages of the universe's evolution. As the universe expanded and matter began to gather under the influence of gravity, galaxies and clusters of galaxies formed in long, thread-like structures known as filaments. Meanwhile, regions of space with slightly less matter became increasingly devoid of galaxies, gradually becoming the vast, empty voids we observe today. The process of cosmic evolution explains why the Botez void appears so empty. In the very early universe, small density fluctuations caused areas with more matter to attract even more material due to gravitational pull. This led to the formation of dense regions of galaxies and clusters. Conversely, areas with slightly less matter became more and more sparse, eventually evolving into vast voids. Over billions of years, this process intensified, drawing matter into the filaments while leaving enormous, empty regions in between. The Botez void is one of the extreme examples of this process, where the depletion of matter has reached such an extent that only a few sparse galaxies remain within it. However, despite its immense emptiness, the Botez void is not entirely devoid of galaxies. Researchers estimate that tens of thousands of galaxies may still reside within this void, though the number is surprisingly low for such a vast region. For comparison, a similarly sized volume in a more typical part of the universe would contain millions of galaxies. Studying these massive voids offers astronomers invaluable insights into the mechanics of cosmic evolution and the formation of structures within the universe. By examining how matter, both visible and dark, is distributed within and around these voids, scientists gain important clues about the nature of dark matter and dark energy, two of the most elusive and mysterious components of the universe. The Botez void, with its almost unimaginable emptiness, provides a stark reminder of the vastness of the cosmos. It highlights the intricate dance of matter influenced by fundamental forces like gravity, which continue to shape the universe in ways we are still working to fully understand. It's a profound example of how the universe's larger structure continues to evolve, even in the most desolate corners of space. Interestingly, the void's emptiness isn't the only cosmic mystery that stumps astronomers. There are numerous phenomena that challenge our understanding of the universe, such as stars that seem to disappear from our celestial maps. One possible explanation for this disappearance is a phenomenon known as significant dimming. This occurs when interstellar dust clouds traveling between a star and Earth block a substantial portion of the star's light. These clouds are not permanent, and once they move away, the star reappears, explaining the temporary dimming of stars in the night sky. Another enigma involves what are known as failed supernovae. In these rare instances, a massive star, typically one with a mass at least 18 times that of our Sun, collapses directly into a black hole, bypassing the dramatic explosion that normally accompanies a supernova. When this happens, the star essentially disappears from view because it no longer emits light that can reach Earth. This creates a puzzling scenario where a once bright star vanishes, only to be replaced by the almost undetectable presence of a black hole. These failed supernovae offer new evidence into the mysterious behavior of stars and contribute to our evolving understanding of the cosmic neighborhood. While many of these cosmic puzzles are still being unraveled, some ingenious techniques have allowed us to study distant objects with greater ease. One such method is the gravitational slingshot, or gravity assist, used to propel spacecraft across vast distances with minimal fuel. This technique harnesses the gravitational pull of planets and moons to accelerate and redirect spacecraft. As a spacecraft approaches a planet, it falls into the planet's gravitational field, gaining speed. By carefully maneuvering, the spacecraft can then slingshot around the planet, using the planet's momentum to accelerate to much higher speeds. This method has enabled many space missions to reach distant destinations, making it one of the most efficient tools in modern space exploration. The Botez void, failed supernovae, and the use of gravitational slingshots are just a few examples of the cosmic phenomena that continue to fascinate and perplex astronomers. Each new discovery brings us closer to unraveling the mysteries of the universe, offering new clues about the nature of the cosmos and our place within it. This technique hinges on the principle of orbital mechanics and the conservation of momentum. When a spacecraft passes close to a planet, it effectively steals a small fraction of the planet's orbital energy. The planet itself experiences no noticeable change in velocity due to its immense mass. However, the spacecraft is given a significant speed boost, propelling it toward its destination. This ingenious method has been pivotal in missions to the outer planets, allowing spacecraft to travel vast distances without requiring excessive fuel. The most notable of this is the Voyager probes, which use gravitational slingshots around Jupiter and Saturn to catapult themselves beyond the solar system, achieving speeds far beyond the capabilities of conventional propulsion systems. This interplay of celestial mechanics and human ingenuity enables us to explore distant worlds. It pushes the boundaries of human knowledge, allowing us to venture farther into space than ever before. The same concept can be seen in the operations of the James Webb Space Telescope, which represents an extraordinary leap forward in our ability to explore the cosmos. Set to provide unprecedented images and data, the telescope features a primary mirror spanning over 21 feet in diameter, almost 3 times the size of the Hubble Space Telescope's mirror. But its power doesn't just lie in its sheer size. Equipped with advanced instruments capable of observing infrared light, the Webb telescope allows scientists to peer through cosmic dust clouds that have long obscured our view of distant stars and celestial phenomena. This capacity to observe infrared light is essential because many objects in space emit more light in this wavelength than they do in visible spectra. As a result, JWST provides an unparalleled ability to see objects in space that were previously hidden from our view. Perhaps one of the most groundbreaking aspects of the telescope is its ability to look back in time. By studying light that has traveled billions of years to reach us, JWST allows scientists to study the early universe, unveiling how the first stars and galaxies formed in the aftermath of the Big Bang. But JWST's mission extends beyond understanding the distant past. It is also on the cutting edge of exoplanet research, analyzing the atmospheres of distant worlds and searching for potential biosignatures, chemical indicators of life. The power of JWST lies not only in its remarkable optics and sensing capabilities, but also in its wide-reaching scope of questions. From probing the origins of the universe to exploring the potential for life beyond our solar system, this telescope is poised to tackle some of the deepest mysteries of the cosmos. Space probes, the unsung heroes of space exploration, are marvels of engineering designed to withstand the harsh conditions of deep space. These probes must endure extreme temperature fluctuations, from the blistering heat near the sun to the icy cold of the outer solar system. To protect the delicate instruments aboard, engineers use multi-layered insulation, often made from materials like gold or aluminum foils. In colder regions, probes are also equipped with heaters to maintain operational temperatures. Radiation is another significant challenge. Cosmic rays and solar radiation constantly bombard spacecraft, threatening to damage their sensitive electronics. To combat this, space probes are built with radiation-hardened components and encased in protective shielding. This ensures the longevity of the instruments and allows them to remain functional despite constant exposure to high-energy particles. For instance, the New Horizons probe, which made history by traveling to Pluto and beyond, was designed with robust systems to cope with these harsh space conditions. Energy management is another critical consideration for deep space probes. While solar panels work well in the inner solar system, they become less effective as probes venture farther into space. To maintain power in the outer regions, probes often rely on radioisotope thermoelectric generators, which convert the heat from decaying radioactive material into electricity. This consistent energy supply ensures the probe's instruments can function and communicate with Earth, even from billions of miles away. These systems combine to ensure that space probes can thrive in the most challenging conditions, transmitting vital scientific data from the vastness of space. The Breakthrough Starshot project represents an ambitious step forward in our exploration of space. Its goal is to send tiny, lightweight probes to Alpha Centauri, our nearest star system, located over 4 light-years away. Spearheaded by a team of leading scientists and supported by substantial private funding, the project envisions launching swarms of small, chip-sized spacecraft known as Starchips. These spacecraft would be propelled by ultra-thin, light-powered sails known as light sails. The concept behind this project relies on leveraging powerful ground-based lasers to push these light sails to speeds of up to 20% of the speed of light. By focusing laser beams on the light sails, the energy propels the starships forward, drastically reducing the travel time to Alpha Centauri. Instead of taking tens of thousands of years, the mission could potentially reach its destination in just 20 years. This breakthrough could revolutionize space exploration, allowing humanity to study the stars in ways previously thought impossible. In summary, these remarkable achievements represent the ever-expanding frontier of space exploration. Whether through gravitational slingshots, advanced telescopes, or cutting-edge space probes, humanity continues to push the boundaries of what we can understand about the universe. Each new discovery brings us closer to unraveling the mysteries of deep space and finding answers to some of humanity's oldest questions. In the vast expanse of space, a revolutionary leap in exploration is unfolding. The Breakthrough Starshot project is a bold endeavor aiming to send tiny spacecraft to distant star systems, and the speed they hope to reach is nothing short of astonishing. Conventional spacecraft, despite their minuscule size, would require tens of thousands of years to reach the nearest star systems. However, these star chips are set to achieve speeds that could bring them to other stars in a matter of decades, far faster than any current technology could ever hope to achieve. Equipped with state-of-the-art scientific instruments, including cameras and communication devices, these tiny spacecraft will be capable of capturing and sending back images and data from far-off star systems, potentially providing humanity with our first close-up views of other stars and planets. This extraordinary mission, however, comes with significant challenges. Achieving these remarkable speeds requires precise control of the laser beams used to propel the spacecraft, as well as ensuring that the light sails, which act as the propulsion mechanism, can withstand the harsh environment of space. These sails must endure extreme conditions, including potential collisions with micrometeoroids and the punishing radiation of space over extended periods. But the potential rewards of success are even greater. If the Breakthrough Starshot project reaches its goal, it could change everything about our ability to explore other star systems. It would open up new possibilities for studying planets orbiting distant stars, and could even help us identify potentially habitable worlds far beyond our own solar system. This project symbolizes a giant leap forward in human curiosity, a testament to our relentless drive to explore the unknown and our ever-expanding technological prowess. It moves us ever closer to our ultimate dream of becoming an interstellar species. Space telescopes have already transformed our view of the universe by bypassing some of the critical limitations posed by Earth-based observations. One of the greatest challenges faced by telescopes on Earth is the distortion caused by the planet's atmosphere. Even the clearest skies scatter and absorb some of the incoming light from celestial objects, resulting in blurred images that lack precision. Space telescopes operating above the atmosphere eliminate this issue entirely, providing astronomers with a crystal clear view of the cosmos. Moreover, the Earth's atmosphere blocks certain wavelengths of electromagnetic radiation, including ultraviolet light, X-rays, and most of the infrared spectrum. These wavelengths are crucial for studying many astrophysical phenomena, from the hot, young stars emitting ultraviolet radiation to the cooler, ancient stars and distant galaxies observable only in the infrared. The Hubble Space Telescope has already provided awe-inspiring images in ultraviolet and visible light, and the James Webb Space Telescope, with its infrared capabilities, will offer new insights by peering through cosmic dust clouds. It promises to reveal regions of star formation and even the atmospheres of distant exoplanets. What sets space telescopes apart is their ability to observe the universe continuously, without interruptions from the day-night cycle or adverse weather conditions. This uninterrupted observation is key to tracking dynamic events such as supernovae, the movement of celestial bodies, and changes in the atmospheres of distant planets. By freeing astronomical observations from the limitations of Earth's surface, space telescopes have not only broadened our understanding of the universe, but have also paved the way for groundbreaking discoveries that were once beyond our reach. However, as humanity ventures further into space, new challenges arise, notably in the form of space junk, defunct human-made objects that clutter Earth's orbit. This debris includes spent rocket stages, non-functional satellites, and fragments from past collisions or disintegrations, creating what is essentially a cosmic junkyard. As more missions are launched into space, the accumulation of this debris continues to grow, creating a perilous environment that poses serious risks to operational spacecraft. The most significant threat posed by space junk is the risk of collisions with satellites, operational spacecraft, and even the International Space Station. These fragments, some traveling at velocities up to 177,000 miles per hour, can cause catastrophic damage if they collide with functional equipment. In fact, to avoid such risks, satellites and the ISS must regularly adjust their orbits, adding complexity and increasing the cost of operations. The danger of space debris is far from hypothetical. In 2009, for example, an inactive Russian satellite collided with an active American communications satellite, creating thousands of new debris fragments in the process. One of the most alarming scenarios tied to space junk is the potential onset of the Kessler syndrome, a catastrophic chain reaction where a single collision creates more debris, leading to further collisions in a self-perpetuating cycle. If this occurs, it could render certain orbits uninhabitable, crippling future space missions and threatening the sustainability of satellite operations that are critical for communication, weather forecasting, and navigation. Addressing the growing problem of space junk will require international cooperation and the development of innovative solutions, such as debris removal technologies and better end-of-life disposal strategies for satellites. Without a concerted effort to tackle this issue, humanity's ability to continue exploring and utilizing space could be at serious risk, threatening the very future of our ventures beyond Earth. In the vast expanse of space, a new frontier is being paved by a transformative propulsion technology, ion engines. These engines are a game changer for space exploration, offering distinct advantages over traditional chemical rockets. Unlike conventional propulsion systems, which rely on the violent combustion of fuel to generate thrust, ion engines work by ionizing a propellant, often xenon gas. This ionization process strips electrons from xenon atoms, creating positively charged ions. These ions are then accelerated by powerful electric fields traveling through a series of grids or electrodes, reaching incredible velocities, sometimes exceeding 990,000 miles per hour. The real magic behind ion engines lies in their efficiency, measured by a concept known as specific impulse. Specific impulse refers to how effectively the engine converts propellant into thrust. While the thrust produced by ion engines is comparatively low, about the weight of a sheet of paper, their extraordinary efficiency allows them to operate continuously for long durations. This sustained thrust gradually builds up immense velocity, which is ideal for deep space missions. Unlike traditional rockets that rely on explosive bursts of fuel, ion engines provide steady acceleration, making them perfect for long-distance travel across the vast stretches of space. This sustained, gradual acceleration has been proven in real-world missions. NASA's Dawn spacecraft, for example, successfully used ion propulsion to travel to and orbit both the asteroid Vesta and the dwarf planet Ceres. These missions would have been nearly impossible using traditional propulsion systems due to the massive fuel requirements. With ion engines, NASA was able to embark on a mission that would have otherwise been unfeasible. This pioneering technology has proven invaluable for exploring distant celestial bodies where fuel efficiency is paramount and the distances are vast. As humanity sets its sights on even more distant targets, such as the moons of Jupiter and Saturn, or even interstellar travel, ion propulsion could be the key to unlocking our journey to the furthest reaches of the cosmos. The ability to operate over long periods without the need for massive fuel reserves makes ion engines indispensable for deep space exploration. In addition to ion propulsion, the upcoming Laser Interferometer Space Antenna LISA mission will offer unprecedented insights into the cosmos. LISA is a space-based observatory designed to detect and study gravitational waves, ripples in space-time caused by some of the universe's most violent events, such as black hole mergers or neutron star collisions. This mission marks a groundbreaking step in our understanding of the universe, as it will be the first dedicated space-based gravitational wave observatory. Unlike ground-based detectors like LIGO, which are hindered by seismic noise and atmospheric interference, LISA will have the advantage of operating in the vast emptiness of space. LISA will consist of 3 spacecraft arranged in a triangular formation, trailing behind Earth in its orbit around the Sun. Each spacecraft will be separated by approximately 1.5 million miles, and they will use lasers to make highly precise measurements of the distances between them. When a gravitational wave passes through this formation, it will cause tiny fluctuations in the distance between the spacecraft. By analyzing these fluctuations, scientists will be able to uncover information about the gravitational waves, including their sources and energies. This will provide unprecedented insight into massive cosmic phenomena like supermassive black hole mergers and the inspiral of large compact objects. One of the unique capabilities of LISA is its ability to detect lower frequency gravitational waves, which are out of reach for ground-based observatories. These low-frequency waves are generated by massive cosmic events, like the merging of supermassive black holes at the centers of galaxies. By probing these waves, LISA promises to enhance our understanding of the most energetic processes in the universe and provide new insights into the very fabric of space-time. Meanwhile, in our own solar system, space weather continues to have a profound impact on both technology and human activity, both on Earth and in space. Solar flares, coronal mass ejections, and geomagnetic storms are all manifestations of space weather, releasing vast amounts of energy and charged particles into space. When these particles interact with Earth's magnetosphere, they can cause significant disruptions. Satellites, for example, are particularly vulnerable. High-energy particles can damage their sensitive electronics, degrade solar panels, and interfere with communication and navigation systems. Even geomagnetic storms can alter the orbits of satellites, forcing them to adjust to maintain proper positioning. The impact of space weather is not limited to space-based technology. On Earth, these events can disrupt GPS systems, which are crucial for everything from navigation in aviation and maritime sectors to military operations. Intense solar storms can degrade GPS signal accuracy or even cause temporary outages. In addition, geomagnetic storms can induce electrical currents in power lines, potentially leading to voltage instability and damaging infrastructure. As our dependence on space-based technology grows, understanding and mitigating the effects of space weather will become increasingly important. In conclusion, ion propulsion, gravitational wave observatories like LISA, and an awareness of space weather's effects are all pushing the boundaries of human exploration and understanding of the universe. These advancements in space technology are not just shaping the future of space missions, but also offering deeper insights into the mysteries of the cosmos and the delicate balance of our planet's technological systems. In the vast, unexplored domain of space, phenomena far beyond our comprehension can disrupt the very technologies that govern our daily lives. One such event that has captured global attention occurred in 1989 when a massive geomagnetic storm triggered by solar activity caused a monumental blackout in Quebec. Millions of people were left without power, and the event revealed just how vulnerable we are to the forces of space weather. These geomagnetic storms can also interfere with high-frequency radio communications, which are vital for aviation and military operations. As the ionosphere, which reflects radio waves, fluctuates under the influence of solar storms, these essential communications can suddenly vanish, affecting everything from air traffic control to emergency services. With our increasing reliance on technology, understanding and preparing for space weather has never been more important. Systems like the Space Weather Prediction Center now monitor these cosmic events, offering invaluable early warnings to protect our electrical grids, satellite networks, and communication systems. The challenge is that as our dependence on these technological assets grows, so does the need for more robust infrastructure to withstand the effects of space-based phenomena. In this context, the development of new monitoring technologies and improved resilience planning could be the key to securing that we are less susceptible to the unpredictable forces of space. One of the most exciting ideas on the horizon is the concept of a space elevator. Imagine a massive, continuous structure stretching from the Earth's surface all the way to geostationary orbit, approximately 22,000 miles above the equator. This elevator would be tethered to the ground and anchored by a counterweight beyond geostationary orbit, maintaining a stable and balanced system. This extraordinary engineering feat would revolutionize our ability to access space without relying on traditional rocket propulsion, fundamentally altering the cost and logistics of reaching orbit. At the core of this concept is the elevator's tether, which would need to be made from materials that are not only incredibly strong but also lightweight to support the immense forces at play. The best candidates for this task are materials like carbon nanotubes and graphene, which possess unparalleled tensile strength and low density. The idea is that specialized vehicles, powered by electric or laser energy, could travel up and down this tether, carrying cargo and passengers as effortlessly as an elevator ride. By drastically reducing the cost and complexity of launching payloads, a space elevator could open the door to a future where space exploration is accessible and affordable. Not only would a space elevator make reaching orbit more efficient, but it could also be a game changer for industries like satellite deployment, space tourism, and even the construction of habitats in space. The elevator could provide a steady stream of resources from extraterrestrial bodies like asteroids or the moon, supporting the development of off-Earth economies. The challenges remain significant, with technical and engineering hurdles to overcome. However, if successfully developed, a space elevator could be the key to a sustainable future in space exploration, making humanity's reach beyond Earth more permanent and accessible. On a different front, the study of extremophiles, organisms that thrive in Earth's most hostile environments, has reshaped our understanding of life itself. These extraordinary creatures survive in places once thought uninhabitable, from the boiling waters of hydrothermal vents to the frigid ice caps of the Arctic and Antarctic. Extremophiles such as thermophiles, halophiles, and acidophiles have evolved unique biochemical processes that allow them to endure extreme conditions. Whether it's intense heat, high salinity, or acidic environments. The discovery of extremophiles has profound implications for the search for life beyond Earth. Traditionally, scientists believed life could only exist within a narrow habitable zone around a star, where liquid water could be found. But the existence of extremophiles has expanded this view, suggesting that life could thrive in far harsher environments than previously imagined. This insight has led researchers to look at moons like Europa and Enceladus, where subsurface oceans could harbor life sustained by geothermal energy, offering exciting possibilities for extraterrestrial life forms. Mars, too, with its history of liquid water and seasonal methane emissions, continues to be a prime candidate for the discovery of extremophile-like organisms. Understanding how extremophiles survive in extreme conditions also guides the development of scientific tools for future space missions. By learning how these organisms thrive, scientists can create instruments that are specifically designed to detect biosignatures, chemical markers that indicate the presence of life. As our search for extraterrestrial life progresses, the study of extremophiles challenges our preconceived notions about where life could exist. It is no longer a matter of just searching for water, but for any environment where life could adapt and evolve. Whether it's on distant exoplanets or within the icy depths of a moon, extremophiles are helping to redefine the boundaries of life's possibilities in the universe. And as we expand the range of environments we explore, we open up new pathways for finding life beyond our planet. The search for biosignatures on exoplanets, too, is more crucial than ever. Scientists are now looking for the specific chemical signatures that could indicate the presence of life, whether it's a planet's atmosphere, its surface conditions, or signs of life processes. As our technology improves and our understanding of life expands, the next giant leap in the search for life beyond Earth could very well be closer than we think. In the search for life beyond Earth, scientists employ a combination of advanced telescopic observations, spectroscopic analysis, and sophisticated theoretical modeling. Together, these techniques allow researchers to study the markers that could indicate the presence of life on distant worlds. One of the primary methods in this quest involves analyzing the light passing through the atmospheres of exoplanets as they transit across their host stars. This technique, known as transit spectroscopy, enables scientists to detect the chemical makeup of an exoplanet's atmosphere. By studying the absorption lines in the light spectrum, researchers can pinpoint key gases like oxygen, ozone, methane, and nitrous oxide. On Earth, these gases are predominantly produced by biological processes, making their presence on another planet an exciting possibility for the existence of life. Oxygen and ozone, for instance, are byproducts of photosynthesis, a biological process central to life on Earth. Methane, on the other hand, can be generated through both biological and geological means. However, the presence of certain gases, especially those that would not remain stable without continuous replenishment, could signal the ongoing activity of biological processes. Detecting such imbalances in a distant planet's atmosphere would be a significant step forward in the search for life. Additionally, scientists are exploring another promising approach known as direct imaging. Through advanced telescopes equipped with high-contrast imaging technology, astronomers aim to capture direct visuals of exoplanets. Instruments like the James Webb Space Telescope, which is set to observe exoplanets in unprecedented detail, will utilize coronagraphs and star shades to block out the overwhelming light from their parent stars, allowing them to capture the faint light from the exoplanets. By studying this light, scientists can gather critical data on an exoplanet's surface conditions and atmospheric composition, further enhancing the search for potential biosignatures. Beyond just atmospheric gases, researchers are also investigating other possible biosignatures. Unusual surface reflectance spectra might hint at vegetation or microbial life forms, while temporal changes in an exoplanet's atmospheric composition could suggest seasonal biological activities. By combining these methods and employing cutting-edge technologies, scientists are refining their ability to detect and interpret biosignatures, inching ever closer to answering one of humanity's most profound questions: are we alone in the universe? Meanwhile, astrobiologists have turned their attention to the potential for life in the subsurface oceans of icy moons. Moons like Jupiter's Europa and Saturn's Enceladus have emerged as prime candidates in this pursuit, as they harbor vast oceans beneath thick, icy crusts. These subsurface oceans remain in a liquid state due to tidal heating, caused by the gravitational forces of their parent planets, which generates internal friction and prevents the water from freezing solid. Europa, for example, is covered in a thick layer of ice beneath which lies an ocean that could contain twice the amount of water found in all of Earth's oceans combined. The interaction between this ocean and the moon's rocky mantle could provide the chemical energy needed to sustain life. Hydrothermal vents on the ocean floor, similar to those found in Earth's deep oceans, could offer the perfect conditions for life to thrive. These vents release heat, minerals, and chemical energy, creating a rich ecosystem. Enceladus 2 has piqued the interest of scientists. The Cassini spacecraft revealed plumes of water vapor and organic compounds erupting from fissures in the moon's icy surface, suggesting the presence of a subsurface ocean. These plumes contain not just water, but also salts and organic molecules, vital ingredients for life. The ability to detect these compounds directly from space makes Enceladus an especially accessible target for future missions looking for signs of life. To explore these moons, scientists are considering a variety of mission concepts. Probes could be sent to sample the plumes of Enceladus, analyzing the ejected materials for biosignatures. For Europa, landers equipped with instruments designed to penetrate the thick ice and probe the underlying ocean could be deployed. Studying these moons and the potential habitability of their subsurface oceans will give scientists insights into the possibility of life in these extreme and alien environments. Such research could also help humanity understand the resilience and adaptability of life across the cosmos. However, exploring potentially habitable worlds is not without its challenges. One of the most important considerations is planetary protection. Preventing contamination is crucial in ensuring that Earth-originating microbes do not interfere with extraterrestrial ecosystems and vice versa. Strict international protocols are in place to prevent both forward and backward contamination. Forward contamination refers to the risk of Earth life being transported to other celestial bodies, while backward contamination involves extraterrestrial materials being introduced to Earth. The Committee on Space Research, COSPAR, sets planetary protection standards, and space agencies around the world follow these guidelines meticulously. A key strategy in preventing contamination is sterilizing spacecraft and instruments before launch. This can be done through techniques like heat sterilization, where components are exposed to high temperatures, or chemical sterilization using powerful disinfectants. By adhering to these rigorous protocols, scientists aim to explore other worlds without risking contamination from Earth's life forms. In the realm of space exploration, the preservation of celestial ecosystems and the integrity of Earth's microbial life is paramount. To ensure these efforts, spacecraft that venture to potentially habitable environments such as Mars, Europa, or Enceladus are constructed in ultra-clean facilities known as clean rooms, where contamination risks are minimized. In these highly controlled environments, engineers wear full-body suits to prevent shedding skin cells or any other contaminants that could interfere with delicate biological investigations. These strict protocols are essential for missions targeting locations where life could possibly thrive, even if only in microscopic forms. For instance, the Curiosity rover, which embarked on its mission to Mars, underwent rigorous sterilization procedures to avoid contaminating the planet with earthly microbes. The rover's design also incorporated redundancy in its scientific instruments, allowing for continuous operation even if sterilization efforts impacted the primary equipment. Missions to celestial bodies like Europa or Enceladus are expected to follow similar, if not more advanced, sterilization practices, given the increased likelihood of encountering environments conducive to life. Additionally, spacecraft that cannot be fully sterilized are intentionally directed away from these worlds to prevent any unintended contamination. This concept was notably demonstrated by NASA's Galileo spacecraft, which was deliberately crashed into Jupiter after its mission to ensure its moons, especially Europa, remained uncontaminated. For future sample return missions, containment and quarantine procedures will become even more critical. Any samples returned from space will be handled in high-security biosafety level facilities, akin to those used for the containment of hazardous pathogens. This level of precaution ensures that potential extraterrestrial life forms, or any unintentional biological material, are thoroughly studied in a controlled and safe environment, without posing any risk to Earth's ecosystems. By meticulously implementing these measures, scientists and engineers strive to protect the delicate balance of life on Earth while maintaining the scientific purity of extraterrestrial exploration. Planetary protection plays an essential role not only in maintaining the integrity of scientific discoveries, but also in preserving the potential for finding untainted extraterrestrial life. This meticulous approach underpins every mission as we continue our search for answers about life beyond our planet. A standout example of this advanced exploration is the Dragonfly mission, a groundbreaking NASA project designed to explore Titan, Saturn's largest moon. Titan, known for its thick nitrogen-rich atmosphere and liquid methane lakes, presents an exciting opportunity to understand the chemical processes that could have mirrored Earth's prebiotic conditions. Dragonfly's unique approach involves deploying a rotorcraft with 8 rotors designed to fly through Titan's dense atmosphere, enabling it to cover vast distances far more effectively than traditional rovers. The rotorcraft will hop between locations, with each hop covering up to 5 meters, amassing over 100 miles of exploration during its mission. The primary objective of Dragonfly is to investigate Titan's complex chemistry, with a specific focus on searching for prebiotic chemical processes. Equipped with cutting-edge instruments, Dragonfly will analyze the moon's surface and atmosphere for organic molecules and potential biological markers. Special attention will be given to Titan's dune fields and icy crust, where interactions between organic compounds and water could form fascinating chemical reactions. Through this exploration, scientists hope to uncover the essential chemical ingredients that might support the emergence of life, offering crucial insight into the conditions that make a celestial body habitable. Another fascinating tool in the hunt for extraterrestrial life is spectroscopy. This technique involves studying the light emitted, absorbed, or reflected by distant planets to decipher their chemical composition. Each element or molecule produces a unique spectral signature, much like a fingerprint. By analyzing the light from these celestial bodies, scientists can detect gases in a planet's atmosphere that may indicate biological processes. For example, the presence of oxygen in significant quantities might suggest photosynthetic life, while methane could indicate biological activity, particularly if found alongside other gases like carbon dioxide. The James Webb Space Telescope and the European Extremely Large Telescope are among the advanced instruments used to collect and analyze light from exoplanets, creating detailed spectra of distant worlds. By studying these spectra, scientists can learn about the composition of exoplanetary atmospheres and surfaces, providing vital clues about a planet's habitability and potential for supporting life. As we continue to push the boundaries of space exploration, these advanced methods of detection offer hope that we may one day uncover evidence of life beyond Earth in its purest and most unaltered form. In recent years, phosphine has sparked a wave of scientific intrigue as a potential sign of life on Venus. This gas, which on Earth is mainly produced by anaerobic microorganisms thriving in oxygen-free environments, such as in swamps, wetlands, and the digestive tracts of certain animals, has caught the attention of researchers seeking evidence of extraterrestrial life. Given the harsh and acidic conditions of Venus, the discovery of phosphine in its atmosphere in 2020 was nothing short of revolutionary. The presence of this gas, detected in the planet's clouds at altitudes where temperatures and pressures are somewhat more forgiving, has opened up exciting new possibilities. The discovery was made through advanced spectroscopic techniques, which revealed unmistakable signs of phosphine gas. But what makes this finding even more remarkable is that Venus's surface conditions are incredibly hostile, characterized by scorching temperatures and crushing pressures. Despite this, the cloud layers at higher altitudes offer a less extreme environment, which has made them a focal point in the search for potential habitability. The most intriguing aspect of this discovery is that known non-biological processes, such as volcanic activity or lightning, cannot easily account for the high levels of phosphine found. If further investigations confirm the presence of phosphine and exclude non-biological origins, the theory that microbial life may exist in the Venusian clouds becomes a plausible hypothesis. As scientists continue to explore this possibility, missions like Veritas and Da Vinci Plus are being proposed to gather more data on Venus's atmosphere and surface. These future missions could either provide evidence that supports the idea of microbial life floating in the clouds of Venus, or challenge the notion altogether. In any case, the discovery of phosphine on Venus opens up fascinating new avenues for the study of life beyond Earth. However, Venus is just one example of how life could thrive in extraordinary environments across the universe. While life on Earth has adapted to a wide range of extreme conditions, the potential for life to evolve in radically different environments elsewhere in the cosmos broadens our understanding of what makes a planet habitable. For instance, extremophiles, organisms that can survive in the most inhospitable environments on Earth, serve as a key reference point for scientists considering the possibility of life in other parts of the universe. These hardy organisms, capable of enduring extreme temperatures, radiation, or chemical imbalances, provide insight into how life could survive under completely alien conditions. One such scenario involves the possibility of life evolving on a planet with oceans of methane and ethane, much like those on Saturn's moon Titan. In this environment, life would need to be based on a biochemistry entirely different from what we know on Earth, possibly using methane as a solvent instead of water. This life would have to endure freezing temperatures around 94 Kelvin while utilizing chemical reactions unique to a hydrocarbon-rich environment. Another intriguing possibility involves life on a planet or moon exposed to high radiation or acidic oceans. In such environments, organisms could have evolved with radiation-resistant biochemistry or developed cellular mechanisms that neutralize or repair damage caused by high radiation exposure. On moons like Jupiter's Europa or Saturn's Enceladus, where extreme pressure and thick layers of ice protect subsurface oceans, life may exist in a completely different form. Here, energy sources like hydrothermal vents, similar to those in Earth's deep oceans, could support ecosystems based not on sunlight, but on chemical energy. Endolithic organisms, which live inside rocks on Earth and extract energy from the chemicals present, offer a model for how life could potentially exist in the frozen or rocky environments of these moons. While the true nature of alien life remains speculative, the astonishing diversity of life on Earth provides ample reason for scientists to consider the potential for life in radically different conditions across the cosmos. The discovery of organic molecules on planets like Mars only adds to the growing body of evidence that the building blocks of life may be more widespread in the universe than previously believed. Organic molecules, composed primarily of carbon, hydrogen, oxygen, and other elements, are the foundational components of life as we know it. Their presence on Mars, particularly in samples collected by NASA's Curiosity rover, strongly suggests that the planet once had the chemical conditions necessary for life to emerge. Mars's geological history, marked by ancient riverbeds, lakes, and possibly vast oceans, further enhances the significance of this discovery. The detection of organic molecules offers a tantalizing hint that Mars may have supported microbial life in the past and that traces of this life could still be preserved in the Martian subsurface. These findings not only broaden our understanding of the conditions required for life, but also fuel the ongoing quest to answer one of humanity's most profound questions: are we alone in the universe? In the mysterious expanse of our solar system, moons like Saturn's Enceladus and Jupiter's Europa stand as testaments to the compelling potential for life beyond Earth. Both of these icy moons harbor subsurface oceans beneath their frozen surfaces, a discovery that ignites a fascinating conversation about the possibility of extraterrestrial life. Plumes of water that shoot from Enceladus, carrying with them complex organic molecules, are a striking indication of the active chemistry occurring beneath its icy crust. This suggests that these subsurface oceans could offer the right conditions for life, sustained by the heat and energy provided by hydrothermal activity and the rich chemical interactions that emerge from the planet's interior. These revelations are not just scientific curiosity, they represent a paradigm shift in how we think about life's potential across the cosmos. The detection of organic molecules on these distant celestial bodies opens up the tantalizing possibility that the very building blocks of life could be scattered across the solar system, or even beyond. As we expand our search for life, it becomes increasingly likely that life might exist in forms and environments entirely different from what we've previously imagined. This realization suggests that we may not be alone in the universe, and that life, in some shape or form, could arise in many unexpected places. In the field of astrobiology, the question of what defines life itself is complex and evolving. Life is generally understood to involve a combination of biological, chemical, and physical criteria. criteria that must be flexible enough to encompass potential forms of life that differ from Earth's standards. One commonly accepted definition of life centers around several fundamental characteristics: growth, reproduction, metabolism, and responsiveness to stimuli. Living organisms also possess the ability to evolve through natural selection, a driving force behind the diversity and adaptation we see in life on Earth. At its core, life as we know it relies on a set of essential components. It is carbon-based, utilizing carbon's unique ability to form stable and complex molecules, amino acids, proteins, and nucleic acids that are crucial for cellular structures and metabolic processes. These molecules serve as the very foundation for genetic information storage, transmission, and cellular function. Metabolism, a complex series of chemical reactions, transforms energy in ways that support growth and reproduction. The genetic code, typically found in DNA or RNA, ensures precise replication of organisms and the inheritance of traits, facilitating evolution. However, astrobiologists are also considering life forms that may not conform to these terrestrial patterns. Scientists are exploring the possibility of life forms based on alternative biochemistries. For example, silicon-based life forms or organisms that rely on solvents other than water, like liquid methane on Saturn's moon Titan, are theoretical possibilities that stretch the boundaries of our current understanding. To embrace the potential for life forms, astrobiology must adopt a broader, more inclusive approach. It looks at the four primary elements: hydrogen, oxygen, nitrogen, and carbon, that are efficient in forming life's known biochemistry, but remains open to the possibility of life based on other complex chemistries. In practice, the search for life involves identifying biosignatures, specific organic molecules, unusual atmospheric gases, or structures that could indicate biological activity. This inclusive, adaptable definition of life reflects our expanding understanding of the possibilities for life, fueled by ongoing discoveries and technological advancements in both our solar system and distant exoplanets. To understand the broader context of life's origins, one must also consider the history of the universe itself. The cosmic dark age, a period that began roughly 380,000 years after the Big Bang, represents a time when the universe existed in a state of profound darkness and simplicity. During this epoch, the universe had cooled enough for electrons and protons to combine and form neutral hydrogen atoms, rendering the cosmic plasma opaque. The universe was essentially dark. There were no stars, no galaxies, only the dim afterglow of the Big Bang's radiation stretched into the microwave part of the spectrum. This era of darkness ended with a transformative event known as the Epoch of Reionization. This critical phase began around 150 to 800 million years after the Big Bang, when the first stars and galaxies started to form. These early stars, often called population 3 stars, were massive, hot, and emitted intense ultraviolet radiation. This radiation was powerful enough to ionize the surrounding neutral hydrogen, breaking apart hydrogen atoms and turning space from an opaque medium back into a transparent one. As more stars and galaxies formed, their light continued to ionize the universe, eventually allowing for the formation of the cosmos as we know it. Today, we observe the remnants of this transformative period through the study of the cosmic microwave background radiation and distant quasars. The fluctuations in the cosmic wave background offer clues about the conditions of the early universe, while the absorption spectra from distant quasars give us a glimpse into the ionization state of the intergalactic gas at different points in time. As we continue to explore the depths of space and the potential for life beyond Earth, our understanding of life's origins and the universe's evolution will undoubtedly deepen. We are on the brink of unlocking the secrets of the cosmos, and who knows? We may soon find that we are not alone in the vast expanse of the universe. By analyzing vast amounts of data, scientists are gradually constructing a timeline that reveals the transition of the universe from the dark age to the vibrant, light-filled cosmos we observe today. At the heart of this transformation lies the epoch of reionization, which marks the emergence of the first galaxies and stars. This luminous activity began to light up the cosmos, paving the way for the rich and complex cosmic tapestry that would continue to evolve. The study of the very early universe often revolves around the cosmic microwave background, CMB, the faint afterglow of the Big Bang that provides a snapshot of the universe when it was just 380,000 years old. This relic radiation permeates the cosmos and carries crucial information about the conditions of the early universe. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB forms a nearly uniform background, but with subtle temperature fluctuations. These fluctuations hold the key to understanding the universe's birth and its subsequent evolution. Advanced space telescopes such as the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have played an instrumental role in measuring the CMB with remarkable precision. These measurements have proved invaluable for cosmologists, providing them with several critical insights. One of the most significant pieces of information lies in the tiny temperature fluctuations, known as anisotropies. These reflect the density variations in the early universe, and over time, these variations grew under the influence of gravity, ultimately giving rise to the large-scale structures we see today, such as galaxies and galaxy clusters. By studying these anisotropies, scientists are able to infer the initial conditions that contributed to the formation of such structures. Furthermore, the CMB offers an extraordinary wealth of data about the universe's composition, shedding light on the proportions of dark matter, dark energy, and ordinary matter. The pattern of anisotropies within the CMB provides crucial parameters, such as the universe's rate of expansion, its geometry, and its age. For example, the angular size of the observed anisotropies is dependent on the universe's curvature, making the CMB a powerful tool for testing cosmological models. Another fascinating aspect of the CMB is its polarization, which contains vital clues about the universe's state just after the Big Bang and the subsequent inflationary period. The polarization patterns, especially the so-called B modes, may offer evidence of gravitational waves generated during inflation. By examining these different features, cosmologists are piecing together a coherent picture of the early universe's composition, its dynamic evolution, and the fundamental questions surrounding the origin and fate of the cosmos. One of the most intriguing concepts in modern cosmology is the theory of cosmic inflation, which proposes a period of rapid expansion that occurred immediately after the Big Bang. This expansion took place within an incredibly brief fraction of a second, about 10 to the power of negative 36 to 10 to the power of negative 32 seconds following the Big Bang. Introduced by physicist Alan Guth in the early 1980s, this theory addresses several significant issues in cosmology, such as the apparent uniformity of the universe and the absence of large-scale irregularities. During the inflationary period, the universe expanded exponentially, growing by a factor of at least 10 to the power of 26 in less time than it takes light to cross a proton. This dramatic expansion smoothed out any initial irregularities, stretching microscopic quantum fluctuations to macroscopic scales. As a result, regions of the universe that were once causally connected, able to exchange energy and matter, became spread far apart, leading to the highly homogeneous and isotropic universe we observe on large scales today. The theory of cosmic inflation also provides an explanation for the uniformity of the cosmic microwave background radiation across the sky. Without inflation, regions of the universe separated by even a few degrees in the sky would not have been able to communicate or equilibrate their temperatures, given the finite speed of light and the finite age of the universe. Yet observations show that the temperature of the CMB is almost identical in all directions, with only minor fluctuations. Inflation resolves this paradox by suggesting that these once-connected regions were pushed beyond each other's horizons during the brief inflationary epoch. Moreover, cosmic inflation lays the groundwork for understanding the formation of large-scale structures like galaxies and galaxy clusters. The tiny quantum fluctuations that existed before inflation were magnified to scales that are still observable today, helping to shape the intricate web of matter and energy that makes up our universe. In sum, by studying the cosmic microwave background and the theory of cosmic inflation, scientists are uncovering the deepest secrets of the universe's origins and evolution. These efforts provide a fascinating glimpse into the universe's earliest moments and offer profound insights into the very nature of space, time, and existence itself. These fluctuations in the early universe sparked the gravitational collapse that ultimately led to the formation of the intricate and complex structures we observe throughout the cosmos today. Cosmic inflation offers a powerful framework for understanding the uniformity of the universe, the nature of primordial density perturbations, and the large-scale structure formation. It is supported by a wealth of observational evidence and continually refined by ongoing research in cosmology. The formation of the first stars and galaxies, a period known as cosmic dawn, represents a monumental chapter in the universe's history. This transformative process began toward the end of the cosmic dark age, several 100 million years after the Big Bang, when density fluctuations born from quantum perturbations were amplified through gravitational collapse. These primordial fluctuations acted as seeds from which the first stars and galaxies would emerge. As the universe expanded and cooled, neutral hydrogen gas began to clump together in increasingly dense regions. These regions were governed by gravity, with the gas undergoing cooling primarily through radiation emission. This cooling allowed the gas to contract, setting the stage for star formation. The gas clumps, often referred to as dark matter halos due to their dark matter dominance, eventually became suitable for the birth of the first stars. Once these gas clouds reached sufficient density and cooling, they fragmented into smaller pockets, each collapsing further under its own gravity. The first stars, known as population 3 stars, were vastly different from the stars we see today. Composed mostly of hydrogen and helium, these stars lacked heavier elements, also known as metals, which are typically synthesized in stellar cores and scattered across the universe by supernova explosions. Due to the absence of cooling agents, population 3 stars were large, hot, and short-lived, with masses tens to hundreds of times greater than our Sun. These massive stars emitted intense ultraviolet radiation capable of ionizing the surrounding hydrogen gas. This marked the beginning of the reionization process, which ultimately allowed the universe to become transparent to light. After their brief lifespans, these stars exploded as supernovae, dispersing heavier elements into the surrounding space. This enrichment set the stage for subsequent generations of stars, such as population 2 and population Fun stars, which formed under cooler and more varied conditions. These later stars played a crucial role in the creation of rocky planets and more intricate celestial structures. The first stars also released powerful ultraviolet radiation and stellar winds that shaped their surroundings, influencing the formation of the earliest galaxies. These galaxies began as small, proto-galactic fragments that merged over time to form the more complex and larger galaxies we observe today. The hierarchical assembly of these galaxies saw smaller galaxies collide, merge, and evolve through processes such as star formation, supernova feedback, and the accretion of intergalactic gas. These interactions guided their evolution and growth, resulting in the stunning galaxies we observe in the universe. Observations from telescopes like the Hubble Space Telescope have provided glimpses into these early galaxies, allowing astronomers to study their features and gain a deeper understanding of this critical cosmic era. This period marked the transition of the universe from darkness into a realm filled with light and structured beauty. Galaxy mergers have played a critical role in this evolution, significantly shaping galaxy formation, growth, and the overall structure of the universe. Mergers between galaxies, a natural consequence of the gravitational forces they exert on each other, are especially common in densely populated regions such as galaxy clusters. Over time, galaxies often collide and merge, driving substantial changes in their morphology, star formation rates, and galactic dynamics. During these mergers, the gravitational interactions between colliding galaxies can trigger bursts of star formation, known as starbursts, as their gas clouds collide and compress. This provides fertile conditions for the rapid creation of young, bright stars. Such intense star-forming activity can dramatically alter a galaxy's luminosity and spectral characteristics, making it detectable across a wide range of wavelengths, from visible to infrared. In particular, infrared light is often enhanced due to the dust heated by the newly formed stars. Moreover, galaxy mergers play a pivotal role in the formation of different types of galaxies seen today. When two spiral galaxies collide, for example, they may merge into an elliptical galaxy, which is characterized by a more diffuse and less structured appearance. Throughout the merger process, the interplay of stars, gas, and dark matter reshapes the galactic structure, turning spiral arms into a smoother, more spheroidal form typical of elliptical galaxies. These interactions also have profound implications for the central supermassive black holes found in many large galaxies. During a merger, the black holes from the colliding galaxies may eventually coalesce, growing in mass and exerting significant influence over the dynamics and evolution of the resulting galaxy. The inflow of gas toward the center of the merged galaxy can fuel these black holes, triggering active galactic nuclei, AGN, phenomena. These AGNs release vast amounts of energy and radiation, further impacting star formation and the interstellar medium over extended periods. Through these dramatic events, the universe continues to evolve and reveal the intricate processes that shape the cosmos we observe today. Galaxy mergers have long been considered a pivotal force in shaping the universe's structure. These cosmic collisions, often violent and chaotic, are not mere accidents. They are foundational processes that lead to the gradual formation of larger galaxies. With each merger, smaller galaxies combine their mass, energy, and content, feeding into the growth of massive clusters. Over time, this ongoing accretion directly influences the large-scale cosmic architecture we observe today. In fact, the universe's vast variety of galaxies and their evolving shapes are the direct result of these persistent mergers. Instruments like the Hubble Space Telescope, coupled with sophisticated simulations of cosmic structure formation, reveal a crucial truth: the intricate tapestry of galaxies, ranging from sprawling spirals to enigmatic ellipticals, was shaped by these mergers. These ongoing processes, often invisible to the naked eye, play a key role in the grand narrative of cosmic evolution. The merging of galaxies is, therefore, a linchpin in our understanding of how the universe evolved from the earliest post-Big Bang era to its present state. As galaxies collide and merge, they give rise to fundamental changes across many scales. The transformations that take place during these cosmic events are not limited to the galaxies themselves. Star formation surges, triggering bursts of new stars and reshaping galactic structures. Simultaneously, the growth of supermassive black holes accelerates as a direct consequence of these mergers. Understanding these cosmic events is essential for unlocking the mysteries of the universe's grand design, as each merger brings with it a unique set of physical and chemical consequences that influence everything from star birth to the growth of black holes. The cosmic star formation history is an essential framework for understanding these events. It tracks the rate at which new stars have been born, revealing the dynamic, ever-changing nature of the universe's evolution. During the earliest stages of cosmic history, the star formation rate was relatively low. This period, known as the Cosmic Dark Ages, was a time of near total darkness in the universe. There were no bright stars, no galaxies shining in the sky. It was only after a few 100 million years that the first stars, called population 3 stars, began to emerge, and with them the birth of new light in an otherwise dark universe. These early stars were large, massive, and composed primarily of hydrogen and helium. Their formation marked the beginning of a new chapter in the universe's evolution. The enormous heat and energy produced by these stars ignited the formation of new generations of stars, enriching the interstellar medium with heavier elements. These elements, such as carbon and oxygen, served as the building blocks for future stars and planets. This process laid the groundwork for the star formation rates to rise dramatically, eventually reaching a peak during the epoch known as cosmic noon, roughly 1.5 to 3 billion years after the Big Bang. During this peak, star formation was at its most vigorous, with galaxies across the universe bursting with new stars. Observations from advanced telescopes like Hubble show a large number of high redshift galaxies from this period, which emit intense ultraviolet and infrared light. This emission is a direct indication of the immense star-forming activity taking place within these galaxies. This period of intense star formation was driven by abundant cold gas in galaxies, mergers between galaxies that triggered starbursts, and other favorable conditions for stellar birth. However, after this period of intense star formation, the rate of star birth began to gradually decline. This decrease wasn't due to any single factor, but rather a combination of interconnected processes. Over time, galaxies depleted their interstellar gas reserves, which are the raw material necessary for star formation. In addition, feedback from active galactic nuclei and supernovae expelled gas from galaxies, making it difficult for new stars to form. The expansion of the universe also played a role by spreading galaxies apart, decreasing the frequency of mergers and interactions that might otherwise have reignited star formation. Today, the universe is entering a relatively quieter phase. Star formation still takes place, but at a much slower pace than in the past. Galaxies like our own Milky Way continue to form new stars, but these events are less frequent. The stellar populations within these galaxies are aging, and the dramatic transformations witnessed in the early universe are now rare. The dynamics of galaxies have shifted from explosive growth to a more subdued evolution. The cosmic star formation history, when viewed as a whole, provides us with a remarkable narrative, a roadmap of the universe's dynamic and ever-changing nature. It helps us understand not only the formation and evolution of galaxies, but also the complex interactions between the physical processes that govern the cosmos. By studying this history, astronomers gain valuable insights into the intricate web of events that shaped our universe, from its earliest days to the present day, and continue to influence its future. According to current cosmological models, the fate of the universe is predominantly shaped by its rate of expansion, driven by dark energy and influenced by the amount of both dark and ordinary matter it contains. This expansion plays a pivotal role in determining what will ultimately happen to the cosmos. Current observations suggest that the universe will continue expanding indefinitely, eventually leading to a scenario known as the Big Freeze, or heat death. In this model, dark energy, identified through the accelerated expansion of the universe, is central to the universe's long-term fate. Discovered in the late 1990s through observations of distant supernovae, dark energy is estimated to make up about 70% of the universe's total energy density. This mysterious force acts in opposition to gravity, driving the universe's expansion to accelerate over time. As galaxies recede from each other, the density of both ordinary matter and dark matter decreases, leaving dark energy to dominate the universe's evolution. The Big Freeze scenario unfolds as the universe stretches out endlessly, and galaxies drift farther apart. Eventually, galaxies will move beyond each other's observable horizons due to this accelerated expansion. Over immense periods, star formation will halt as galaxies run out of the necessary gas to create new stars. Existing stars will age and die, leaving behind remnants such as white dwarfs, neutron stars, and black holes. These remnants will gradually cool and fade, leading to a cold, dark, and diffuse universe. One key aspect of the Big Freeze is entropy. As the universe reaches a state of maximum entropy, energy distribution becomes increasingly uniform, leaving fewer gradients to drive processes that increase complexity. This results in a universe where all physical processes, including those that might support life, slowly grind to a halt. The overall outcome is a universe devoid of the energy needed for any meaningful activity. However, an alternative scenario, though less likely, depends on the behavior of dark energy. If the energy density of dark energy increases over time, it could lead to the so-called Big Rip, a catastrophic event where the universe's accelerated expansion tears apart galaxies, stars, planets, and even atomic particles. But current evidence does not support this outcome, making the Big Rip a more remote possibility. Another theory, the Big Crunch, suggests that the universe might eventually reverse its expansion, collapsing back into a highly dense state. This hypothesis was more plausible before the discovery of the accelerating expansion of the universe. However, with the dominance of dark energy becoming more apparent, the Big Crunch is now considered unlikely. The ultimate fate of the universe hinges on the precise properties of dark energy, which remain one of the biggest mysteries in modern cosmology. As our understanding of dark energy evolves, through new observations and theoretical breakthroughs, our predictions about the universe's end will become more refined. For now, the Big Freeze is the most widely accepted scenario among scientists. To understand the age of the universe, astronomers employ several complementary methods. The most robust estimates are derived from observations of the cosmic microwave background, CMB, the expansion rate of the universe, and the ages of the oldest star clusters. Together, these methods offer a consistent picture of a universe that is approximately 13.8 billion years old. The most precise measurements come from studying the CMB, the remnant radiation from the Big Bang. Space observatories like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have mapped the CMB with incredible precision. The CMB provides a snapshot of the universe when it was just 380,000 years old, encoding vital information about its early conditions. By analyzing the temperature fluctuations and the polarization of the CMB, scientists can infer key cosmological parameters such as the expansion rate, Hubble constant, the density of matter and dark energy, and the overall geometry of the universe. These parameters feed into the lambda cold dark matter LCDM model, which predicts the universe's age with remarkable accuracy. Another critical method is measuring the Hubble constant, the rate at which the universe is expanding. This is done by determining the distances to distant galaxies and their recession velocities, primarily using observations of type 2a supernovae and redshift. By plotting these distances against their velocities, astronomers construct the Hubble diagram, which allows them to calculate the current expansion rate. Once this rate is known, and combined with models of how it has changed over time, astronomers can backtrack to the Big Bang and estimate the universe's age. Lastly, astronomers also estimate the ages of the oldest star clusters, particularly globular clusters, which are tightly packed groups of ancient stars. By studying these clusters, scientists gain additional insight into the universe's timeline and further confirm the robustness of the 13.8 billion-year-old estimate. This combined knowledge of the universe's expansion, the distribution of dark energy, and the detailed study of ancient cosmic structures provides us with a profound understanding of the cosmos, its past, present, and ultimately, its future. By examining the properties of distant stars, particularly on the Hertzsprung-Russell HR diagram, a plot showcasing stellar brightness against temperature, scientists can estimate the ages of these celestial bodies. These estimates are grounded in well-established stellar evolution models, offering insights into the star's life cycle. The oldest globular clusters, which contain some of the universe's most ancient stars, are thought to be around 13 billion years old, providing a lower bound for the universe's age. As a result, these various methods converge on a consistent age estimate, reinforcing our understanding of the cosmos and the timeline of its evolution. This alignment of different observational techniques strengthens the confidence in the current age estimate of the universe, allowing us to piece together a coherent narrative from the Big Bang to the present day. In the vast tapestry of the universe's history, one fascinating topic is the existence of primordial black holes, PBHs. These hypothetical black holes could have formed in the earliest moments of the universe, shortly after the Big Bang, through processes distinct from the collapse of stars. If they exist, PBHs could provide a critical window into the conditions that prevailed in the infancy of the cosmos, potentially unlocking answers to some of the universe's greatest mysteries. One of the most compelling aspects of primordial black holes is their possible connection to dark matter, the mysterious substance that makes up about 27% of the universe's mass energy content. Unlike ordinary matter, dark matter neither emits, absorbs, nor reflects light, making it virtually invisible to conventional observational techniques. It can only be detected through its gravitational effects. PBHs, being massive and non-luminous, are prime candidates for this elusive form of matter. If a substantial portion of dark matter were made up of primordial black holes, it could explain various gravitational phenomena that are currently attributed to dark matter. For example, the unexpected rotational speeds of galaxies and the peculiar motion of galaxy clusters might be more easily understood if PBHs were playing a role in shaping the gravitational landscape. Another fascinating possibility involves the potential role of PBHs in the formation of supermassive black holes, the titanic cosmic giants that reside at the centers of galaxies. These supermassive black holes can possess masses billions of times that of the Sun. The formation and rapid growth of these black holes during the early universe remain one of the greatest enigmas in modern astrophysics. If PBHs formed early in the universe's history and had a head start, they could have merged and accreted matter far more efficiently, accelerating the growth of these supermassive black holes in a manner that would otherwise take much longer. This connection could provide key insights into how the most massive objects in the universe came into existence. PB8s are also crucial to understanding the dynamics of the early universe itself. Their formation is believed to be linked to density fluctuations in the primordial cosmos. If the density of a particular region exceeded a critical threshold, it could collapse, forming a black hole. Studying these density fluctuations could shed light on the physical conditions that governed the early universe, probing energy scales that are unattainable by current particle accelerators like the Large Hadron Collider. Moreover, primordial black holes could have left a lasting imprint on the universe's history, particularly through their evaporation via Hawking radiation. This theoretical process suggests that black holes slowly lose mass and emit particles over time, a phenomenon that could have produced high-energy particles and photons. These emissions could be contributing to the background radiation we observe today. Some gamma-ray bursts or cosmic ray events that remain unexplained could potentially be linked to this very process. By studying these potential imprints, we may uncover vital clues about the universe's early stages and its evolving structure. The significance of primordial black holes extends far beyond their theoretical existence. They may help to elucidate the composition of dark matter, explain the rapid formation of supermassive black holes, and provide a crucial window into the early universe's density fluctuations. Their theoretical evaporation might also offer observable effects, contributing to our understanding of the universe's history and evolution. Research into PBHs continues to be a dynamic and speculative field, with scientists working tirelessly to confirm their existence and understand their potential role in the larger cosmological framework. The composition of the universe has undergone dramatic transformations since the Big Bang, evolving from a state of extreme simplicity to its current intricate mixture of various forms of matter and energy. Understanding this evolution provides crucial context for how the universe has developed over the past 13.8 billion years, offering us a glimpse into the past that shapes our present understanding of the cosmos. In the beginning, the universe existed in an incredibly hot, dense, and energetic state. This phase, just moments after the Big Bang, was crucial in the formation of the universe's most fundamental components. During this initial few minutes, a period known as Big Bang nucleosynthesis took place, where the universe's first light elements were created. As the universe expanded and cooled, protons and neutrons came together to form the simplest elements: hydrogen, helium, and trace amounts of lithium and beryllium. Around 75% of the universe's mass was made up of hydrogen, with approximately 25% in helium, while the remaining mass consisted of these minute quantities of heavier elements. This primordial composition has remained largely unchanged in regions of the universe that haven't undergone significant star formation. As the universe continued to expand and cool, it entered a phase known as the Cosmic Dark Ages. This period lasted until the first stars and galaxies began to emerge, about a few 100 million years later. During this time, the universe was still primarily composed of hydrogen, helium, and dark matter, with no stars to illuminate the vast emptiness. The birth of the first stars marked a turning point in the universe's evolution. These early stars, known as population 3 stars, were massive, hot, and short-lived. Their intense heat and pressure ignited nuclear fusion in their cores, initiating a process that would forever change the universe: stellar nucleosynthesis. In the hearts of these stars, hydrogen and helium fused to form heavier elements, those we refer to as metals in astronomical terms. When these stars reached the end of their lives and exploded as supernovae, they expelled these newly formed elements into the surrounding interstellar medium. This enrichment of the surrounding gas slowly increased the metallicity of the universe, paving the way for the next generations of stars to form. As more and more stars lived and died, heavier elements continued to accumulate, contributing to the chemical diversity we observe in the universe today. Simultaneously, galaxies began to form. The formation of galaxies was driven by the gravitational collapse of dark matter halos, which also had a profound effect on the composition and evolution of the universe. Galaxies are like factories for star formation and element generation, where cycles of stellar birth, evolution, and death continue to shape the cosmos. Through these ongoing cycles, the universe became richer in diversity, from the elements to the structures we observe. A mysterious substance, dark matter, also plays a crucial role in the formation and structure of the universe. Though it doesn't interact with electromagnetic radiation, meaning it neither emits, absorbs, nor reflects light, it constitutes about 27% of the universe's mass and energy content today. The nature of dark matter remains one of the greatest unsolved mysteries of cosmology. However, it's clear that dark matter exerts a profound influence on the universe through its gravitational effects. It shapes the formation and evolution of galaxies and large-scale structures, playing a central role in the cosmic web. But perhaps the most groundbreaking discovery in recent cosmological history was the revelation of dark energy in the late 1990s. Dark energy is a mysterious form of energy that permeates all of space, pushing the universe apart and causing its expansion to accelerate. Now believed to make up around 68% of the universe's total energy density, dark energy is fundamentally different from dark matter. While dark matter is associated with the formation of cosmic structures, dark energy influences the very expansion and geometry of the universe, altering its future trajectory. Over time, the universe's composition has evolved dramatically. It began as a simple blend of hydrogen, helium, and traces of heavier elements. Today, the universe consists of a complex interplay between ordinary matter, and dark energy. This evolution has been the driving force behind the formation of stars, galaxies, and the larger cosmic structures we observe in the universe. These forces, cosmic, invisible, and powerful, have shaped the universe into a vast and intricate expanse that continues to evolve in ways that scientists are only beginning to understand. The holographic principle, one of the most provocative ideas in theoretical physics, challenges our very understanding of the universe. It suggests that everything within a given volume of space, all its information, can be encoded on the boundary of that space, much like a hologram. This concept, which emerged in the 1990s, reshapes the way we think about space, time, and gravity. Initially rooted in the study of black holes and quantum mechanics, it offers profound implications for the fabric of the cosmos itself. The holographic principle first gained attention through the groundbreaking work of physicists Gerard 't Hooft and Leonard Susskind. They proposed an astonishing idea: the maximum amount of information, or entropy, that can be contained in a region of space is proportional not to the volume of that space, but to the area of its boundary. This insight means that, in some sense, the universe we experience in 3 dimensions might actually be a projection from a 2-dimensional surface. Our world, which we perceive as tangible and vast, could be nothing more than a sophisticated holographic image. A key motivation behind this theory comes from the study of black holes. The work of renowned physicists Stephen Hawking and Jacob Bekenstein revealed a crucial feature of black holes. They possess entropy, a measure of the information contained in them. But remarkably, the entropy of a black hole is proportional to the area of its event horizon, not its volume. This discovery led to the realization that the information about a black hole and potentially all of space could be encoded on the surface of its boundary, sparking a shift in our approach to the very nature of spacetime. In the world of string theory, the holographic principle took on a more formal and mathematical form. In 1997, physicist Juan Maldacena proposed the anti-de Sitter conformal field theory, ADS-CFT correspondence, a duality between string theory in a higher dimensional space and a conformal field theory on the boundary of that space. This groundbreaking conjecture implies that a theory of gravity within a volume of space might be fully described by a quantum field theory on its boundary. A theory without gravity. This concept doesn't just open up new vistas for understanding gravity and spacetime. It also suggests that the entire universe could be understood through data encoded on its boundary. If the holographic principle holds true for our universe, it would lead to a radical transformation of our understanding of reality. It suggests that the physics of any given region in space could be fully captured by the information on the boundary of that region. In this way, our seemingly three-dimensional universe could be a holographic projection, with all its complex interactions and phenomena emerging from simpler, two-dimensional data. This concept challenges the very structure of reality as we know it, offering new perspectives that could bridge the gap between quantum mechanics and general relativity, two pillars of modern physics that have long been seen as incompatible. But the implications don't stop there. The holographic principle also holds promise for addressing some of the most profound questions in cosmology. Could the observable universe itself be a holographic projection, with its boundaries stretching all the way to infinity? Could the principle provide insights into the mysteries of dark energy or even the ultimate fate of the universe? The holographic principle suggests that the answers to these questions might be found not in the bulk of the universe, but on its outer edges, encoded in data that could revolutionize our understanding of the cosmos. Beyond its implications for cosmology, the holographic principle might also serve as a key to unlocking the elusive theory of quantum gravity, a theory that could unify the macroscopic laws of general relativity with the microscopic principles of quantum mechanics. While the holographic principle remains unproven and lacks direct experimental evidence, its potential to reshape our understanding of the universe has made it a central topic of study in contemporary theoretical physics. At its core, the holographic principle challenges our conventional notions of reality. It compels us to question what we know about space, time, and matter, and to reconsider the very nature of the universe itself. As research in this field continues, we may find that the universe is far more complex and far more interconnected than we ever imagined. In parallel with the holographic principle, the theory of parallel universes, especially the many worlds interpretation of quantum mechanics, provides an equally mind-bending framework for understanding quantum phenomena. Proposed by Hugh Everett III in 1957, the many worlds interpretation offers an attempt to explain the strange behavior of particles in quantum mechanics, where they exist in multiple states at once until they are observed. This interpretation challenges the classical understanding of reality, suggesting that every quantum event spawns a new universe, a parallel reality where all possible outcomes are realized. It's a theory that, like the holographic principle, forces us to reconsider the very nature of existence and the reality we perceive. Both theories point to a future where our understanding of the universe may be completely transformed, where dimensions and boundaries are not as fixed as they once seemed, and where new technologies and perspectives could redefine what we know about space, time, and the very essence of reality itself. In the world of quantum mechanics, the act of measurement forces a system to collapse into one of its possible states. The traditional Copenhagen interpretation suggests that this collapse occurs randomly upon measurement. However, there's a different perspective offered by the many worlds interpretation, MWI. It proposes that instead of the wave function collapsing into one state, all possible outcomes of quantum measurements actually occur, but in separate, parallel universes. Rather than collapsing into a single reality, the universe splits into multiple non-interacting branches, each representing a different outcome. For example, in one universe, Schrödinger's cat is alive, while in another, it is dead. This view provides a deterministic framework where the quantum system evolves smoothly and continuously, with no need for collapse. Every possible state of a system's wave function manifests in a branching universe, allowing all potential outcomes to coexist simultaneously, but in different realities. This eliminates the randomness often associated with quantum mechanics and negates the need for a special role for the observer. In this framework, all components of the quantum system, including the measurement devices, are treated as quantum objects, governed by the same fundamental rules. The idea of parallel universes provides compelling explanations for various quantum phenomena. Quantum entanglement, for instance, is addressed within the MWI by suggesting that when two particles become entangled, their combined wave function spans across multiple universes. Each outcome reflects a different reality, where the measurement results of the entangled particles are correlated across these branches. This approach resolves the issue of spooky action at a distance, as each universe contains its own consistent outcome, with no need for instantaneous communication between distant particles. In terms of quantum superposition, the existence of multiple universes offers a natural explanation. Rather than a particle being in multiple states simultaneously, it exists in one state in each universe. This eliminates the paradox of superposition and gives rise to a more elegant view of quantum behavior. Quantum interference phenomena like the famous double-slit experiment can also be understood within the MWI framework. When particles display wave-like interference patterns, these patterns can be seen as the interactions between different branches of the universe. Each possible path a particle might take corresponds to a different universe, and the interference arises from the coherent superposition of all these paths. Despite its mathematical consistency and the deterministic view it offers, the many worlds interpretation is not without challenges. One of the major issues is testability. The existence of parallel universes remains beyond our ability to empirically verify, as we cannot observe or interact with these other branches of reality. This makes the theory difficult, if not impossible, to confirm through traditional scientific methods. Furthermore, MWI requires a profound reimagining of reality itself, raising philosophical questions about existence and identity in the context of multiple parallel universes. Nevertheless, theories like the many worlds interpretation provide a coherent and thought-provoking explanation for various quantum phenomena. They allow for the coexistence of all possible outcomes of quantum events in an expansive multiverse of branching realities. While MWI remains a topic of theoretical debate, it continues to inspire discussions and research in both physics and philosophy, pushing the boundaries of how we understand the fundamental nature of the universe. Quantum entanglement, one of the most puzzling phenomena in quantum mechanics, involves the interconnection of particles in such a way that the state of one cannot be described without reference to the state of the other, regardless of the distance between them. This strange relationship persists no matter how far apart the particles are. Once entangled, a change in the state of one particle will instantaneously affect the state of the other, defying classical expectations that information cannot travel faster than the speed of light. This phenomenon was famously described in a 1935 thought experiment by Albert Einstein, Boris Podolsky, and Nathan Rosen, known as the EPR paradox. Einstein referred to this instantaneous connection as spooky action at a distance, highlighting the tension between quantum non-locality and classical physics' insistence on local reality. Entanglement challenges our understanding of space and time in profound ways. In classical physics, objects have well-defined positions and velocities, and interactions occur locally, either through direct contact or via fields propagating at the speed of light. Quantum entanglement, however, defies this locality. Once two particles are entangled, measuring one particle's state instantly determines the state of the other, regardless of the spatial separation. This instantaneous correlation suggests a kind of communication or connection that transcends the limitations imposed by the speed of light, implying that distance works differently in the quantum realm. Another intriguing aspect of entanglement is its temporal independence. Unlike classical interactions where effects gradually weaken over time or distance, the entangled particles' connection does not diminish, no matter how far apart or how much time passes. This challenges our fundamental understanding of time and space, further deepening the mystery surrounding the quantum world. As we continue to explore these phenomena, the many worlds interpretation offers a fascinating lens through which we can rethink quantum mechanics, even if it remains a topic of intense debate. Entanglement, in the realm of quantum mechanics, represents a fascinating and perplexing phenomenon that challenges our classical understanding of the universe. When two particles become entangled, changes to the state of one particle are instantly mirrored in its entangled partner, no matter the distance or time difference between them. This instantaneous connection, defying the boundaries of space and time, raises profound questions about the very fabric of reality. It challenges our classical views of past, present, and future, urging us to rethink the very nature of time and how we perceive it within the quantum context. This entangled state also throws classical realism into disarray. The traditional notion suggests that particles exist with well-defined properties, independent of any measurement or observation. However, in the quantum world, particles in an entangled state do not retain individual, independent properties. Instead, their properties are inherently linked. Observing one particle in an entangled pair immediately determines the state of the other, defying the classical idea that objects possess inherent properties regardless of whether they are observed. This departure from classical expectations leads us to reconsider the nature of reality itself. John Bell's groundbreaking work and subsequent experiments only deepen the mystery of quantum entanglement. Bell formulated a series of inequalities to test the predictions of quantum mechanics against those of local hidden variable theories, which attempt to explain entanglement using local realism. The results of numerous experiments consistently violated Bell's inequalities, offering strong evidence that quantum entanglement cannot be explained by any local hidden variable theory. This experiment underscored the non-local, non-classical nature of quantum mechanics, further cementing the idea that our understanding of the universe must extend beyond classical principles. The implications of quantum entanglement are both philosophical and practical. On a deeper level, it forces us to reconsider the fundamental structure of the universe and the interconnectedness of all things. It challenges our classical concepts of space, time, and even reality itself. On a more practical level, quantum entanglement is already driving the development of cutting-edge technologies like quantum computing and quantum cryptography. Quantum computers promise to harness the power of entanglement to solve complex problems that classical computers cannot even begin to tackle. These quantum machines could revolutionize fields like cryptography, medicine, and artificial intelligence by performing calculations at speeds unimaginable by today's standards. Quantum cryptography, for instance, uses entanglement to create theoretically unbreakable encryption systems. Any attempt to eavesdrop on entangled particles disrupts their delicate state, alerting the parties involved to the intrusion. This makes quantum cryptography a potentially revolutionary tool for securing communications in an increasingly digital world, offering a level of security previously thought unattainable. Quantum entanglement exemplifies the profound and often bewildering connections that exist between particles at the quantum level. These connections challenge our classical notions of space and time, suggesting that the universe operates on principles far more subtle and interconnected than those we observe in our everyday macroscopic world. In parallel with the development of quantum mechanics, the quest for a unified theory of gravity remains one of the greatest challenges in physics. Enter loop quantum gravity, LQG, an ambitious theoretical framework that seeks to merge the smooth, continuous nature of general relativity with the probabilistic, discrete world of quantum mechanics. This unification aims to resolve the deep contradictions between these two foundational theories, addressing one of the most significant problems in modern physics: how to reconcile the vast scale of the universe with the infinitesimal particles that populate it. While string theory posits that the fundamental building blocks of the universe are one-dimensional strings, LQG takes a different approach. Instead of seeking a deeper, hidden structure beneath the fabric of space, LQG quantizes space-time itself. General relativity, which describes gravity as the curvature of smooth, continuous space-time, is at odds with the probabilistic nature of quantum mechanics. This incompatibility leads to complex mathematical issues when attempting to apply quantum principles to general relativity's smooth spacetime. Loop quantum gravity offers a solution by suggesting that spacetime is not smooth, but rather composed of discrete, quantized units, providing a new way to look at the universe at its most fundamental level. This vision of spacetime as discrete rather than continuous could pave the way for a deeper understanding of the universe. It may unlock new insights into the nature of black holes, the Big Bang, and the very structure of the cosmos itself, offering a unified theory that could explain both the vast scale of the cosmos and the minute particles that make it all up. In this delicate balance between quantum mechanics and general relativity, the quest for understanding continues. Each breakthrough, each experiment brings us closer to unraveling the deep, hidden truths of the universe, truths that may one day redefine our place within it. According to loop quantum gravity, LQG, the very fabric of spacetime is constructed from finite loops, intricately woven into a delicate and complex network known as a spin network. These loops, or spin networks, represent the fundamental building blocks of the universe, and their interactions dictate the geometry of spacetime, particularly at the Planck scale, a mind-bogglingly tiny scale around 10 to the power of minus 35 meters. At this minuscule scale, the continuous nature of spacetime that we experience at macroscopic levels breaks down into a granular structure governed by quantum principles. One of the key ideas in loop quantum gravity is the quantization of geometry. In LQG, geometric properties like area and volume are not continuous. Instead, they exist in discrete, indivisible units, much like energy levels in an atom. This is a crucial departure from classical physics, where these quantities are seen as continuous. Calculations within LQG suggest that areas and volumes possess a minimum value, what's known as a quantum of space. This prevents the singularities and infinities that plague classical general relativity, particularly those that arise at the centers of black holes or during the Big Bang. In this quantum framework, the infinite densities that general relativity predicts no longer exist, offering potential solutions to some of the most perplexing problems in cosmology. To investigate the quantum structure of spacetime, LQG employs spectral analysis, a powerful mathematical tool borrowed from quantum theory. This analysis allows physicists to explore the spectrum of geometric operators, offering insights into how space behaves on a microscopic scale. It reveals the quantum mechanical nature of spacetime itself, allowing us to understand the universe in a fundamentally new way, one that is inextricably tied to quantum principles. The loop representation of LQG is another vital aspect of the theory. Unlike classical general relativity, where the equations are expressed using a continuous spacetime metric, LQG reformulates these equations using loop variables. This shift is not just mathematical, it reflects the deeper connection between quantum mechanics and the fabric of spacetime itself, where space and time are no longer separate entities, but part of a unified whole that evolves probabilistically. One of the most remarkable features of LQG is its background independence. This principle echoes the foundational tenets of general relativity, asserting that the theory does not require a fixed, pre-existing spacetime background. Instead, spacetime itself is dynamic, evolving within the theory. The geometry of the universe is not a static stage on which events unfold, but a malleable entity that changes over time. For any quantum gravity theory to succeed, it must accommodate this dynamism, and LQG offers a framework that allows for this constant evolution. Within LQG, spacetime is conceptualized as evolving through discrete steps. The evolution of spin networks is captured using a structure called a spin foam, which depicts how the spin networks change over time. This approach is akin to considering spacetime as a kind of quantum foam, constantly fluctuating and evolving, much like the frothy surface of a boiling pot. These fluctuations happen at the Planck scale, where quantum effects dominate, leading to a picture of spacetime that is much more complex and fluid than the smooth, continuous surface we observe at larger scales. Loop quantum gravity has provided new ways to approach classical problems that have long eluded solutions. For example, LQG offers a potential resolution to the singularities found in black holes and the Big Bang. Unlike classical general relativity, which predicts that black holes contain infinite densities at their centers, LQG suggests that such singularities do not exist. Instead of a singularity, LQG predicts a bounce, a point where gravitational forces become repulsive at extremely high densities. This theory proposes that, rather than collapsing into a point of infinite density, black holes could potentially give rise to new regions of space, or even new universes. This idea could completely reshape our understanding of black holes and their role in the universe. While loop quantum gravity is still a developing field, it represents a promising avenue for understanding the quantum nature of spacetime and bridging the gap between general relativity and quantum mechanics. As research advances, experiments and observations may provide further insights into this theoretical framework, helping to validate or refine LQG and bringing us closer to a complete understanding of the fundamental workings of the cosmos. Another fascinating field that intersects with loop quantum gravity is cosmic topology. This branch of cosmology studies the large-scale shape, size, and structure of the universe, beyond the local geometric properties described by general relativity. While general relativity explains the curvature of space-time due to mass and energy, cosmic topology delves into the global structure of the universe, how it might be connected, wrapped, or finite in its overall form. The shape of the universe is often discussed in terms of both its geometry and its topology. The geometry of the universe tells us about its local curvature, whether it is flat, positively curved, or negatively curved. Observations from the cosmic microwave background, particularly from missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, suggest that the universe is very close to being flat, offering valuable clues about its overall structure and the forces shaping its evolution. As research in both LQG and cosmic topology progresses, our understanding of the universe's fundamental structure continues to deepen, paving the way for breakthroughs that could answer some of the most profound questions about the nature of reality itself. However, this local flatness doesn't exclude the possibility of more intricate global structures. Cosmic topology delves into one of the most fundamental questions of the universe. Is it finite or infinite? And if it is finite, what is its shape? For a flat universe, several possibilities emerge, each more fascinating than the last. The simplest of these possibilities is an infinite flat universe. In this scenario, the universe extends endlessly in all directions without any repetitions, much like an infinite plane. But there's another equally captivating idea: a finite flat universe with identifications. This model suggests that although the universe appears flat, it could still be finite if its spatial dimensions curve back onto themselves. Picture a flat surface where opposite edges are linked together to form a cylinder. Now, if the ends of that cylinder are also connected, we get a three-dimensional version of a donut. This is called a torus. In higher dimensions, this concept can allow for a finite universe with no edges, where traveling far enough in any direction brings you back to your starting point. Alternatively, the universe could possess positive curvature, leading to a spherical topology. In this case, the universe would be closed and finite, akin to the surface of a sphere. Travelers journeying in any direction would eventually return to their starting point, just as anyone walking across the surface of the Earth would do. The three-dimensional analog of this is a three-sphere, an extension of a spherical surface into higher dimensions. On the flip side, a negatively curved universe could be hyperbolic, with multiple connected finite regions that form a tessellated pattern. This highly complex configuration might suggest a universe that is finite but unbounded, with its space intricately covered in patterns far more complex than those of flat or positively curved spaces. Scientists are using a variety of methods to study cosmic topology and its implications. One of the most crucial tools in this investigation is the Cosmic Microwave Background, CMB, a snapshot of the universe's early stages. By analyzing the patterns and correlations within the CMB, scientists can gain insight into the universe's global structure. For instance, matching circles or repeating patterns in the CMB might point to a multi-connected topology, where the same region of space appears in different parts of the sky due to spatial wrapping. In addition, large-scale galaxy surveys examine the distribution of galaxies and clusters, revealing patterns that might suggest a non-trivial topology. Another fascinating aspect of cosmic topology involves the study of cosmic rays and light paths. By tracking the paths of high-energy particles and light from distant quasars or gamma-ray bursts, scientists can detect intersecting paths that hint at the existence of a finite universe. These unusual patterns might provide additional evidence for a universe with a complex finite structure. The study of cosmic topology is pushing the boundaries of our understanding, providing new perspectives that go beyond the conventional models of an infinite or finite universe. While much of this research remains theoretical and difficult to test empirically, advancements in observational cosmology are opening up new possibilities to explore the universe's true shape and structure. But there's an even more mind-bending idea that ties into this discussion, the simulation hypothesis. This theory proposes that our entire reality could be an advanced digital construct created by an intelligent entity, potentially a future civilization. Philosophers and physicists have long debated the plausibility of this idea, weaving it into the realms of philosophy, physics, and computer science. In his groundbreaking paper, philosopher Nick Bostrom proposed a probabilistic framework for the simulation hypothesis based on three core ideas. First, that technological advancement will eventually enable civilizations to simulate entire universes with incredible precision. Second, that these civilizations might create simulations of their ancestors or historical events for research or entertainment. And third, that the vast number of simulated universes would make it far more likely that we are living in one, rather than the original base reality. The argument is further bolstered by analogies to our own technological progress. Video games, virtual reality, and computational simulations of the physical world are becoming increasingly sophisticated, suggesting a future where simulations could be indistinguishable from reality. Advocates of the simulation hypothesis point to several key aspects that support their view. For instance, digital physics proposes that the universe exhibits properties that resemble sophisticated computation. The quantized nature of space and time, as well as the discrete energy levels in quantum mechanics, all suggest that the universe might function like a digital system, governed by underlying computational processes. Furthermore, the fine-tuning of physical constants, those improbably precise values that allow for complex structures like galaxies, stars, planets, and life, could be interpreted as deliberate settings by the creators of the simulation. The very structure of the universe might have been crafted to achieve specific outcomes. The concept of information theory also plays a role in this theory, as the increasing emphasis on information and computation in theoretical physics suggests that reality itself might be informational in nature, further aligning with the idea of a simulated universe. Unexplained phenomena, such as peculiar behaviors of particles or unresolved paradoxes, are also cited as potential glitches in the simulation, signs that we are experiencing errors or anomalies in an artificial construct. Yet, critics of the simulation hypothesis argue that its unfalsifiability presents a major challenge. If the simulation is perfect or nearly so, any evidence we collect could itself be part of the simulation, making it virtually impossible to disprove using conventional scientific methods. As these theories unfold, they continue to reshape our understanding of the universe's nature. Could we be living in a simulation? Is the universe finite or infinite? These are questions that scientists and philosophers alike are still grappling with, as they continue to explore the deepest mysteries of our existence. Some argue that Bostrom's probabilistic approach is based on assumptions that may not hold true, such as the motivations and capabilities of future civilizations. Despite the difficulties in proving or disproving the simulation hypothesis, it continues to provoke thought-provoking discussions and research across various disciplines, sparking deep reflections on the nature of reality, consciousness, and the future of technology. Whether we exist in a base reality or a simulated one, exploring these ideas pushes the boundaries of our understanding, presenting new perspectives on the universe and our place within it. The cosmic censorship hypothesis, first proposed by Roger Penrose in 1969, addresses the nature of singularities produced by gravitational collapse and their potential visibility. Singularities are regions in space where the curvature of space-time becomes infinite, and the laws of physics, as we know them, cease to apply. There are two primary forms of the cosmic censorship hypothesis: the weak and strong cosmic censorship hypotheses. The weak cosmic censorship hypothesis suggests that singularities arising from gravitational collapse are hidden within event horizons, the surfaces of black holes. This ensures that these singularities are censored from distant observers, preserving the predictability of the external universe, which remains governed by classical physics. Since information about the singularity cannot influence regions outside the event horizon, the structure of space and time remains unaffected. On the other hand, the strong cosmic censorship hypothesis argues that the deterministic nature of general relativity holds even during the collapse process. According to this view, the laws of physics should predict the future uniquely, given an initial distribution of matter and energy, ensuring that singularities cannot disrupt the overall predictability of the universe. The significance of the cosmic censorship hypothesis is multifaceted. First, it preserves the predictability of general relativity, meaning that the future evolution of spacetime is determined by its initial conditions. Without this safeguard, if naked singularities, those not hidden within event horizons, existed, they would lead to regions where the laws of physics break down, resulting in a loss of determinism. The weak cosmic censorship hypothesis prevents this by ensuring that singularities are hidden within black holes. Second, it maintains the mathematical consistency of general relativity. Exposing singularities to the broader universe would mean standard physical theories no longer apply, creating undefined or infinite quantities that conflict with known physics. The hypothesis offers a safeguard against this, preserving logical coherence. In addition, the cosmic censorship hypothesis plays a critical role in astrophysical scenarios, particularly in understanding the formation of black holes from collapsing massive stars. Observations of black holes and their properties are consistent with the hypothesis, further supporting its validity. It also contributes to our understanding of the life cycle of stars, the formation of galaxies, and the behavior of matter under extreme gravitational forces. Furthermore, the study of cosmic censorship intersects with the quest for a unified theory of quantum gravity. If we can determine whether singularities are hidden or exposed, it might provide key insights into the nature of spacetime at incredibly small scales and high energies, where quantum gravitational effects become significant. The implications of the cosmic censorship hypothesis extend beyond the black hole framework, touching on broader cosmological questions about the universe's evolution, its initial conditions, and its ultimate fate. The nature of singularities is closely tied to the mysteries of the Big Bang, cosmic inflation, and the dynamics of spacetime. While the hypothesis remains unproven, it continues to be a central pillar in understanding the extreme phenomena of the universe. Ongoing research is dedicated to either proving or challenging the hypothesis, refining our knowledge of the universe's most elusive and intense phenomena. The theory of eternal inflation further expands upon the concept of cosmic inflation, proposing that our observable universe is only one among many bubble universes in a larger multiverse. First suggested by physicist Alan Guth and later extended by André Linde and others in the 1980s, eternal inflation builds upon the inflationary model, which posits that the early universe underwent rapid exponential expansion following the Big Bang. At the heart of this model is the scalar field known as the inflaton, which drives this accelerated expansion. The inflaton's potential energy landscape determines the behavior of inflation, and in many models, it is nearly flat. This causes the field to roll slowly, creating a rapid expansion during the inflationary period. Quantum mechanical fluctuations in the inflaton field cause different regions of space to experience varying rates of inflation. Some regions inflate faster than others, even as inflation begins to slow down or cease. Due to these fluctuations, certain regions of space continue to experience rapid exponential expansion, never settling into a stable state. These regions can form bubbles, where inflation halts and a more typical universe like our own can emerge. This self-reproducing nature of inflation makes it eternal on large scales, leading to an infinite number of bubble universes, each with potentially distinct physical properties. These differences might include variations in fundamental constants, the types of particles present, or even different laws of physics. This framework offers a natural mechanism for creating a vast ensemble of universes, each potentially unique. The concept of eternal inflation implies that an infinite number of bubble universes exist, each with potentially different laws of physics and constants. This diversity might help explain the fine-tuning of our universe's parameters, suggesting that we live in a universe with conditions suitable for life, because such universes are among the countless possibilities. In this context, the anthropic principle, which states that the universe's laws and constants are as they are because they permit life to exist, gains a new meaning within the multiverse framework. If infinite universes exist, some of them would inevitably have the conditions necessary for life, making our seemingly fine-tuned universe less surprising. Testing eternal inflation directly is challenging because the other bubble universes would be causally disconnected from our own. However, some cosmologists speculate that traces of collisions between our bubble and others might be detectable in the cosmic microwave background or large-scale structures. Finding such signatures could provide indirect evidence of the multiverse. The existence of a multiverse carries profound implications for fundamental physics, as it challenges the idea of a single, unique set of physical laws governing everything. Instead, it suggests that our understanding of physics could be local, contingent upon the specific configuration of our universe within the multiverse. Eternal inflation transforms the inflationary paradigm, moving from a model that explains the early universe's rapid expansion to a grander vision of an ever-expanding, infinitely diverse multiverse. While direct evidence remains elusive, the theory offers compelling explanations for some of the most perplexing aspects of our universe, prompting deep theoretical and philosophical exploration. Quantum foam, or space-time foam, describes the fluctuating, turbulent nature of spacetime at the smallest scales, proposed by physicist John Wheeler in the 1950s. At the Planck scale, around 10 to the power of negative 35 meters, spacetime is not smooth and continuous, but instead exhibits a frothy, foamy structure due to quantum mechanical effects. This quantum foam is a crucial concept in understanding the nature of spacetime at the most fundamental level, where classical physics breaks down and quantum effects dominate. In the realm of modern physics, there exists a profound and mind-boggling concept: quantum foam. Emerging from the intersection of quantum mechanics and general relativity, this idea challenges our traditional understanding of the universe's fabric. At the heart of it lies the Heisenberg uncertainty principle, a foundational concept that dictates there is a fundamental limit to how precisely certain pairs of physical properties can be known simultaneously. For instance, we cannot measure both the position and momentum of a particle or the energy and time intervals of an event with perfect accuracy. This uncertainty takes on a new significance when applied to the Planck scale, the incredibly tiny scales of space and time where quantum mechanics governs the universe. Here, the Heisenberg principle implies that energy and space-time geometry itself are not fixed, but fluctuating, causing rapid and unpredictable changes at these small scales. Space and time at this level are not smooth and continuous, but are instead characterized by a frothy, turbulent structure. This is the essence of quantum foam. According to this theory, at the smallest distances, space-time itself is no longer the stable, smooth continuum depicted in general relativity. Instead, it behaves more like an ever-changing sea of energy fluctuations. Temporary distortions in the fabric of space-time, like sudden bends or twists, constantly form and disappear. These distortions can manifest as miniature versions of some of the most bizarre features predicted by physics, such as micro black holes, miniature wormholes, and other exotic topological phenomena that we would never encounter on larger macroscopic scales. To understand the context, consider general relativity, which models space-time as a smooth, continuous fabric that is warped by the presence of mass and energy. While this model works brilliantly for large-scale phenomena like planets and galaxies, it completely breaks down when applied to the quantum realm, the very smallest scales of space and time. This is where quantum foam comes into play. It suggests that space-time at the Planck scale is dynamic, granular, and fundamentally different from the smooth continuum we experience in our everyday lives. This concept is at the very heart of the search for quantum gravity, a theoretical framework designed to unify quantum mechanics with general relativity. The unification of these two pillars of physics is no easy feat, and it's here that quantum foam may play a crucial role. Theoretical approaches like loop quantum gravity, LQG, and string theory are two such attempts to understand spacetime at the Planck scale. In LQG, for example, spacetime is described as being quantized, made up of discrete loops or spin networks that form the foamy structure at the smallest scales. These quantum fluctuations at the Planck scale challenge our classical understanding of the universe. Instead of thinking of space as a smooth, unchanging backdrop to the events of the cosmos, Quantum foam paints a picture where space-time itself is fluctuating and granular, with every point in space constantly shifting and vibrating. These fluctuations may be responsible for the behavior of particles and forces, influencing the very constants of nature that we observe, such as the speed of light or the strength of gravitational forces. The universe at its core may not be as stable and unchanging as it seems at larger scales. One of the key figures in the exploration of quantum effects on spacetime was the renowned physicist Stephen Hawking. His groundbreaking work on black hole radiation provides a perfect illustration of how quantum foam operates in extreme conditions. Hawking theorized that near the event horizon of a black hole, virtual particle pairs constantly appear due to quantum fluctuations. One of these particles falls into the black hole while the other escapes. This process results in what we now know as Hawking radiation, a phenomenon that challenges traditional views of black holes and suggests that quantum effects play a crucial role in their behavior. Through his research, Hawking reinforced the notion that quantum mechanics is deeply intertwined with the nature of spacetime. The concept of quantum foam helps explain why black holes behave the way they do, and it may even offer answers to some of the most perplexing questions about the universe. Quantum foam may be the key to understanding not only the workings of black holes, but also the nature of the universe itself. Furthermore, quantum foam might also hold clues about the fundamental constants of nature, the very values that govern the behavior of particles and forces in our universe. The fluctuations at the Planck scale may influence the fundamental properties of particles, possibly explaining why certain constants, such as the gravitational constant or the fine structure constant, have the values we observe today. As we push the boundaries of quantum physics, general relativity, and cosmology, the concept of quantum foam continues to spark wonder. It challenges our ideas of space and time, suggesting that the universe is far more dynamic and strange than we could have ever imagined. With future advancements in physics, we may one day unravel the mysteries of the quantum realm and understand just how quantum foam shapes the universe on the most fundamental level. Quantum foam, a theoretical construct, is deeply connected to the concept of vacuum energy, the underlying energy present in empty space driven by quantum fluctuations. This vacuum energy isn't just a passing curiosity, it has profound implications. It plays a key role in shaping the cosmological constant, a pivotal element in understanding dark energy, which in turn influences the large-scale structure and the accelerated expansion of the universe. As research in quantum gravity advances, the role of quantum foam becomes ever more fascinating. It offers a tantalizing glimpse into the underlying fabric of space-time, potentially revealing the foundational principles that govern not just the cosmos, but the very nature of reality itself. Yet quantum foam is not just about energy fluctuations. It connects deeply to one of the most mind-bending ideas in modern physics: the possibility that time, as we know it, may not be a fundamental element of the universe. Traditionally, we view time as the backdrop against which all events unfold. But what if this perspective is wrong? What if time is not a basic, unchanging feature of reality? What if it emerges from deeper, timeless laws and structures, only giving us the illusion of flow? This shift in thinking challenges centuries-old assumptions and opens the door to radically new ways of thinking about the universe. Several theoretical frameworks support this idea that time could be an emergent property. For instance, the thermodynamic arrow of time, which is driven by the second law of thermodynamics, suggests that in a closed system, entropy always increases. From this viewpoint, the direction of time is simply a macroscopic consequence of increasing entropy. In essence, time doesn't flow at the most fundamental level. Rather, the growth of entropy and the unfolding of events give rise to our perception of time moving forward. This raises the possibility that the progression of time might not be inherent, but a product of the laws of physics. In the world of quantum mechanics, this idea gains further traction. Time may emerge from quantum entanglements, relationships between particles that exist in a state of mutual dependence. Carlo Rovelli's relational quantum mechanics takes this further, suggesting that time is not a universal parameter. Instead, it is a measure of the change in relationships between quantum systems. Time, in this view, emerges from the complex web of interactions between particles, and it's defined not by a global clock, but by the dynamics of each unique relationship. Moreover, the holographic principle, a cornerstone of string theory, offers yet another framework for understanding time as an emergent property. The AD-CFT correspondence, a key aspect of this principle, suggests that a higher dimensional gravitational theory can be equivalent to a lower dimensional quantum field theory. Here, time emerges from the entanglements and interactions within the lower dimensional theory, reinforcing the idea that time may not be a pre-existing dimension, but rather something that arises from quantum phenomena. Loop quantum gravity, another theory that reshapes our understanding of spacetime, posits that spacetime is quantized. At the smallest scales around the Planck length, space is not continuous but discrete, made up of structures called spin networks. In this model, time doesn't exist as an independent entity. Instead, it emerges from the evolution of these networks. As spin networks evolve, so too does time. In essence, the very fabric of space-time grows out of these quantum geometries, with time being an emergent property of their relationships and transitions. Causal set theory adds yet another layer to the discussion. This theory suggests that space-time is composed of discrete events ordered by causality, not by pre-existing geometry. These causal events form the underlying structure of space-time, and the perception of a continuous space-time continuum arises only at large scales. Time, in this theory, is a product of the sequential order of these causal events, emerging from a fundamental structure devoid of the smoothness we experience at macroscopic scales. Then there's the radical concept proposed by Julian Barbour in his shape dynamics theory. Barbour imagines the universe not in terms of time, but as a series of geometric relationships between matter. In this framework, time doesn't flow. Rather, it's an emergent phenomenon that arises from the changing configurations of the universe. His idea of time capsules further explores this, suggesting that what we experience as the passage of time is actually just a sequence of distinct configurations of the universe, each encapsulating all the information from the past. What we perceive as the forward march of time is merely a sequence of snapshots in the cosmic timeline. These theories, while still largely speculative, represent a dramatic shift in how we understand the universe. They suggest that time, far from being a constant, flowing force, may emerge from deeper, more abstract laws governing the cosmos. This is an exciting frontier in our quest to understand the true nature of reality. If we can push these ideas to their full potential, they could reveal a radically different picture of the universe, one where time is not a fundamental backdrop, but a consequence of deeper, more complex interactions. Though much of this is still in the realm of theoretical physics, the implications for our understanding of space, time, and reality are profound. We may be on the verge of unlocking a new chapter in our exploration of the cosmos.